Artificial intelligence has been one of the hottest topics in the IT industry since the last 2 years. According to the research done by Grandview Research Organization, by the beginning of 2030, the AI market is predicted to develop at a compound annual growth rate of 38.1%. Not only that, but the projected yearly income in the field of AI is estimated to be approximately 1,811 billion US dollars by 2030. I think this fact itself proves that the future belongs to AI and its dominance in the overall computer science industry. On that note, I welcome all of you guys to this extensive session on artificial intelligence by Intellipaat. With this session, we are going to uncover the basics of AI and a few subdomains involved in it. But before we do that, I request all of you guys to enable that subscribe button and bell icon so that you never miss any update from Intellipaat. First of all, we shall look into the agenda for this session. We'll begin this session on a friendly note by introducing AI to all of you guys. Then we'll try to understand what is intelligence and growth. In the next phase, we'll talk about subdomains of AI named as machine learning and deep learning. Later, we'll talk about limitations of machine learning and introduction to deep learning. Then, by moving one step forward, we'll talk about the intricate details of model building, including topology of a network, artificial neuron, linear regression, activation functions, and their types. After done with that, we'll talk about perceptron training algorithm and computation of a graph. And finally, we'll cover the concept of gradient descent and understanding epochs. I hope I have made myself clear with the agenda. So without wasting any time, let's get started with this session.
I think again the first question is what is artificial intelligence, isn't it? And firstly, I think why should we even study AI? And we looked at a couple of examples. The examples sort of spanned across financial sectors. We looked at transportation. We looked at medical science, healthcare, and medical sciences, gaming, heavy industries, whatnot. I mean, I think right now, AI and ML, artificial intelligence as a field, has really been helping a lot of industries. Starting from trying to build systems that could automatically predict aircraft component failure, or let's say your car component failure, to building systems that can automate mundane tasks like loan approvals or whatnot. Loan approvals, which is a very manual task, you could essentially automate that using very simple artificial intelligence technique. Two complex scenarios, like trying to find two complex scenarios, like for example, in the field of medical sciences or in the world of pharmaceutics, uh, identifying the right kind of drugs is a huge challenge, or identifying, given a particular drug, or given a particular drug, given a combination of drugs, what kind of adverse effects that it could result in. So think about it, right? There's so many different trials of medications that keep going on outside today, but and a lot of data gets collected, mind you. Healthcare sciences, they collect a ton of data because they need to publish papers, and at the end of the day, this is science, right? You're not this is not pseudoscience. At the end of the day, the allopathy, or rather the medical sciences that we currently have, the established medical sciences that we have, is science. And what science requires and deems is, it requires you to provide proofs if a particular medication is useful or not. So to prove that a lot of data is captured, when a lot of data is captured, you need folks to actually go back and look at that data and make sense out of that data. Um, and one of the things that you could do while making sense out of that data is to look at that data and say, hey, look, a combination of these two drugs for a given patient could cause a certain adverse effect. Like, for example, if there are two medicines that are being given to a particular to a particular patient, then you could always highlight and say that, hey, look, these two medicines in combinations could cause a headache, or these two medications in combination could cause, let's say, constipation. And identifying such kind of helping doctors or helping clinical studies is where the AI is playing a very pivotal role right now. Same is the case with leveraging AI in heavy industry. I visited, true story by the way, I visited a battery manufacturing firm, a very, very popular battery manufacturing firm here in India. So these are car batteries, not the remote cells or any of those. These are essentially car batteries, automobile batteries, and these huge batteries that get basically manufactured. This Indian manufacturer, a lot of work is quite manual in process. Like for example, I don't know if you're familiar with the science of how a battery typically gets manufactured. Let me just kind of give you a small intro into it. This is by no means a mechanical engineering session, but I think I kind of want to kind of draw I wanted to kind of let you know the kind of problems that we get to solve. So the battery manufacturing company, what they do is they basically manufacture batteries. So when you look at a battery basically consists, and this is a lead acid battery, right? A lead acid battery basically has a set of plates, right? And these are basically plates. Each of these plates, and they call each of these plates as basically a cell, and there are 6 or 12 different plates, and they're separated by, and they're immersed inside a particular acid. One side is positive and the other side is basically a negative, right? The cathode and an anode. Yeah, correct, exactly. So each of these cells that you see here, each of these plates that you see here is basically a lead plate. It's made out of lead. So what you essentially have is you basically have a grid like structure, and all of this is made out of lead, or PB, plumbum, right? The scientific name. Now, the thing about this particular lead grid is that these grids, when they have certain kind of perforations, like see, imagine the way they manufacture these grids is they have a press machine, and the press machine essentially, uh, you know, uh, you place a lump of lead into it, and then you do run the press, and the press kind of returns this kind of a structure. But when the press doesn't work well, what happens is you at times may see certain perforations, or that the grid is not proper in shape. And as a result, what happens is if this particular grid is not properly made, what happens is that the battery, and if you have a significant aberration in the way this particular grid is generated, or the way this grid is manufactured, the battery in itself can go for a toss. So to make sure that the grid is proper, what they have is on a huge conveyor, they have one man standing over here, and his only responsibility is basically to look at these grids, and he has to basically look at these grids and say, hey, this is good, hey, this is good, hey, this is good, this is not good, let me just kick this out. So this guy's only responsibility over here is to stand and make sure that these grids, manually inspect if these grids are manufactured properly or not. Now, all said and done, the reason I quoted this particular example is because if these grid is not well manufactured, it could typically cause a lot of issues. Because if this guy misses any of these, if there's an actual incorrectly manufactured grid, and if it goes through, then what is likely to happen is it is going to go and sit inside a battery, and they would never know if this particular, it'll work well initially, but then once it is out in the market, it is likely to malfunction. Then when something malfunctions, then warranty kicks in, and there's 100 other issues with things like these, with especially in the battery industry. So this guy basically has to make sure. Of course, this is not the only issue. There are a ton of other issues as well, but this is one of the many issues that the battery industry basically faces. Now the thing is, imagine the challenge that this guy would be facing. Imagine the kind of pressure that this guy has. He's one man, and he's standing there and he's looking all over the place. He's manually inspecting. He's trying to find out if the lead grid is properly manufactured or not. It's a manual manufacturing process. Now imagine what could go wrong, right? Everything possible could go wrong. There's so much pressure, and he's a human being at the end of the day. And beyond a certain point, it just becomes very difficult for somebody to concentrate on the same thing. You would start to have blurred vision. So I was standing here for a couple of hours, for almost an hour or so, and then I was visually manufacturing. I could clearly see one or two things just slip by. Not to kind of undermine this person's abilities. It's just that the nature of work is so mundane. The thing is, can you actually find a way to automate this kind of identifying these? Can you actually put something here that would automatically identify if a particular grid is properly manufactured. So you could essentially put some kind of an AI bot or something over here. And what that would do is that would basically replicate what this man is doing. What that would essentially do is that would be you would essentially have a camera, and that camera would keep clicking photographs, and that photograph goes in, you process that particular image, and then you identify if that grid is properly manufactured or not. Again, a classic AI implementation in a manufacturing world. This is one of the many small, by the way, this is a very, very small example. And, this identifying such defect detection uh, defect detection in manufacturing industries is a very, very manual process today. I had the opportunity to visit a bottling unit of Coca-Cola, and what happens is Coca-Cola bottles essentially get bottled at almost around one single machine can bottle basically somewhere around 800 to 1,000 bottles every minute. And I'm talking about the glass bottles that we all sort of get, right? So 800 to 1,000 bottles every minute is what get bottled, and you again have on the conveyor you have people sitting here and there, who manually try to identify if the level is proper or not, or if the coke or if the drink is properly, if the beverage is properly filled in the bottle or not. Of course, they have a few systems, but these are very simple examples. But these examples can basically go all the way up to detecting defects in an engine, right? If you're familiar with engines and how the way engines work, detecting defects on engines is another issue, because if there's a crack or some kind of an aberration inside the bore of a particular engine, then your engine is going to go knocking. You at times might hear these sounds, these large sounds that keep coming out of cars or bikes, the booming sounds, and that's called as knocking, and that might happen. So for all these scenarios, we require AI systems to come in, and these AI systems are the ones that are basically going to help automate tasks which are extremely manually challenging. And that's basically that's again one of the many things that AI could achieve. I'm not saying AI is only for automating tasks. No, or AI. One of the things that AI is currently doing is automating manual labor, getting rid of extremely manually challenging tasks, and that's one of the things that AI is doing. Apart from that, AI is also doing tasks that is humanly not possible. Like, for example, the adverse effect detection. It would just be impossible for somebody to manually go through data and then identify what combinations or what patterns causes a certain kind of adverse effect in the case of drugs. They call it concomitant medication or parallel medication. So when there are parallel medications being given, it's manually impossible for somebody. It's possible. It's the job of the doctor to do it. But then when you have patients like how you have patients in India, imagine the kind of complexity that you keep pumping. A lot of unorganized. It's a huge unorganized sector. You don't have a lot of staff. The doctor to patient ratio is very low, and that causes a huge issue. Automation via doing some kind of, or basically the fundamental thing that artificial intelligence is bringing in is building intelligent systems, building systems or aiding human beings in the activities that they do. So as you see, when you talk about automation, right, that in the 1980s, the fact that somebody came up with a washing machine was a wonder, right? What this could do is it could automate washing clothes, right? It could basically automate washing clothes. You had to press a set of buttons, and what that could do is it would basically wash clothes in a certain fashion. Is this AI? Well, in 1980s, probably this was artificial intelligence. But today, in the 21st century, we definitely don't treat this as artificial intelligence. Why? Because we're saying that, hey, where is the intelligence here? There is definitely some automation going on there, but there's no intelligence in there, because it's essentially doing what it has to do, right? I click a button, and then the machine is behaving the way it's supposed to behave. There's no intelligence there. The modern day definition of AI has gone one step before, one step beyond that. What we're saying is that today, the way we define artificial intelligence is much more than just that. We are expecting our systems to automatically understand. So when I put a piece of cloth inside the washing machine, I expect the washing machine to identify that, hey, look, it's a jeans, so let me run it at a hard mode. Hey, look, it is or if I put, let's say, a very thin cloth, I would expect my washing machine to run it in a small and in a soft mode. So that's essentially what artificial intelligence is. I want my system, my machine, to possess a human-like quality, right? So that is what we mean by artificial intelligence today. Artificial intelligence is not just about automation, but automation with a human-like intelligence. So I think to define what is AI is a field of computer science that sort of emphasizes on creation of intelligent machines which can work and react like human beings. I think the fundamental thing is about working and reacting like we can always probably find systems that could probably work like human beings, but can they react like human beings? Can they adapt like human beings? Because today, if I ask you to play a sport, you would play a sport, but then suddenly the moment you start feeling the heat, you'd probably take off your shirt, or you would suddenly realize that, hey, look, it's getting really warm in here, so why don't I turn on the AC? So there's a decision that you've made based on the outcome of a particular of a particular environment. In a specific environment, there was an activity that you performed, and that activity yielded in a specific outcome. And on the basis of that outcome, you have made a choice of what you want to do. Do you want to take off your shirt, or do you want to keep your shirt? Do you want to switch on the AC or not switch on the AC? So working and reacting like human beings. So I want to build a system that is powered by computer science, that can act and work like human beings. That is essentially what AI really is. There are a lot of models that are being built for trading. There's a field called as algorithmic trading, and what they do is they build AI systems that can help you. All large companies, all large fund managing companies, right? Portfolio management companies. What they basically do is they have hedge fund companies. What they do is they basically try and find a way to build an algorithm that can predict what fund is likely to go up, what stock is going to go up, what stock is going to go down, and on the basis of that, you then find a way to come up with. On the basis of that, you then find a way to identify what stocks should I invest in so that my complete fund performs well. So there's a lot of work that's going on in the financial industry based on with the help of AI. You see, AI in surgeries is something that's like a dream. People want to get there, but I think the fundamental question is: are you ready to get operated by an AI bot? Are you ready to get operated by a robot? I think the larger question is that: are you okay to get operated by a bot without a human being around? I think you should basically ask yourself those questions. See, laser for eyes, even when you do lasers, when you do the laser treatment for eyes, that's not fully automated. There's still somebody who's running the machine. So it's not completely automated. There's somebody who's still dictating what needs to be done. What we're talking when you say AI for surgery, what you're basically saying is that you go sit in front of a machine, and the machine says that, hey, look, your heart's not beating well. Let me replace your heart. Not, of course, not as extreme as that, but let's say your heart's not beating well, your heart's skipping a beat, and then you see that your ECG is all over the place. So then you basically go and try and perform some kind of a bypass surgery. So yeah, there was this wonderful chess player by the name. If you have some time, go read about him. Gary Kasparov. He once got beaten by an AI system called IBM Watson. He's a grandmaster in chess. This man, Gary Kasparov, he got beaten by he was beaten by IBM's Deep Blue. I'm sorry, not Watson. IBM's Deep Blue. Thank you for correcting. And he was so disappointed. He actually went ahead and gave a talk about it, and he's written a couple of books around it. And this man, he is so good. He asked uh, he asked a very interesting question. He said that, hey, look, you've been beaten. I've been beaten by an AI system. So, and a lot of people come back and ask me, is AI going to take away my job? right? Are we going to lose jobs because of AI? I think the answer that to that particular question lies in, are you okay to send your, let's say, 9 or 10-year-old kid, right? Or whatever, how many ever year old kid to school in a driverless car? Are you okay to say, which is 99.9% accurate or 99% accurate, let's say? Are you okay to send your kid to school in a driverless car, which is 99.9% accurate? Right? I mean, that's food for thought. Are you okay to do that? As human beings, we probably are not. We'll probably get there. We still have time to getting there. I think what we need to learn is we need to learn to live with technology. We need to basically start accepting AI in our daily lives. So I think we should not start talking about AI as if the world is going to change like tomorrow. It's a gradual process. Things will evolve slowly. As somebody pointed out, yeah, Tesla is in the forefront of its tech. Yeah, absolutely, yes. I mean, Tesla is up there trying to embed AI into everything possible. But you have to understand that things are not going to change in a day. Things will evolve as we go along. And that's the most important thing for all of us to understand. So AI systems will get better and better by the day. You'll build very, very complex systems. Yeah, there'll be one fine day where whatever we saw in the movie, what was the Christopher Nolan's movie? Okay, what was the Christopher Nolan's movie? Very recent movie, very about gravity. Not Tenet, and the other the one about gravity. Okay, anyways, they were basically bots. Interstellar, yeah, correct, yeah, thanks. Interstellar. In Interstellar, you had basically AI bots that were basically traveling along with the astronauts, Tars and Mars and Cams and whatnot. So you had those AI bots. They're very much like human beings. They very much talk like human beings. It's just that they are not human beings. So fundamentally, the question is, we want systems that can work and act and talk like human beings. So we want to extract that kind of intelligence, and AI is a field that basically helps us build such kind of systems, right? Yeah, I think. But the question is, for us to kind of for us to kind of build artificial intelligence systems, we first need to understand what is intelligence, right? We want a system that acts like a human being, that is as intelligent as a human being, that kind of reacts like a human being. But the question is, what is intelligence? How do you define intelligence? The definition of intelligence, a human intelligence, is a combination of these five components that you see on the screen right now. Starting from reasoning to linguistic intelligence. So linguistic intelligence is understanding the ability to understand language. So when I speak something, you're able to comprehend language, and you're able to translate that into a thought and then reply back using a language. That's linguistic intelligence. It's so important as a human being that you possess this, because if you do not have the ability to comprehend any form of language, then it becomes really difficult to communicate. And I think that's one of the fundamental intelligences that somebody has. Perception is when you touch something, it's hot or cold. Perceiving something as hot or cold, the senses that you have, or when you see something, identifying that this is a male or a female, or the ability to see, the ability to feel, the ability to hear. These are all perceptions. This is the ability to perceive certain activity that goes around you. We've got to be able to embed this kind of a perception ability inside an AI system. If you want an AI bot that works like a human being and acts like a human being, then make sure that the AI bot actually sees like a human being and hears and listens like a, right. Remember, understand the difference between, when we have, see, take for example, on a human being, and this is, let's say, an AI system. A human being sees through eyes. How can an AI system see through? How do you capture something for an AI system? How does an AI system perceive something visually? The visual perception, how does it capture? Using cameras, right? Sensors, cameras, absolutely, right? So the camera, a video cam or a sensor, whatever, the camera is just a perceiving medium. The camera just clicks a photograph, but even your eye just capture a particular visual. but the ability to understand what is inside that particular photograph or one inside that image is not possessed by the eyes, is possessed by the brain. So passing whatever your eyes see, your eyes are just giving you the visual perception, but converting that whatever you've perceived through your eyes to intelligence is what a human brain does. Similarly, in the AI system, your camera definitely captures an image, but extracting intelligence out of that is where the AI algorithm is going to help. That's essentially where concepts like ML and the other things are going to come in. But the point that you have to understand is that just by perceiving, it's not enough. Just by putting a camera doesn't solve the problem. You need to build an algorithm that can perceive what is in that particular image, to understand what is in that particular image. That is really important. So that's essentially the thing that I was talking about over here. Perception is just one part of the problem, but understanding what is in that particular thing is another problem. That's essentially where reasoning comes in, right? That's essentially where reasoning comes into picture. So you should be able to reason what you see, reason uh, what you experience, and that only happens with human intelligence. And right now, what we're trying to do is we're trying to replicate that human intelligence into how a machine would reason or a machine would learn. Same is the case with learning, right? Today we are learning something. Take the example of a kid. The kid goes and puts his hand inside fire. He burns his hand, or he goes and touches something that is extremely hot. He burns his finger. He or she burns their finger. The moment they burn their finger, they realize that, okay, next time I'm not meant to do this, because what this has done is it has resulted in a negative outcome. So you've experienced something, it has resulted in a negative outcome that I have now learned that, hey, look, I've done this twice or thrice. Every time I do this, I've burnt my finger. So moving forward, I'm not supposed to do this. That's learning. Reasoning is trying to understand why that has caused. Asking the question of why is that hot is the reasoning element, which human beings possess very, very innately. It's a very common question that we all have. Like, how do I know this? How do I know that something is hot? You know something is hot because you're seeing that it is red in color, or the fumes coming out, so you're perceiving something weird. Then you're also asking the same question as to why is it hot. It's probably because it's on a flame, right? So telling yourself that, okay, that's a flame, the flame can heat things up, and when something gets heated up, it is hot, and when you put your finger on it, it burns. This is the reasoning cycle that a human being possesses, and it comes very naturally to us. And embedding that kind of intelligence into a system, into an AI system, is non-trivial. It is not very easy. And the AI world has essentially set off on that path, trying to teach human intelligence to machines. It's not easy, but it's not impossible. I mean, the fact that we are learning this means that it's not impossible. So these 5 intelligences that you see here: linguistic intelligence, problem-solving abilities, perceiving intelligence, learning intelligence, and reasoning intelligence. These 5 components contribute towards the kind of brilliant intelligence or unparalleled intelligence that a human being possesses today. We're trying to replicate that. Basically, we're trying to be God. We're trying to replicate that in another machine using something that we've built. It'll be brilliant if we can achieve it, but that's the idea. Another thing that we also have to understand is that I don't know if any of you all have, because somebody just spoke about Tesla a while ago. If you have seen the the stock price of Tesla over the last couple of years, it has skyrocketed over the last few years. It has just become insanely expensive or insanely sought after, the stock price of Tesla. And the reason for that is because of the kind of AI tech that they are at the forefront of. What they're doing is they're building driverless cars, they're building Hyperloop, they're building whatnot, they're building everything that one can possibly think of. And Elon Musk is pegging to become one of the richest men in the world. Of course, he's not there yet, but pegging to become one of them for sure. Uh, what you see on your screen right now is the amount of investments that have been going into the field of AI. year after year, what we're seeing is we're almost seeing a 50% growth rate increase, 50% increase in the investments on the AI front. So you know that there's a lot of people are looking forward to AI systems because it would cut down on a lot of expense for a lot of companies. B provide that kind of cutting edge, leading edge technology to companies that could be a key differentiator in their products. And also, of course, that's the natural evolution of a human being, right? So we as human beings, what we're saying, this is digital era, so we're trying to create something really cool. So there's a lot of investments that are flowing into this into this area. So yeah, brace yourself for impact. Cool. A lot of people actually think that artificial intelligence, machine learning, and deep learning are all the same. Yeah, let me actually tell you some real facts about it. I think we should start here. AI is like the mothership, right? AI is like the larger, what do you say? AI is like the larger pie, artificial intelligence. And one of the key components under AI, as you can see here, one of the key components under AI is called as ML, machine learning, right? What does machine learning do? So what machine learning basically does is machine learning is an approach to achieving artificial intelligence. It's a subfield of AI that aims to teach computers the ability to do tasks without explicit programming. So you remember I spoke about achieving these intelligences, right? The way you could achieve that intelligence is via finding a way to tell computers to learn certain things without explicitly programming it. Like, for example, you can tell a washing machine to wash clothes in a certain way. You can always write code or program it to do certain things in a certain way. You say, okay, wash clothes first and then rinse them, then spin them, and then dry them. That's the sequence. You can always program something to work in a certain fashion. But that's not what you want. What you want is a human like intelligence. So the field that is going to give you that human like intelligence, or the ability to automatically learn about certain tasks, is what machine learning is all about. So the intelligence is being powered.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective as it is taught by IIT professors and industry experts.
By ML. So ML is the subfield of AI that gives AI the intelligence that is required. One subfield of machine learning is what is called as deep learning. A lot of people kind of a lot of people kind of assume that, hey, look, I'm working on, I want to learn deep learning. You can never start learning deep learning from day zero. I mean, you have to understand the larger context of things. You have to understand how ML works, and that's when you can actually appreciate how deep learning works. You just cannot start from deep learning, because deep learning is just one application of machine learning, but really strong application. It is one of the best set of techniques that we have today. The thing about deep learning is deep learning uh, tries to, while machine learning is a set of computer algorithms, deep learning is an attempt by the computer science world uh, to build algorithms that actually work like human brain. They replicate a human brain. That means the networks that you have. So all of you all must have heard of a core component of our brain called as the neuron, right? This is called as a neuron, right? So, and every neuron has the neuron is basically the most atomic part of our brain. The neuron basically captures pulses and stuff like that. So what your brain is basically a combination of all these neurons. So you have another neuron, and this neuron basically connects to this particular neuron, and there's another neuron that is connected over here. So think of a combination of neurons that are basically trying to capture a lot of information inside them, and store a lot of information inside them. We'll learn more about neurons as we go along, but basically, deep learning is an attempt to replicate how a human brain works. Exactly trying to replicate like how a human brain works. That's the reason the deep learning actually shares a lot of commonality with neurology, neurosciences, and whatnot. So you would also see a lot of neurophysicians and neurosurgeons actually talking about a lot of artificial intelligence. You would see that, hey, look, you'd basically see that side of the world also trying to talk a lot about AI, not just the computer science world. Uh, but well, then what is data science? This is AI, this is ML, and this is deep learning. What we're saying is deep learning is basically a sub part of ML, and ML is a sub part of AI. Then what is data science? Applies all these three techniques, right? Who applies all these three techniques, not just any one of these, and also a few others, right? This is what basically data scientist is. A data scientist is somebody who just doesn't do one of these, who basically does all of these, and in addition, he or she also probably works on a little bit of statistics. So you have stats, statistics, and a couple of other concepts, like for example, data engineering, whatnot. A couple of other elements as well. So that's what a data scientist is all about, right? So that's essentially exactly what is represented in this particular diagram. I hope that answers a lot of questions to a lot of people. I hope you all understand what we mean by deep learning. As a part of this course, what we are going to learn is we're going to try and learn deep learning. But to learn deep learning, we all sort of have to appreciate machine learning. So I'm assuming that you all have, in some form or the other, worked on some bits and pieces of machine learning before. If you haven't, it's okay. We're going to talk about what machine learning is and basics of machine learning in the next couple of slides, the next couple of minutes. But I think fundamentally what we are saying is that deep learning is an application of machine learning. So what is ML, right? As I said, machine learning is basically that particular field of artificial intelligence that has the ability to learn from whatever has happened in the past. Machine learning kind of gives you ways and means to learn from something, learn from data around about whatever has happened in the past. You basically look at that and you learn from it. And machine learning is a set of algorithms that helps you do that. Okay. So if you see this here, an approach, as you see here, it's the ability to do tasks with data without explicit programming. It teaches computers the ability to do tasks without explicit programming. So what we are saying is that we're first trying to extract some kind of intelligence from whatever has happened in the past. Like for example, your Amazon product recommendation, not just Amazon, any product, any e-commerce website you visit. What you would bump into is that uh, when you start selecting a set of products, automatically Amazon starts giving you those recommendations that are really cool, right? Based on whatever you have browsed, Amazon starts giving those in. Let me quickly show you. I don't want you to keep peeping into my shopping history, but then yeah, this is, let's say, my so yeah, basically I have a puppy at home. I bought a couple of puppy products, and then you look at all the suggestions that I'm getting for my puppy over here, the bowls and whatnot, calcium and toys and all of that. So right now, all my purchases, all my suggestions are right now flooded with all puppy products. Or even, for example, the kind of recommendations that you see here, similar to whatever I would probably purchase based on my purchase history right now, what kind of food that I want to buy and whatnot. The point being, based on the products that you select, based on the products that you've been shopping, Amazon keeps recommending products on the basis of that, and that recommendation is basically powered by machine learning, right? So that is basically powered by machine learning in the background. So what the machine is doing, the machine is basically starting to learn from whatever has happened in the past and try and apply that in the present. Um, it is it is a specific application of AI, but is it a complete AI system? Well, no. It's a specific application of AI. It's a specific application of artificial intelligence. But is it a complete AI? Is it like a human being? Is it like acting like a human being? Well, probably not. So Alexa, on the other hand, is another example, right? So you ask Alexa a question, and based on that particular question, Alexa responds back. So based on the query that you ask, Alexa goes back and looks at its huge corpus of of answers that it has, and then it comes up with the most relevant response, and then it responds back to you. That's another application of artificial intelligence. Is it a complete AI system? Well, maybe not, but it's one of the applications of AI again. Movie recommendations on Netflix, right? Same thing again, right? So based on what you watch, based on whatever. See, here you go. Because you watched Orange is the New Black. Looks like somebody watched Orange is the New Black, and then he or she is being recommended to watch House of Cards and whatnot, a couple of others. And also because you have watched so and so particular show, you think Netflix thinks that you should probably watch these shows. This is another cool example of how Netflix recommendation systems work. Yeah, traffic prediction, predicting how long is it going to take you from reaching from point A to point B. Predicting your ETA. Not just this, when you make an order from any of your food vending apps, food delivery apps, like for example your Zomato, DoorDash, Swiggy, whatnot, Uber Eats. The moment you place an order, what happens at the background is you have a quick. They immediately come up with an estimated time of arrival of your food, saying 30 minutes, 32 minutes, 28 minutes, and whatnot. Remember that it is, the determining how long it is going to take to deliver that particular food in your doorstep is driven by a lot of factors. It is driven by the kind of food that you ordered. It is driven by the traffic. It is driven by the driver. It is based on the kind of vehicle the person is coming in. It is based on the weather, whatnot. It is based on so many different elements. Basis all of those elements, they combine with all those factors, and then they come up with one particular number, saying that hey, your food is going to arrive in 32 minutes or 33 minutes, whatnot. If you actually start thinking about how that happens, if you start thinking about, hey, how does that actually happen? That's essentially where machine learning plays a real pivotal role. Machine learning plays a real fundamental role in all of that. Let's try to understand how it works. Let's first live through a small example of ML. Let me give you the intuitive understanding about how under the hood ML works, and then maybe we can try and apply that particular example and to all the learnings that we're going to go through in the next few minutes. So let's take, for example, the food delivery system, a food delivery business. Like for example, take Uber Eats, right? An international brand, Uber Eats. So let's say they've launched very recently in your city, and what they want to do is they're basically delivering food from the nearby restaurants, and then on the basis of that, you get to basically, as an end user, you get to order whatever food you want from the nearby restaurants just by clicking a couple of buttons on your phone. One of the cool features of the food delivery business is that they give you, whenever you select on their mobile app, once you place an order, they give you an estimated time of arrival. They say that, hey, look, your food is going to arrive in the next 32 minutes. The question is, how do they come up with this number? And if you've observed, this 32 minutes or 35 minutes or whatever number that they come up with is in a lot of cases spot on. In a lot of scenarios, I mean, I would say in almost 95 to 98% of cases, this number is really good. I mean, they're almost spot on. How do they come up with this? Imagine, I mean, if they kind of give this a very large number, if they end up saying that, hey, look, your food is going to come in 50 minutes, or if they say that, hey, your food is going to come in 32 minutes, or if they say that their food is going to come in 20 minutes, if they say that the time is very large, as a user, I might not even place an order because, like, hey, dude, I'm hungry. I can probably wait for half an hour. I cannot wait for like 1 hour for my food to come. And if somebody says that the food is going to come in 20 minutes, at the 20th minute, I want to start pestering these people that, hey, look, I placed an order. My food is not at my doorstep yet. So what is wrong? What is wrong? And I will start pestering the delivery boy and the call center. So I want to make sure that this number is spot on. I want to make sure that this number is perfect. How do I come up with it? So the way this works is Uber Eats or Swiggy or any of these delivery systems, they historically collect a lot of data. So what they do is they go back into the past, order ID, let's say order ID 100. Then they start capturing all kinds of information what was the food that was ordered. They capture information about the distance, start point and end point. What was the distance in kilometers? They capture what was the traffic during that time, right? The what was the traffic like, high, good, bad, whatever. And then they capture the weather information. They capture all of this information, and based on this particular information, they also additionally capture ETA. How much time did it take for the order to get delivered? So order ID 100, the food that was ordered was let's say noodle and some kind of soup was ordered. The distance is let's say 25, or let's say 250 meters, and the traffic is let's say moderate, and the weather is let's say rainy, and the ETA was let's say around 28 minutes. Similarly, now think of it, for different combinations of food and distance and traffic and weather, the ETA would vary. So imagine I would end up capturing let's say uh, information for 10,000 such orders. Now, based on all the 10,000 orders that I have had historically, what I would then do is I would then use these 10,000 orders to then come up with one. Then I'm going to try and capture all the patterns that are there, that are available inside this particular data, and then come up with one kind of a mathematical formula. And I'm going to try and come up with one mathematical formula, and that mathematical formula is something like um, that could look something like this. Like for example, it could be ETA is equal to uh, 10 times food plus 10 times food. When I say 10 times food, that means 10 times the size of the food or the quantity of the food, plus 5 times the distance, 0.5 times the distance, minus plus 3 times, let's say, traffic, minus 1 time the weather, plus let's say 35. Some mathematical equation like this. Don't worry too much about the equation. Don't read too much into the equation right now. What I'm simply saying is that I take all of this data, and then based on all of this data, then I come up with one mathematical equation that would simply define ETA. What I'm saying is that to compute my estimated time of arrival of my food, I would then need to substitute all the values in here. And then when I substitute all the values in here, then I can comfortably compute what the ETA is, right? So what I've simply done is I've basically captured all the patterns of my data, all the patterns of these 10,000 historical orders into a mathematical form. Now, what does this help me do? What this helps me do is in the future, if I know what the food is, if I know what the distance is, if I know what the traffic is, and if I know what the weather is, I can comfortably compute what the ETA is. I don't need any other data. All that I need is just this equation. I can simply substitute all the values in here, and then I can compute my ETA. Right? I know there are a couple of questions in somebody's head saying that, hey, if the food is noodles, what is 10 times noodles? Right? So don't worry about that. Basically, what we're going to do is we're going to try and convert all of this into some kind of a numeric representation later on. Similarly, if the traffic is moderate, then how do I, and what is 3 times the traffic? How do I convert this? How does this become a mathematical? Don't worry about it right now. I mean, it's too early in the day for us to worry about all of that. The point that I'm trying to drive here is that right now what we've done is we've converted all of this data into a simple mathematical equation. And this mathematical equation is called as a predictive model. This mathematical equation is called as a predictive model, also called as an ML, machine learning model, because now my machine has learned from whatever has happened in the past and has captured all of that pattern using this simple equation. Now I'm going to use this predictive model, or use this model to try and predict for what is likely to happen in the future. Like for example, if I substitute what the food is and the distance is for any new order, if I know what the food is, distance is, traffic, and weather is, I can compute the ETA, right? Make sense? That is what machine learning is all about, right? Machine learning is the ability to convert historical data into some form of a consumable intelligence. I'm converting historical data into some form of intelligence that can be consumed. What you're currently seeing, this equation, and Naresh, you're absolutely right. This equation is basically called as a linear regression equation. This is not the only way of converting this intelligence. You can also apply a ton of other techniques. There are a ton of other techniques. There are tree-based algorithms. There are different ways of converting this data into intelligence. One such popular way is what you currently see on the screen. It converted into an equation. Is this the only way? The answer is no. There are many ways of doing it. So machine learning model or machine learning is the ability to learn from historical data and apply that learning on your current data or apply that learning on a new instance to predict what is likely to happen. This is one of the brilliant applications of machine learning models or ML, so to say. Superb. Let's talk about another example, a very popular example, and this is basically called as churn. Right? When we say churn, what we mean is take for example a telecom company. Take for example a telecom. The thing that a telecom that thing they want to retain as many customers as. Are you overly sentimental customer or an AT&T customer? Sentimental about it? Are you like, hey, look, I'm a Verizon fan. I just want to use Verizon. Sentimental about it? Like, no, dude. I mean, somebody that you're married to the service provider. So the point that nobody cares. Nobody gives this. Nobody, as long as I'm getting the best service, I'm happy. Some companies have is to make sure everything and anything does. The challenge is that do not to another service provider. I have to start predicting. Why would they want to predict which customers are likely to go up? If I know which offers to them, I can try and I can I will, but we at least can try and attempt. So what do you do is so my problem statement churn. Telecom industry means customers predict customers there and move to another service provider and look at historical data. So I'm going to say location of that particular customer, the bill amount of that customer, the app, all that information around how many calls has usage related information, right? Now, and then I also capture information or not churned. So I then I'm going to capture information like just 25 GB per month. Number of calls, it's let's say 29 calls or 200 after, let's say 28 calls that got dropped. Has a customer churned out? Yes. Similarly, I capture all of this pattern, all of this data historically. Then same process again. I'm going to then convert all of this intelligence, all of this data into some form of. Now, what does ML now has learned all the pattern is likely to happen in the future or to learn from my historical data. So now what customers data in, I can say, hey, look, I have who uses let's say 30 GB per month. After all of that data, I pass it. This customer is not going to churn now. Like that. So that is the response model is basically that has been extracted from the historical data that already existed. That is where ML models really come into picture. In our tomorrow's session or different types. We'll also learn about what reinforcement learn how does recommendation systems work broadly at least. Okay. So yes, the point that I was trying to drive here was that ML is sort of everywhere, but then to kind of talk about what ML really means, machine learning is a subset of artificial intelligence, which gives machine the ability to learn from data without explicitly being programmed, right? The most important point about machine learning is that we really require the right kind of data. More data means more examples. More examples means more learning. Right? We spoke about this a while earlier as well. We spoke about how ML basically helps artificial intelligence systems or gives artificial intelligence systems the ability to learn from historical data, just like how a human being learns, right? A human being learns more and more from a human being, just like how a human being learns from historical data and then tries to apply that learning in the current state of affairs. Similarly, ML gives artificial intelligence systems the ability to learn from historical data, right? So Preetam, I think the point that I'm trying to drive here is that while AI is like, I want to build an artificial intelligence system that can act like a human being, but one of the most fundamental traits of a human being is the ability to learn, right? So because what we do is as human being, I look at something like that looks like an apple, and if somebody keeps continuously telling me that, hey, this is an apple, automatically what happens is that it kind of reinforces the fact that anything that looks in that particular shape is an apple. It reinforces that in my mind. So what's happening at the background is that we're learning more and more from data. We're looking at more and more examples, and our brain is basically learning. The learning side of things that our human brain has is sort of we're trying to replicate that using machine learning. So for the AI systems to really work and act like a human being, we need the ability to learn, and that ability to learn is being provided by machine learning, which is basically a subset of AI. There are other things in artificial intelligence as well, but one of the many important things is the ability to learn, and that's essentially what machine learning is providing. Does that make sense? Moving on. So the question is, yeah, so I think somebody pointed out about this data, not algorithms, is the key for machine learning success. I'm going to talk about that as we go along, but I think the most important point that we have to understand is that more the amount of examples, the more our learning gets better. What I mean by that is the more amount of data means more amount of learning, more scenarios for me to learn from. So the most important thing with machine learning is that I need large amount of data, or I need good amount of data rather than learning. The learning process is actually going to be quite simple, but I think the most important thing that we're trying to learn from here is that while we can of course try and build very complex systems to learn from data, if the data in itself is bad, then the whole point is lost. So we would want to make sure that our data, the quality of data that we provide, the quality of historical data that we provide to machine learning models is as better as possible, is as good as possible, so that we don't have to really worry about building really complex techniques. That's the whole point of data, not algorithms, is key to machine learning. So for the benefit of everyone, I'm just going to talk a little about how ML and deep learning are sort of different from each other. So in general, one of the most, we all know that we want to build AI systems, right? And we all know what AI system really means, right? AI, artificial intelligence systems, are systems that can act or think and act and react like human beings, right? Any system that can act and think and react like a human being is basically an artificial intelligence system. Our final goal is to build systems that are AI enabled, or basically I want to build artificial intelligence systems. That's the primary goal of this whole of whatever we are learning. But if you remember, we told ourselves that to actually make something intelligent or call something intelligent, we require these five things. We require these five forms of intelligence: reasoning, linguistic intelligence, problem solving, perception, and learning. What we are trying to get out of, while all of these are really important, what we are saying is we're first trying to tackle the learning side of things, first trying to tackle the learning aspect of things. Because if systems have the ability to learn, then that means you are evolving, or the system is evolving. It is ability to learn and act based on whatever we are passing to it, rather than trying to experience everything. What we are saying is, if I can give you some, if I can give you some information about whatever has happened in the past, if I can give you a book, can you learn from that particular book, just so that you don't have to experience the whole thing? Like for example, if I were to tell you that, hey, look, in the year 1947 India got independence, it's written in the book somewhere. Or in the year 2000 and 2007 8 there was a financial recession, it's written in the book somewhere. If I give you that information, you can read through it and you can learn. That's the fundamental trait that a human being has. If, let's say, you did not have that trait, then what would happen? You would have to experience that whole process to really learn what would have happened, or what recession really means. You cannot really learn from a book. You But rather what you would simply have to do is you'll have to experience it to actually learn from it. But that's a very expensive affair. What we are trying to do here is we're trying to learn from historical data. So under AI, one of the most important, under the AI mothership, one of the most important subset is called ML, which gives the ability for AI systems to learn from historical information. So I can basically pass on historical data to my system, and then it will be able to learn from the past. That way pattern extraction happens. That way a lot of intelligence is being embedded. Firstly, it's learning a lot of stuff. It's becoming more and more knowledgeable and intelligent as time goes by. That is the process of ML, right? And under ML, we have one more section, one more type of techniques called as deep learning. Under ML, we have another type of algorithms called as deep learning. What deep learning does is, deep learning is basically another type of ML only. ML is also basically a type of algorithm that will help us learn from historical data. Similarly, deep learning is also a technique that helps us learn from historical data. Then how is ML and deep learning different? The only difference that ML and deep learning has is that traditionally what has happened is a lot of problems was we were able to solve a lot of problems using ML techniques. Like for example, if you had structured data, we have something called as structured data and we have something called as unstructured data. And under the structured data section, what we basically have is data that can be comfortably stored in a tabular format. And under the unstructured data, we have information like images, audio, video, text, and so on and so forth. Other forms of data is basically called as unstructured data. Historically, what we've realized is that techniques that are like structured data techniques or structured data can actually be solved using traditional ML algorithms. But with unstructured data, traditional ML algorithms were not very successful. Hence, people went ahead and they identified another section of techniques called as deep learning, which is basically a more complex form or a more advanced form of technique. So that's how deep learning has become more popular. And deep learning over the years, people have realized that they're more efficient than traditional ML technique. That's the whole point. That's why deep learning is slightly more different from ML. You can call deep learning more powerful, but it's just that deep learning would require more larger volumes of data. And we'll dwell into the details as we go along. But yeah, in short, you're right. So technically, when we talk about machine learning, right, machine learning basically has these three categories of problems called as supervised learning, unsupervised learning, and reinforcement learning. Supervised learning, of course, is the form of learning where you kind of provide data. Along with the data, you also guide the algorithm towards a specific direction. And say that, hey, look, this is an apple, this is an apple, and this is an apple. You're basically saying, think of a structured form of learning, a supervised form of learning. So in this particular case, whenever you have labeled information, such kind of data, or when your analysis is sort of, or when your learning process is sort of directed in a specific fashion, in such cases we call it a supervised learning problem. When, for example, unfortunately, you do not have any pre-labeled information, like for example, you have all of this information like what you see on the screen right now. You have a bunch of fruits, but you have no labels. But the form of learning where you automatically try to gather or bring similar data together is what is referred to as unsupervised learning. Like in a lot of cases, what happens is that you might not have access to labeled information, and when you do not have access to a lot of labeled information, then you might have to employ techniques called like unsupervised learning techniques, which can automatically try and put data in the right bucket. So like for example, all your clustering and all the other techniques are basically examples of unsupervised learning technique. Yeah. So the idea is that you automatically club them and then cluster them into the same set of into the same bucket. That's what is basically called as unsupervised learning. Similarly, on the unsupervised learning side of things, like for example, if you have a bunch of movies and you want to kind of club all those movies together.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
That is also in a lot of ways an unsupervised learning technique. Without really knowing what is what, you can simply cluster all of those movies together based on the characteristics that they have. So that's also an unsupervised learning technique. The more popular or the more advanced form of learning is what is called as reinforcement learning. And reinforcement learning is basically in a lot of ways how a human being actually learns. I mean, the kind of environment that we are set up, that's what is essentially called as a reinforcement learning. So in the case of a reinforcement learning, you might not really have a lot of historical information. You might not have a lot of historical data to learn from, but what you would have is you essentially have an environment. Like for example, in this case, take the example of this particular road. So, and say there is a car, right? The car has no knowledge about this whole environment. The car has no knowledge about this whole environment. And all that it knows is there's a road and I'll have to go through that road. So what happens is that the agent observes, or the car observes, it goes ahead, it decides, okay, let me go ahead, let me walk straight. So it selects an action. The action is, let's say, let me go ahead. So the machine goes, or the car goes ahead, and it crashes into this particular board. The moment it crashes into the board, then the environment is going to come back and say that, hey, look, you made an incorrect decision, so I'm going to deduct 50 points from you. So now what happens is now the system learns that, oh, okay, so when I crash into this particular board, I'm going to lose 50 points. That's not a good outcome. So then what the agent is then going to do is the agent is going to then try another outcome. So the agent will go, instead of crashing, it takes a right. The agent goes ahead, instead of crashing into the system, it takes a right. The moment it takes a right, because it hasn't crashed, it gets a 50 point. It gets plus 50 points. That way you've reinforced the fact to the system that, hey, look, when you don't crash, you're going to get more points. When you crash, you're going to lose points. So you're reinforcing a certain kind of behavior into the system. So to begin with, you might not have a lot of information, but as you keep going along, you've designed your system in such a way, you've designed your environment in such a way that it acts in a certain fashion whenever a certain kind of outcome, whenever a certain kind of action is taken. So yeah, like for example, how you would play a game of chess. Think of how you would play a game of chess. So at the beginning, you might not be a pro at it. So you start playing the game of chess. You make a move, and then you suddenly realize that, oh, look, I've made an incorrect move and I lost my queen. So from the next time, you learn that that's an incorrect move. So you try something else. Then again, you lose another piece of yours, and then you try something else. So there are a bunch of options that you have, and out of those options, you try out different options, and then from there you explore that certain options will lead a positive outcome and certain options will lead into a negative outcome. So if you're optimizing for a positive outcome, you will always try to choose options that will lead you towards a positive outcome. So what you're doing with reinforcement learning is you're essentially designing a particular environment, and then asking your car or asking your player to automatically try and learn from that particular environment. That's the beauty about reinforcement learning. You don't need any historical information, but you're essentially designing a framework through which the machine in itself can explore various things. The process is going to be slow, but surely you will always get to a certain point where your systems start to perform really very well. Classic examples are all gaming system, right? Your Microsoft recently came up with an algorithm that was able to crack Pac-Man. Pac-Man is one of the most silliest games that you and I can ever think of. But imagine how difficult it must have been to actually train an algorithm that can really go through all of that and capture all those grains without losing. And that has happened by training a reinforcement learning system for a couple of days, a couple of months, and after that, it kind of got better at it. So yeah. So I hope that kind of clarifies what supervised, unsupervised, and reinforcement learning is. A key point that you have to understand is with supervised and unsupervised learning, you have historical data, but with reinforcement learning, you might not have historical information. You let the system learn as it goes. Yeah, use case self-driving cars. Yeah, I mean, yeah, their testing frameworks are essentially reinforcement learning algorithms. They get better by the day. Do you think Tesla is not already doing this? Tesla is not doing this on the road for sure. Tesla has done it. Tesla has leveraged the reinforcement learning system at the background. So yeah, I mean, they've used reinforcement learning systems to train, and then after that, once they're fully trained, then they let them out into the actual world. So yeah. So broadly put, these are a bunch of ML algorithms. A lot of folks must have already tried a few of these. You must have learned a few of these already. Like for example, in the supervised learning bucket, you must have come across regression, decision tree algorithms, random forest algorithms, and so on. Similar, I mean, just like another classification algorithms. In the unsupervised learning side of things, you must have come across clustering techniques, association analysis, Markov models, and whatnot. What we are going to learn is we're essentially going to learn similar to your supervised and unsupervised learning techniques. We're also going to learn right now, of course, reinforcement learning. We haven't really learned much on reinforcement learning. That would require another form of learning altogether. We will get there when we have to. But right now, in the focus is essentially going to be just like how you've learned regression techniques and classification techniques. Under the classification and regression techniques, we're also going to learn another form of deep learning technique based on neural networks. We'll learn neural networks and we'll essentially progress from there. Great. Limitations of machine learning. The limitations of machine learning, of course, are that machine learning algorithms require large volumes of data. Yeah, lack of creativity, because machine learning algorithms, of course, will require, they're not really complex algorithms. Yeah, traditional ML algorithms are not very complex algorithms, so they don't have a lot of complex learning approaches. But of course, the idea, of course, is that you would want to enhance these traditional machine learning techniques using complex techniques like deep learning that we're going to learn in the next few hours. Are we going to use Python to implement all these algorithms? Absolutely, yes. We're going to do it. So yeah, introduction to deep learning. So this part of this is essentially where things get a little more interesting and a little more complex. Like for example, if you observe the first line, deep learning is a part of a machine learning methods, but it's just that the way they are trained is, or the way the deep learning algorithms work, are basically the way how humans learn naturally. We learn about what that graph really means. The point is, this particular the images that you see on your screen right now, the network that you see on the screen right now is what is called as a deep neural network. But I think what we need to understand before we understand what deep neural networks are is what is a neural network. Right? We need to learn what a neural network is, and why are neural networks so good, and how are they so better. I mean, how do they actually perform, how do they outperform traditional machine learning models so well in the case of in comparison to traditional ML models. Actually, deep neural networks are actually much better. So we've got to probably understand firstly what is so good about neural networks and why, what really separates them from everything else. The cool thing, of course, is that just like how our human brain thinks, when you look at a particular image, our human brain also tries to extract a lot of features uh, from a particular piece of information that we see, like edges, and combinations of edges and some kind of object models. So whenever you see a particular photograph, we just don't capture the photograph, we just don't capture the face, but our brain, knowingly or unknowingly, actually captures much more than just the face. It actually captures features, it captures edges, it can capture actually multiple characteristics about a person's face. And that's the beauty about deep neural networks. I think the most important thing that we have to understand is that if I just a human brain, that when you look at a particular person from front on, you can recognize the person. But if you've ever observed, we also have the ability to actually recognize a person when we look at the person from side on as well, from the side, from a side angle as well. And that's because we don't remember the face. Our brain just doesn't remember the face. Along with the face, it actually remembers the features of that particular person. And neural networks essentially try to replicate the same. So our techniques, the techniques that we are going to learn, are techniques that are going to be very similar to how a human brain captures its information. So yeah, I mean, why deep learning? I think the other most fundamental point about deep learning is deep learning algorithms actually get better and better by the amount of data. They get smarter by the amount of data, they get better by the amount of data. More data means more learning, and learning and the performance of deep learning models actually increases by the volume of data. And of course, it doesn't mean that deep learning is an easy technique. Absolutely no. There are certain design considerations that we also have to take into account. But once they are trained well, what you will see is that more data means more and more learning, so the algorithms will only get better by time. So yeah, one of the most popular applications of deep learning is your translation, machine translation, and image recognition, object detection, machine translation, machine comprehension, speech to text translation. All these are all deep learning applications. And I think that's just, it's just brilliant the way deep learning has changed the way people have started looking at unstructured data, and how people have started were able to actually extract more and more information out of unstructured data. Okay, so let's talk a little about how deep learning models actually work. Firstly, the concept of a deep learning models, broadly speaking, what happens is that broadly speaking, we have three types of layers. We have something called as an input layer, hidden layer, and an output layer. The input layer is where information or data is going to be passed into. So that's basically the layer where all raw information is being sent into. What happens in the hidden layer is a lot of features about the data is getting captured, and in the output layer what happens is we are going to learn about, if the person is a male or a female, or if there is a dog or a cat given a particular image. Doing some kind of a classification can happen as an output. Like for example, if you look at this image, the input layers is where you pass raw images, just like how you see here. In the hidden layers, what happens is we learn certain key characteristics about that particular image, and from various, as you move from one hidden layer to another hidden layer, the kind of features that we capture are going to be very different. The early layers are going to capture very raw features. The layers, the deeper layers are going to capture more and more complex features. But with the help of these features, what we can then do is we can basically, instead of actually remembering the image in itself, the layers internally will capture more and more complex patterns. So using these layers, what we can do is we can perform some kind of classification algorithms or some kind of regression algorithms and so on. We can apply regression or classification technique. The point that you have to understand is, the more the number of layers, the more complex the algorithm is. The more the number of layers, the more smarter the algorithm becomes. You also have to understand that the reason why we call it a deep neural network is because at times the number of hidden layers can go up to 20 and 30, 50 at times as well. And what that means is, when you have those many number of hidden layers, or those many number of layers in between, the algorithm is going to be super complex, which means that you end up learning a lot more complexity with you end up extracting a lot more information from the data. So because we have more number of layers, we call it deep neural networks. That's where the term deep learning came from. The ability to train deeper and deeper algorithms is what deep learning is all about. Deeper and deeper neural networks is what deep learning is all about. So see, the input layers doesn't always have to just be an image. It can be an image, it can be regular data, it can be regular structured data, it can be text, it can be anything. In this particular example, it is an image because it is easier for us to understand. But in general, it doesn't always have to be an image. It can be anything. One point that you have to understand is, more number of hidden layers means that more amount of time that it takes to train the algorithms. So a deep neural network with around 10 or 15 layers could take us anywhere between, let's say, a few hours to train. So the larger and larger that the networks become, the more complex the learning becomes. So this is like is a 10,000 feet level introduction to what a deep neural network really means. A deep neural network broadly has three main components. One is called as an input layer, the other is called as a hidden layer, and the last is called as an output layer. The input layer and output layers are, think of them as your raw data is going to pass through your input layer, and your output layers is where your predictions are going to come out from. Just like in a regular machine learning algorithm, how your predictions are going to come out, that's essentially where your outputs are going to come from. And your hidden layers are where a lot of processing happens. Hidden layers is basically where a lot of learning takes place. You extract information, you extract knowledge out of the data that has been passed via the input layer. Okay. So that's basically what a hidden layer and then hidden layers are meant to do. We will learn about them in more detail as we go along. DNN means deep neural networks. CNN means convolution neural networks. RNN means recurrent neural networks, and so on and so forth. So these are all different variants of deep learning models specifically tasked to do certain kinds of techniques. Like for example, convolutional neural networks are meant to perform very well on image data. Recurrent neural networks are meant to do very well on text data. Regular DNNs are meant to do very well on structured data. So they are different variants of deep learning models. We will learn about them when we get there. ANN means artificial neural networks. ANN and DNN mean the same. This is exactly what marketing gimmicks mean. These, folks have just confused the heck out of people. Firstly, it is neural networks. They've made it artificial neural networks, and they've made it deep neural networks. And from there, it has become deep learning. And from there, things have become super complex. All of this mean one and the same, right? So don't get worried about the terminologies. ANN, DNN, deep learning, they all mean the same. neural networks, they're all one and the same. So if you look at it, a neural network basically is a computing model. Think of a computing model whose this is essentially how a neuron in our brain works. Think of each hidden node as a neuron in our brain. So if you think of it, our human brain is made up of a lot of neurons, and it's not independent neurons. These neurons are basically entangled with each other. These neurons are sort of tied to each other, right? They all actually work together. There's a network of neurons that is available in our human brain, and the hidden nodes is essentially trying to replicate that network of neurons. Think of each hidden node as a neuron, and these neurons are basically trying to they're basically the hidden nodes, or the hidden layer in the case of a neural network, is basically trying to replicate that kind of a behavior. So let's actually dig into how does a neural network really work. Cool. This is essentially how a neural network looks like, right? So you have a simple neural network basically looks like this. So you have an input layer, and from input layer some kind of information is being passed into the input layer, and this what is happening here is that this information is then passed into the hidden nodes, and some kind of computation happens here, and that information is again passed back onto the output layer, and an output is being generated, right? So what we would want to understand firstly is what is the kind of computation that is happening inside here. And we'll want to learn what is the exact computation that's happening inside the hidden layer, and what is the data that's flowing inside through this particular input layer. We want to learn that. So let's dig into it. As I said, the most fundamental element of our human brain is what is called as a neuron. And a neuron basically consists of these elements. A neuron basically consists of um, you see these I think I'm going to talk about the most important parts, which is of course these dendrites. The dendrites are these branches like things which are kind of protruding out of the neuron. This part is basically what is referred to as all these branches like things, stems like stuff that is sort of protruding outside are what is called as dendrites. And these dendrites are responsible for receiving and sending messages. Right? These dendrites are basically responsible for receiving and sending messages from this neuron to another neuron. Okay. This is your axon. The axon is think of just axon as an impulse carrying part. The axon really has no real importance, at least in the context of our scenario. I mean, it has a lot of importance in the biological sense, but in our case, it doesn't really have a lot of importance. But the axon are also referred to as the synapse. The points that you see here, the root-like things that you see there, that is basically called as a synapse. What that synapse does is that synapse basically goes and ties itself to the dendrites of another neuron. So essentially what happens is you have a neuron here and you have the dendrites. These dendrites are basically receiving information from other from synapses of other neurons. So there could be another neuron over here, and its synapse is basically connected to this dendrite. Similarly, the synapse of this particular neuron is connected to the dendrites of another neuron. So that way, if you think of it, there is a huge network that is basically getting created. And think of a few million neurons and the complex network that your brain would end up your brain would end up creating, right? What we are trying to replicate with the help of our neural networks is that complex structure of our neurons. There is an input and there is an output, and between your inputs and your outputs is a complex network, and that complex network basically takes inputs from everywhere and gives outputs to everywhere else. So if you see, even here, look at the kind of network that it has, look at the kind of dendrites that it has. It can take inputs from so many places and it could give outputs to so many different places.
So what we are trying to replicate with this particular architecture over here is that we're trying to say that, hey, I have a few inputs. I'm going to receive inputs from everywhere, and I'm going to send outputs of that particular neuron. Whatever is going to come in, I'm going to do something inside this, and I'm going to send it out to an output layer. Okay, so now this is the biological neuron. Wonderful. Let's try to overlay this on top of a artificial neuron. What happens to an artificial neuron? The artificial neuron is essentially this. These are basically your dendrites, your input layers. If you see, there are some inputs which are coming into this particular node. Think of this as a neuron. And what happens is there is an input coming in, lot of inputs which are coming in. There's some kind of an aggregation that happens here, some kind of computation that happens here, and there is an output. There is some kind of a function that is applied, and there is an output generated. Okay, there are inputs, there is some aggregation, and there's an output. This whole thing is basically one of this purple, these purple circles that you see here. There are inputs, there is a computation, and there's an output. Does the hidden layer contain ML algorithm for computations? No, the hidden layer doesn't contain a machine learning algorithm. The hidden layer basically contains a small mathematical function, like a summation, something as simple as summing up values. Okay, so let me give you a small insight into what do I exactly mean by a hidden layer. So here we go. In your introduction to one of your first few deep learning models, or let's say your first Perceptron model, we call it as a Perceptron model, but we'll learn more about it. So let's take, for example, a traditional machine learning problem, right? So let's say you're trying to predict sales based on two features, x1 and x2. So you're essentially trying to predict sales. So you're saying sales is equal to some function of x1 comma x2. So if you apply a linear regression model on top of this, how would this look like? This would look like sales is equal to some 10 times x1 plus 5 times x2 plus 3, something like this. All of us are okay with this? Yes, this is linear regression. Simple y is equal to mx plus c. Yeah, nothing really complex. Now carefully look at this. So there will be numerous points over here, 1, 2, 3, 4. Let's say they have 100 data points, and I'm going to pass these 100 data points, and I'm going to learn this equation from that complete thing. Okay, now what we're going to do is I'm going to simply transform this problem into a neural network representation. Take a look. So what I have, x1 and x2, right? I have two inputs, x1 and x2, and what I'm doing here, right? I'm passing x1 and x2 into a particular hidden layer. This is my input layer. This is my hidden layer, and then I'm passing this to another output. Let's say this is my output. So for, in all fairness, because I'm not doing anything here, instead of actually having multiple, I'm simply going to say this is my hidden and output layer. In this case, I don't really have a hidden layer. Let's assume that I don't really have a hidden layer in this particular case. I just have an input layer and an output layer and nothing else. Let's not worry about the hidden layer for now. Hidden layer is basically some more layers in between. So I have x1, x2. Now this is, let's say the value over here is, let's say, some kind of a w1, some kind of a weight w2. So every time I pass a value x1 into it and x2 into it, what I'm saying is that don't just pass the value x1 and x2 as it is, multiply it with w1 and multiply it with w2. Multiply the input value here with x1, multiply the input value here with the value input x2 with w2, and then pass it to my output layer. This is, let's say, my output layer. So what will be the value here, anyone? If, let's say, I have a summation symbol over here, anyone, what will be the value here, anyone? This will be x1 times w1 plus x2 times w2, right? Because I have x1 coming in from here and x2 coming in from here, and this is nothing but my weight or my coefficient. Instead of w1 w2, let's say instead of w1 w2 over here, what would happen? I would have, let's say, 10, and let's say if I have 5, so this whole thing would then basically look like, this whole thing essentially is going to look like 10 times x1 plus 5 times x2, and if I, let's say, have a bias term over here, another bias term, ignore the 3 for the moment. Let's not worry too much about the 3 for now. So now my output, my sales, is equal to 10 times x1 plus 5 times x2, which is exactly the same as my linear regression model. Does that make sense, everyone? So my linear regression, I've essentially converted my linear regression into a neural network type representation. This is not fully a neural network, almost there. We're almost there. We'll get there as we go along. But in a lot of ways, if you think of it, my neural network is not very different from a linear regression problem. This is referred to as a perceptron, or a neural network with no hidden layers is what is simply called as a perceptron. Or a perceptron is also nothing but your linear regression model in a lot of ways. Now, so now the question is, in the case of your linear regression, what were we trying to do? Because at the end of the day, I would want to make a prediction. I would want to predict my sales. But to predict my sales, I need a linear regression equation. So when I require a linear regression equation, so this whole thing is essentially going to look like this. So my historical data would be, let's say I have money spent on ad, right? And number of stores. And my final, let's say, is I want to predict sales. I want to predict the sales of my business as a function of ads and the number of stores. So let's say across various years, year 1, 2, 3, 4, across different years, I've captured, let's say, the money spent on ads, money spent on the amount or the number of stores that I have, and the sales. And now I've come up with this equation. So to come up with an equation that will predict sales, I've applied linear regression, and my sales would look like sales is equal to some W times beta naught times some beta naught, or rather, just for simplicity's sake, some beta 1 times, let's say, ads, money spent on ads, plus beta 2 times number of stores, plus a constant. Let's not worry about the constant too much for now, right? So plus some constant. Let's not worry too much about the constant. For now, let's basically say that this is the equation that you would want to come up with. So when you solve for a linear regression problem, what are we trying to compute? When you apply a linear regression technique, what are we trying to compute? We are trying to compute beta 1 and beta 2, because beta 1 and beta 2, from my historical data, I'm essentially trying to compute my beta 1 and beta 2, because if I compute my beta 1 and beta 2, if I know what my beta 1 and beta 2, I'm going to say sales is equal to 10 times money spent on ads plus 5 times number of stores. So on any given day, if I know the value of ads and the number of stores, I can always compute my sales. Always understood? Sorry, are we all on the same page here? Do we all agree with the fact that we are trying to compute beta 1 and beta 2 with a linear regression problem? Now that we want to compute beta 1 and beta 2, we just go about our technique, right? We apply whatever kind of techniques that are required, and then we come up with the beta 1 and beta 2 approach. Exactly the same way, even in the case of your neural networks, we are trying to achieve the same thing. So I have my inputs.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
This is X1, or rather in this particular case, money spent on ads and number of stores. And here I'm basically performing a summation. This is beta 1 and this is beta 2. I want to compute the right values of beta 1 and beta 2 in such a way that whenever I multiply the value of ads and the number of stores, I get the value of sales. I want to identify what that value of beta 1 and beta 2 should be in such a way that whenever I perform that kind of a computation, I get the right value of sales. Does that make sense, everyone? So these values of beta naught and beta 2, they are called as weights. In the case of linear regression, we call them as coefficients. In the context of perceptrons, we call these as weights. This is basically how one can actually solve a simple linear regression problem with the help of a neural network. But now the question is, how do I actually solve for beta 1 and beta 2? How do I get the right values of beta 1 and beta 2? I need to find out the right values of beta 1 and beta 2 such that my sales are the best. I can actually come up with the right values of sales. Whenever I pass the value of ads and number of stores, I need to find the correct values of at beta 1 and beta 2, such that this summation, whenever I do, which is beta 1 times ads plus beta 2 times number of stores, will always give me the exact sales. So I need to know what that exact value of beta 1 and beta 2 should be. So I need to learn beta 1 and beta 2. How will I learn beta 1 and beta 2? Just like how we've kind of learned beta 1 and beta 2 in the case of linear regression, similarly, we'll have to learn beta 1 and beta 2. So for all you know, the linear regression algorithm that you folks have learned all these years or all these months is in a lot of ways the most simplest implementations of a neural network model. Okay, now let's learn, how does a neural network model actually learn from here? I mean, this is great, this is all wonderful, but how do you actually solve for beta 1 and beta 2 in the context of neural networks? How are you going to actually find the values of beta 1 and beta 2? We'll learn that in the next couple of in probably the next couple of classes. We're going to learn how beta 1 and beta 2 is going to work. Do we use neural networks to identify the values of beta 1 and beta 2? So we are going to use certain techniques within deep learning neural networks to find out beta 1 and beta 2. This is a neural network, Puneet, but it's just that this neural network is not very large. It's a very small, simple neural network. Now, let's go back here. In a lot of, see, if you see, a perceptron is a linear model. Now, in a lot of ways, I can actually, what we can actually do here is, instead of solving for a linear regression problem, I can also solve for a classification problem, same as the one that I mentioned earlier. So let's say I want to predict if somebody is going to churn or not. Churn prediction, which is basically somebody is going to quit or not. And let's say based on the bill amount and I don't know, number of calls, I want to predict if somebody is going to churn out or not in a telecom company based on the amount of bill and the number of calls that they make. And this is basically a 0 or 1 prediction. 0 means the person won't churn, 1 means the person is going to churn. Now, yeah, cool. Okay. So now coming back to the bill amount and the number of calls, let's say I historically capture all possible information. So bill is let's say 200 rupees or dollars, whatever, and the number of calls is let's say 50 calls, and the person hasn't churned. Similarly, somebody's bill amount is let's say 1500, and then the number of calls is let's say 100, and then let's say the person has actually churned, and whatnot, and all of that information basically. Okay, so now what we're going to do is, just like how we've trained a linear regression problem, we can actually train a classification problem. How can you train a classification problem? Same, two input one input layer with two nodes, this one for bill amount, and this one for number of calls. And what's going to happen is these two are then going to come here, and because it's going to come here, remember, this time I want a prediction that is going to be between 0 and 1. If I want this prediction to be between 0 and 1, what do I need to do? And I just cannot do a, this is going to be W1 and W2, just wait. But it just cannot be that, because I want the prediction to be between 0 and 1. What do I need to apply over here? Anyone? I want my prediction to be a probability which is true, not the probability threshold. So Shira, I have to perform something, not scaling, something like scaling. No, not the log transform, not the log transform term. Guys, come on, you all know this. No, you have to apply a simple sigmoid transformation. Sigmoid, exactly. You'll have to perform a sigmoid, 1 by 1 plus e to the power of minus. Logit, exactly, Diksha. You'll have to apply a logit transformation, because at the end of the day, I'm solving a classification problem, not a regression problem. So if I want a classification problem, I want my output to be squashed between 0 and 1. So all that I'm going to do is just to kind of give that out as an output. My output will simply be, instead of just a summation, I'm going to apply a sigmoid transformation over here. So my output will then be 1 by 1 plus e to the power of minus W1 times bill amount plus W2 times number of calls. That's essentially what my output is going to be. So what I've done here is, instead of just adding, in the case of a linear regression, what I just did a summation. But in the case, because I want to solve a classification problem, I just don't do a summation. I actually applied a sigmoid transformation. So I just didn't, if I were to simply do a linear regression, I would have just done stuff inside. But because I want a classification, I've essentially applied a sigmoid transformation over here. So the sigmoid transformation would make my prediction to look like that, or make my outputs to look like that. It'll always give me the values between 0 and 1. And Hina, absolutely right. This is nothing but a logistic regression, right? So this is exactly like a logistic regression if you observe. There is no difference. So a single layer perceptron or a neural network with one single layer is no different from a logistic regression. With a sigmoid transformation is no different from a logistic regression. What is going to make this different and complex is when the hidden layers come in. So when the hidden layers come in, this will look very different. The same sigmoid instead of directly performing sigmoid, what I'm going to do is I'm going to have two layers. I might have something like this. So this is going to be bill amount, and this is going to be number of calls. So I'm going to pass these values into everywhere. So now think about it. So now what's going to happen? This node, the value in this particular node is going to be a linear summation of values that is coming from this node and something that is coming from this particular node. Similarly, for this one, the value that comes from here and here, so on and so forth. So things get a little complicated when you have a hidden layer. But when you don't have a hidden layer, we'll come to hidden layers in more detail later on. But when you don't have a hidden layer, this is as simple as a linear regression or a logistic regression. I hope that makes sense. The reason it's called as a hidden layer is because the hidden layers are not exposed outside. You have an input layer and an output layer. The input layers are exposed outside and the output layer is exposed outside. The hidden layers are basically squashed in between. That's the reason we call it hidden layers, because those layers are not exposed anywhere else and nothing else can impact them. Secondly, I think the more relevant question there would be, why do we need a hidden layer? I mean, if I am able to solve a classification problem and a regression problem just like this, then why do I actually need a hidden layer is the question. What hidden layers basically do is, hidden layers, if you don't have a hidden layer, let me just go back to that PowerPoint. So if you look at this particular image, right? If you did not have the hidden layers actually help in capturing more and more intricate patterns from our data, more complex patterns from our data. If you do not have hidden layers, and if you just had like one layer, then you wouldn't be able to capture more complex patterns like from here, because these patterns are very generic patterns. If you have more hidden layers, that means more complex patterns can be captured. More complex patterns meaning better predictions. So more hidden layers essentially will help us build more complex algorithms or more complex prediction solutions. But for now, at a high level, at a 10,000 feet level, that's basically an answer. Through neural networks, we can do everything. Why don't we use neural networks for everything? Great. Don't we use neural networks for everything? Because we don't know. Neural networks are not very easy to train. Once trained, neural networks are super powerful, but neural networks are not very easy to train. So the manual labor that it takes to train a human neural network is very, very high, because you will have to identify what should be the right size of the network, how many hidden layers should be there, and all of that. That makes neural networks extremely complex to train, extremely difficult to train. So that's one of the reasons why it's not easy. Why we don't use neural networks for everything. Okay, we only use neural networks for complex problems where you can really spend some time and you really want good amount of accuracy. That's where you actually use neural networks. Else there's no point in using neural networks, especially if you're getting good amount of accuracies with traditional algorithms. Then there's no reason for you to go to neural network, because neural networks require a lot of manual labor. Cool. Okay, so going back here again, let's go back here. Let's actually try to learn from a small example, and then we can. So if, for example, let's say you have a small network neuron, and let's say you're getting inputs from two sources, and let's say the weight over here is 0.5 and the weight over here is 1 point is, let's say, 1, and this is x1, this is x2, and let's say you have a for different values of x1 and x2. If you observe for different values of x1 and x2, so for example you have x1 and x2 over here, and then you, let's say you pass x1 and x2 through this particular network, we can quickly compute what will be the output from here. So whatever the output is, you can actually compute the output. Can someone tell what will be the output here for each of these values? And let's say this is a summation, just a simple summation. So the value that is going to come out from here is, let's say, 0.5 times x1 plus 1 time x2. So for the first value, the first one is 7, absolutely right, because it's going to be 0.5 times 10 plus 1 times 2. 0.5 into 10 plus 1 into 2, which is going to be 7. What about the second one? The second one is also going to be 7, because it's going to be 8 times 0.5, which is 4, and 3 plus 1 is 3, so 4 plus 3 is 7. And the last but not the least is going to be 17.5, spot on, perfect. So 2.5 plus 15, which is going to be 17.5, brilliant. So right now, what we've been able to achieve is what is referred to as a forward pass. So knowing the weights, what we've been able to do is we've been able to do a forward pass. That means I've basically passed my values of x1 and x2 through the network, and I got the values as an output. I passed my values of x1 and x2 through the network and I got an output. Great. Now, what would happen if in the case of what would happen if I were actually using the similar network to solve for a regression problem? So imagine, go back to the same example that we had a while earlier. I have two inputs and I have one, let's say, layer over here, and this is a summation. This is, let's say, I'm trying to predict sales. This is y hat prediction, and this is my money spent on ads, and this is, let's say, whatever you call your number of stores that you have. And let's say this is 0.5 and this is 1, very, very similar. So this is money spent on ads, this is number of stores, and this is, let's say, my sales. This is historical data, guys. This is historical data, right? So what I've done is over the years, I've gone back and I've captured what is the sales and what is the money spent on ads and what is the money spent on number of stores. So let's say this is I have spent 10 units on ads, and let's say I have 15 stores, 5 and 8 and 10 and 12. And let's say my sales historically have been 25, 12, and let's say 15, right? From where did we get these values? We all understand how we got this, because this data is historical data. This data we will already have from the past. Oh, from where did we get these? So right now I'm assuming that these are a value. I don't know what those values are, which is exactly the whole problem. I need to find a way to compute these values. I don't know how these values have come from and where these values have come from. Right now I'm assuming that it is 0.5 and 1, right? But in reality, I will have to compute exactly what these values are meant to be. So let's go through one round of forward pass again. Let's actually come up with some predictions, right? So what will be my predictions? So in this particular case, quickly, what will be my predictions over here? So 10 times 0.5, which is 5, plus 15. 15 plus 5 is 10. Sorry, 20 in this particular case. What will be my prediction here? For the second one, anyone? 5 times 0.5 is 2.5. And then plus 8. 8 plus 2.5 is 10.5. What about the third one? 10 times 0.5 is 5, and 12, this is nothing but 17. Brilliant. Now if you observe, this is my actual y, this is my predicted value y. Do you see an error between my actual value and the predicted value? We see an error. So can we compute the error over here? So if I say error y minus y hat, error is nothing but y minus y hat. So this is going to be 5 units. This is going to be 1.5 units. And this is going to be minus 2. Perfect. So this is the actual value. This is the predicted value. And I have my error. So the total error for the 3 data points is how much? The overall error, if let's say, is I can always sum up, or I can square and sum up. Don't just do a direct add, guys. Remember, whenever you're talking about errors, you don't simply add the errors, you do a mean squared error or a root mean squared error. Exactly, you do a mean squared error or you do a root mean squared error, RMSE or MSE. Okay. So you will basically do a square and then you'll basically add them. You can come up with a basic value, whatever your value is, RMSE. Now, the whole point of doing this is that I need to come up with a model. So basically there is an error in my model. So with the values of 0.5 and 1, I came up with a particular set of predictions which result in some amount of error. But right now, I want a model which results in a zero error. I want this to be zero. If I want my results to be zero, or if I want my error to be zero, what do I want? I want to make sure that my predictions are correct. If I want my predictions to be correct, what need to be corrected? What needs to be corrected? If my error, if my exactly my weights have to be corrected, my coefficients have to be corrected, spot on. My W or my beta values have to be corrected. So something has to happen to my 0.5 and something needs to change for 1. Something has to happen here and here. What should happen? Should this increase? Should this decrease? What should go up? What should go down? Something has to go up and something has to go down. Now, you and I can break our heads and we can do a hit and trial approach over here and try out probably 100 different combinations before we can come up with 100 or 1000 different combinations and search for it in the dark to find the best possible values for this whole thing. And for all you know, I might never be able to get to zero error. I might be able to minimize my error, but I might never be able to get to a zero error at all. Does this make sense, everyone? Yeah? Are we all on the same page here? Cool, good, brilliant, very nice. So I want my error to be zero. If I want my error to be zero, I want my predictions to be correct. If I want my predictions to be correct, that means weights have to be adjusted. But if my weights have to be adjusted, how do I adjust my weights? It might take me an eternity to come up with the right kind of weights. That's exactly where we will have to employ slightly more sophisticated techniques to find the best possible values of these weights. Exactly, Mahesh. That's where we are going to leverage techniques called as backpropagation. We will learn about backpropagation and gradient descent. We learn about something called as backpropagation and gradient descent, where we will learn the approach towards correcting these weights. We will find the best possible way to correct these weights. So what will happen is, for all you know, maybe this might go down a little. This might become 0.8. The moment this becomes 0.8, then I am going to run my whole algorithm again. Then I'm again going to get an error. I will see if the error is large or not. If the error is large, then again I'm going to go back and correct. So there will be a back and forth that will happen. But which error has to be, which weight has to be reduced? Should the 0.5 be reduced or should a 0.8 be reduced? Should it actually be reduced or should it be increased? All that will be driven by these techniques called as backpropagation and gradient descent. That way, with the help of gradient descent and with the help of backpropagation, we will know what should be the weights and how much the weights have to be corrected. That way, my learning becomes faster. Rather than just searching for these weights in the dark, rather than trying to find the best weights in the dark, I will find a more efficient way to find these weights. Does that make sense, everyone? Are we okay? Wonderful. Now, the larger question is, okay, this is a very simple network right now. There is no complication here, nothing whatsoever. All that we are doing is we're basically solving for a simple neural network, right? We are essentially solving for beta 1 and beta 2, or rather your Ashok, you're absolutely right. We are solving for beta 1 and beta 2. This is beta 1 and this is beta 2. No, at the end of the day we are going to solve for them. So I just assumed a few values here just to kind of give you a sense of how this whole thing works. But in reality, I will never assume. I don't know what these values are going to be. We've randomly initiated these values. In reality, these values are going to be completely different. Yeah, cool.
I would always want to build a model that could give me a least possible error. That means I would always want a model that can predict the sales perfectly. But for me to predict the sales perfectly or to have a very, very low error, I need to make sure that my predictions are correct. If my predictions have to be correct, one thing that I have to correct is these weights. So the whole process is to learn these weights. The whole idea is to learn these weights. Very, very similar to that of your linear regression problem, right? Even in your linear regression problem, we're learning the coefficients. In what combination of coefficients can I actually get my when I multiply my input features, I'm going to get my output. That's exactly what we're doing here as well. Simplistically speaking, this is a linear regression problem, and this is also a very, very simple perceptron model. But then, of course, more complex neural networks are not going to look this simple. They're going to have much more. They're going to have more complexity involved in them, and we learn what makes neural networks more complex and more sophisticated as we go along. We also told ourselves that in our today's session we're going to learn a little bit more about hidden layers and why hidden layers are really that useful. And we also spoke about how we're going to get introduced slowly to backpropagation and gradient descent in our today's session. Brilliant. So, we all have kind of learned that at the end of the day, a simple network looks something like this. You have two inputs, and these two inputs sort of you can essentially multiply these two inputs. Two inputs in this particular case, it doesn't always have to be two inputs, guys. It can be more than two inputs. It could be 10, 15, 100, how many ever, depends on the number of features you have. We are taking only two inputs for the purpose of this particular example. That's about it. So I have, let's say, x1 and x2. So this is ads, and this is number of stores, and then I'm predicting sales. So technically I'm saying sales is nothing but some function of ads and number of stores. This is essentially what I'm saying. So what I'm simply saying is that somebody can actually predict sales just with the help of ads and the number of stores. So now, when we sort of built our linear regression model, back in the day when you all were learning simple machine learning or straightforward machine learning, you kind of learned that uh, you know a model that basically looks like this: sales is equal to 10 times ads plus 5 times number of stores plus 10. This is basically a simple linear regression model, which is of the form y is equal to beta naught plus beta 1 x1 plus beta 2 x2, where x1, x2, x1 and x2 are your features, beta naught, beta 1, beta 2 are your coefficients, and beta naught is nothing but your intercept. This is what we all have learned back in the day. Similarly, this was called as a linear model. And then we learned something called as a decision tree algorithm. We learned a decision tree algorithm where we said that, hey, look, you know what? This linear regression models can be built using this. Essentially, when you build a linear regression model like this, what you're saying is that if the model basically looks like this, beta naught plus beta 1 times x, then what you're saying is that this is y and this is x. If you have your points like this model is simply trying to basically fit a line. And if this is basically this kind of a model, then in 3 dimensions, you're essentially trying to fit a plane. So this is y, this is x1, this is x2, and this plane that we're basically seeing is nothing but your y is equal to beta naught plus beta 1 times x1 and beta 2 times x2. So these are linear models. They assume that your input features are, or your target variable is linearly dependent on your input features. But when you talk about decision tree algorithms, we suddenly say that, hey, look, okay, decision tree classifiers, the same holds good even for your classification problems as well. Classification problems, like for example, in the case of a logistic regression, all that we are doing is we're basically trying to find a line that can cut through this, that can cut through these two data points and classify the X's from O's. This is logistic regression. But in the case of a decision tree classifier, things are a little different. In the case of a decision tree classifier, what we are saying, or a decision tree regressor as well, what we are essentially saying is that, hey, look, your data points might look like this. We're not going to try and fit one single line. Instead, we're going to draw many lines could that could separate my X's from O's. So you essentially draw one line like this, another line like that, and then by doing so, what you've been able to do is you've been able to successfully separate the X's from O's. You tell me, between your decision tree classifier and your linear regression or logistic regression classifiers, linear regression models or logistic regression classifiers, and your decision tree algorithms, which of these is more complex? Is decision tree more complex or your linear models more complex? Okay, I do see majority of y'all saying a decision tree. There are a few who say that the linear models are more complex. Mayank said that the linear models are more complex. The only point that I'd like to make here is that folks who believe that the linear models are more complex, just understand that your linear models only assume a linear relationship between your input variables and target input features and your target variable. They say that I can simply explain my target variable just with a single line, right? Irrespective of how my data looks like, I can basically separate my data with a single line, is what your linear models will assume. But decision trees, on the other hand, don't simply build a single line. They actually end up building more complex spaces. Though each line is a is linear, at the end of the day, the kind of decision boundaries that your decision trees create are non-linear in nature. When I say non-linear, they're not a single line. They're much more complex. I hope that kind of add some kind of a thought. So think of it, more non-linearity can be captured with the help of a decision tree algorithm than a simple linear or logistic regression algorithm. I hope that that clarity persists in your mind. So as your models become more and more complex, when I say more complex models, what we essentially mean is that your models are able to capture more and more non-linearity within the data. If I want a model to capture, let's say, for example, I have my X's and O's distributed like this in the case of a classification problem, I cannot draw one single line that can separate my X's from O's. I will require a very, very complex boundary to separate my X's from O's. I need something like this. I need something like that to separate my X's from O's. This cannot be achieved by a line. This is a curve. What a decision tree can try and achieve is it can try to approximate that. What a decision tree tries to do is decision tree says, okay, I might not be able to create a line, but what I can do is I can probably try and create many more spaces like these. I'll try and approximate that kind of a space, right? So it'll basically try to create that kind of a space for you. So your decision trees are more complex than your linear regression models or your general linear models. Okay. So when I say more complex, what we are saying is that your decision tree algorithms can capture more non-linearity.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective as it is taught by IIT professors and industry experts.
I hope we're all of the same opinion. Cool. Brilliant. Thank you. Now, once this exists, or this once you establish this kind of a thought process, now let's take this one step ahead. Now you tell me, between a decision tree algorithm and a random forest algorithm, which is more complex? Random forest is more complex. Why? Because random forest is again a combination of many such decision tree algorithms. So thereby your random forest algorithm can capture much more non-linearity than a decision tree algorithm. And between a random forest algorithm and a gradient boosting machine algorithm, your gradient boosting algorithms is more complex because it can capture far more non-linearity. The point being that from one model to another model, from linear regression models to decision tree to random forest to boosting models, the reason why we call certain models are more complex or more accurate is because of the ability to capture more and more non-linearity within the data. When there is more complex, when the data is more is sort of entangled between each other, especially with the classification setup, if you have the positive and negative observations entangled within each other, your complex models can actually capture non-linearity very well. Now, the reason why I've given this background is because whatever we're going to learn right now is to basically try and capture that non-linearity. Right? When you're solving a very complex classification problem, your neural networks with the hidden layers in between help us get that non-linearity. The hidden layers in between help us capture that non-linearity in a much more efficient fashion. Right? So think of this. What we are simply saying is that if I'm able to capture sales as beta naught plus beta 1 times my ads plus beta 2 times my number of stores. This is assuming a simple linear combination. But if, for example, if I don't assume a linear combination, if I don't assume a linear relationship, and if I say that, hey, forget about the linear model, if I want to build a more complex model out of this, one of the ways that you can try and do is, of course, you can use the other random forest models or the other models to build. But what you can also try to do is you can leverage your neural network approach and say, hey, look, instead of just directly assuming a linear combination, this is my sales, this is let's say ads, and this is number of stores. Instead of just assuming this linear combination, I can actually take this one step further. That I can end up building a more complex representation by saying, hey, look, I have my ads and number of stores, but instead of taking a direct linear combination, I'm going to assume, I'm going to first create a certain kind of a combination in between, right? Similarly over here as well, I'm going to create a certain kind of a combination in between, and then use these features that I generate in between as my possible outcome to predict my output. I'm not going to directly use ads and stores, but instead first compute a linear combination of my ads and stores, extract some other forms of relationships, and then use those relationships to predict my output, which is my sales. By adding this additional layer, what I'm doing is I'm adding an additional layer of complexity. I'm adding an additional layer of complexity. So what I'm doing over here is I'm doing some kind of a feature engineering. In between this layer, what is happening in this layer is I'm taking my ads and I'm taking my store. So take a look at this. Take a look at this. Absolutely, Sushira, spot on. You hit the nail on the head. Adding an additional layer is like performing a PCA. Exactly. So what does a PCA do? Your principal component analysis is like your principal component analysis essentially captures a linear combination of your input features. That's very, very similar to what we are doing over here. I'm taking my input features and I'm computing a linear combination over here. Similarly, I'm taking my input features, I'm computing a linear combination over here. Once I get a linear combination of my features, so this is going to be, if let's say this is beta naught, beta 1, beta 2, beta 3, and beta 4. This is going to be, what is the value that is going to come in here? It is going to be beta 1 times ads plus beta 3 times stores. Similarly, in this particular node, I'm going to have values like beta 2 times my ads plus beta 4 times my number of stores. So now, instead of just using directly ads and stores to make a prediction, I have now been able to capture another additional set of features over here. I've been able to capture a linear combination of my features, and then I'm using those linear combination to finally predict my outcome. I'm saying my output is not just directly based on ads and stores by default, but they're actually based on a linear combination of my features. Yeah. So that way, my input features are going to be not just my raw features, but actually engineered features of my raw features, a set of engineered features of my raw features. Does that make sense, folks? I hope that adds some kind of understanding. If I have my raw features, I'm building a model with my raw features, and I'm building a model with engineered features. That means I'm extracting more features out of my raw features. and then using those as a part of my model. Which model do you think will do better? The model with newer features, additional features? That's exactly what we are saying over here. I have a set of raw features, and along with my raw features, let's say I build a simple model. This is just raw features, and then I'm building a model. Here I'm using my raw features, and then I'm enhancing these features, and then building my model. Out of these, which one do you think will be a better model? The second one will have, of course, be a better model, because I'm enhancing my features. I'm not using my features as is. I'm actually doing some kind of a I'm applying some kind of a mathematical function on top of my features, and then using them to generate my predictions. And that's the reason why having this layer in between is really going to help. Does that make sense? Like, for example, if I give you, take this for example. If, let's say, I give you weight of a person, and if I can give you the height of a person, what feature can you engineer out of this? If I give you the weight of a person and height of a person, what feature can you extract out of this? You can generate the BMI of that particular person. And body mass index, exactly. You can essentially generate the body mass index of that particular person. Similarly, if I give you, let's say, the expenditure of a particular person, and if I give you the salary of a particular person, what can you extract out of this? What feature can you generate? You can extract savings of that particular person. The only difference is, right, in the case of savings is a linear combination of salary and expenditure. I can simply do salary minus expenditure and I will get savings. But in the case of BMI is not a straightforward difference of the two. BMI is basically a non-linear combination. So BMI will require me to do something like weight divided by a height or something like that. I'm not exactly sure about the formula, but something like a weight by height or something like that. I'll have to do a non-linear combination. This is linear because I'm just adding or subtracting. Here I'm dividing multiple features. So this is a non-linear combination. Yeah, that's the basic difference. So don't worry about it too much. The point that I'm trying to drive over here is that when you have raw features, you can build a certain kind of a model. But when you have raw features with additional features, the model that you end up building will be far better than your raw features. What you're what you're trying to do over here is that instead of you manually trying to create these features, instead of you trying to manually figure out, okay, I have expenditure and I have salary, so let me create a salary and salary minus expenditure to create a new feature. What you are doing over here is you're taking the help of some mathematical functions, and you're automatically trying to create those features. You're trying to automatically engineer those features. How are you engineering those features? What you're saying is that, okay, let me take ads and let me take the stores, let me add them in a certain fashion. Similarly over here as well, I'm taking ads and I'm taking stores and I'm adding them in a slightly different fashion over here. So this could basically end up generating a different kind of a set of features. This could end up generating a different set of features for me. Does that make sense? Absolutely. So what I'm doing over here is I'm adding my features in a certain way. That way I'm able to generate a different kind of a relationship between my features. All of us are okay till here? All of us understand why the hidden layer is really helping in this case? Are you able to kind of build that intuition? Nice. Okay. Now the thing about now the thing about this is, okay, why should I only have one layer? Can I have more layers? Why should I only do a linear combination? Can I do other types of combinations? I mean, like, who's stopping me to just do a linear combination of my features? Right? I can actually do much more combination of my input features. I can take my features and then I can do some kind of a division. I can probably, instead of just having one layer, I can have multiple layers. And why do I have only two nodes over here? Can I have like 100 nodes over here? Absolutely, yes. I mean, we can do all of that. And that's essentially what is going to make this problem into a deep learning problem. So when somebody says that, hey, look, I don't want to have a single layer, I want to have like 100 layers in between, and then, hey, look, I don't want to simply apply the linear combination, I want to apply more complex functions over here. And then somebody would say, hey, look, I don't want to have like, I just don't want to have two nodes over here. Instead, I want to have like 100 nodes in each of these, and that would That is essentially what would make this problem into a much more complex problem. More complex because you have more hidden layers, and more hidden layers means you're extracting more and more interesting features, and the more and more interesting features that you generate, your predictions are going to be more and more complex. So one layer would have one set of functions, the other layer would have another set of functions. You can also try to do at every node, but then imagine if you have like 10 layers, and if you have in each layer, if you have like 100 nodes, applying one function at every node will be very difficult. So the best thing to do is you apply like one set of functions at every layer, so that you kind of simplify it for yourself a little. We can dig into the details as we go along, but I want you to build this intuition of um, why hidden layers really help enhancing the output of the problem. More features means typically more features means better solutioning that you can do. Okay, cool. So just to kind of summarize, what we are now saying is that, hey, look, instead of building a simple, straightforward neural network like this, um, for simplicity's sake, I'm going to call it x1 and x2 from now on, guys, so that x1 and x2 are nothing but my variables. And just for simplicity's sake, I'm going to call this w1 and w2, which are nothing but my weight, right? These are features, and these are my weights. So the output was until this particular point w1 x1 plus w2 x2. But instead of making it so simple, you can also kind of say, hey, look, I don't want to keep this so simple. So I want to kind of add more layers in between. Something like, let's say somebody decides to, let's say, add one layer with 3 hidden nodes, one hidden layer with 3 nodes, and then one output layer. So in each of these, what's going to happen is I'll have inputs flowing in from here and from here. So this is again still x1, x2, w1, w2. So this is w1 x1 plus w2 x2. Similarly, from here to here and from here to here, this is w3, w4. This is w3 x1 plus w4 x2, and similarly from here to here. And then once you have all of this, everything flows from here to here. So this is going to be 5, 6. So this is going to be W7 and W8. So whatever value is going to be in here, that times W7, so the W8 and this is W9. That times W8 and this times W9. That will be your final output. So suddenly, from here to here, what do you see? Here, how many weights did I have to compute? In this case, how many weights did I have to compute? Just 2. I was just trying to solve for 2 weights. But from here to here, what happened to the number of weights? My number of weights just went up from 2 to 9, just by adding one hidden layer with 3 nodes, right? So with just computing a linear regression problem would take us a good amount of time to solve, because in the case of linear regression, you're just solving for X number of weights, depending upon how many features you have. But here, if your number of inputs are going to increase, and if you have good number of hidden layers, can you see how the number of weights go up exponentially? You actually see how the number of weights just increase exponentially, because more and more hidden layers means more and more combinations. More and more combinations means more and more number of weights. And the number of weights that you will end up having to compute will increase exponentially. That's one of the other reasons why computing or actually solving a linear regression or solving a neural network problem is far more complex than solving for a simple perceptron type of a setup. Solving a simple linear regression sort of a problem. This is actually super simple. When you look at this one, this becomes super complex because the number of weights are much higher, and also because the number of the more the number of weights, the number of computations are actually much higher. Now, so we've been able to establish the fact that hidden layers are going to help the model, because more hidden layers means more complexity. But then when we talk about more hidden layers, one of the things that we said was, we don't know how many hidden layers do we have to capture. We don't know that. Secondly, when we talk about uh, when we don't know how many hidden layers we need to put, and we don't know how many nodes should be there in each hidden layers and all of that, it becomes like super complex. So that's one of the reasons why we would want to make sure that we kind of come up with some kind of a heuristic around how many hidden layers should be there and how many nodes should be there and all of that. Generally there is a heuristic that people have, but then we will come to all of that when we get into when we get into further details. The point that I'm trying to drive here is that right now we've just drawn a network over here that you see on your screen, but we don't know if this network is really going to be good enough or not. So just like how you tune your hyperparameters, you might have to tune how many nodes should be here and how many layers should be added. All of that has to be tuned by us. We have to figure out how many layers and how many nodes we need to keep adding as we go along. That's up to us. It depends from case to case. It depends from model to model. It depends from the data to data. So it's case by case. Uh, there is a heuristic around it. There is a kind of ballpark idea around how people should typically go about designing their architectures, network architectures. But there is nothing written on the stone. There is no mathematical proof to what would work and what would. So we will have to figure it out. There are certain widely used approaches, but then we will learn about those as we go along. Right now, just know that we will need to figure the number of layers out. There is no rule of thumb right now. Just assume that there is no rule of thumb. We will learn about certain heuristics as we go along. Brilliant. Okay, let's come back to this. Now, we I need to first learn about how do I compute W1 and W2. We still haven't learned how to compute W1 and W2 yet. If I know how to compute W1 and W2, I can use the similar approach to compute the multiple weights that we saw in a larger network. If we are able to solve a perceptron model, then we can use a similar approach to solve for a larger problem. So the most common approach towards solving for the weights in a linear regression problem is by using the classic ordinary least squares approach. So if you all remember the ordinary least squares approach that you learned, it's the same exact approach. We can just do a quick refresher around it. I'm just going to spend like a few minutes just doing a quick refresher. That way, it'll make it easy for us to work with. So what we are going to do is quickly. So let's say this is what we have. Let's say I have two inputs. I have x1, I have x2, x1, I have x2, and I have, let's say, my y. And then we have my predicted value y hat. This is nothing but w1 x1 plus w2 x2. So let's say the values are 10, 5, 8, 12, 6, 3. And then let's say w1 value is 1 and w2 value is 2. And let's say this is 25. And let's say this is 30. Let's say this is 15. So quickly, is w1 is 1 and w2 is 2. Assume. The first step is assume or randomly initialize w1 and w2. We have randomly initialized w1 and w2. You can initialize with any values that you want, but then we have to keep continuously changing these values to see what's the best. A typical hit and trial approach will ask us to keep randomly changing these values, but we don't know how to change those values. So one approach that is commonly suggested is that ignore what these values are. Just kind of assume that they are w1 and w2. So if, for example, you were to make a prediction, what would this prediction be? So forget about the fact that this is W1 and W2. Forget the fact that it is 1 and 2. Let's say this is W1 and this is W2. So what would this prediction be over here? So it's going to be 10 times W1 plus 5 times W2. Similarly, this is going to be 8 times W1 plus 12 times W2. And this is going to be 6 times W1 plus 3 times W2. So this is the actual value. This is my predicted value. What would be the error? Error is going to be the actual value minus predicted value. So it's going to be 10 times W1 plus 5 times W2 minus 25. Similarly, in this case, it's going to be 8 times W1 plus 12 times W2 minus 30. In this case, it's going to be 6 times W1 plus 3 times W2 minus 15. Doesn't matter y minus y hat or y hat minus y, it wouldn't really make a difference. Actual minus predicted, predicted minus actual, it wouldn't matter because what we are doing is we're essentially going to, you can do a y minus y hat or y hat minus y, it doesn't matter because what we're going to do is we're going to compute MSE, mean squared error. This is error. So if I were to compute a mean squared error, then I'm going to compute an error square. So the error square is simply going to be the square of all of this. And then I need to sum up all of these values and then divide it by 3 because I have 3 values over here. Mean of the squared error, right? So the mean of the squared error in this case is going to be 10 times W1 plus 5 times W2 minus 25 the whole square plus 12 times W2 minus 30 the whole square plus 6 times W1 plus 3 times W2 minus 15 the whole square, the whole thing divided by 3. That is my mean of the squared error. This part is just the error. This is the square of the error. And then I'm doing the mean squared error of the whole thing, of my complete model. This is my mean squared error. Now, if my model were to be really good, if I were to assume that my model is really good, what should happen? My MSE should be minimum. Hopefully 0, but at least the minimum possible value, as minimum as it can possibly get, right? I want this to be as minimum as it can possibly be. So to compute the minimum, so exactly the numerator has to be 0. 0 is like the best possible case, guys, but I don't know if we can really hit a 0. So that's essentially why I'm saying I want it to be as minimum as possible. Preferably 0, but at least it has to be as minimum as it can possibly get. So I need to find, so my problem now has become find W1 and W2 such that my MSE is minimum. That's my problem. All of us agree on this? This is linear regression, guys. I'm not doing anything different here. This is simple, plain linear regression, right? Ordinary least squares. Now, from here, what do we do? What we do is we say that there are multiple ways of solving it from here, but because we would want to solve it the ordinary least squares approach, what we generally do from here, anyone? What do we do from here? Because I want it to be minimum. What is the best approach towards finding my minimum? I differentiate, absolutely. Hit and try is one approach, Kundan. I can try the hit and try approach. My hit and try will take me forever because then I'm basically searching in the dark. I'm not solving, I'm not optimizing. I'm searching for it in the dark. I can try hit and try approach, but it'll just take me forever to solve it. So the best way is to leverage some kind of mathematical approaches over here. What if you actually look at this? If you actually look at this, so I want to kind of establish this intuition in you guys as well, and that's one of the reasons why I'm doing this. So if you observe this one, this complete equation with W1 and W2, what is the degree of this equation? Forget about the 3 in the denominator. Just look at the numerator part. What is the degree of this particular equation? When I say degree of the equation, what is the maximum power? Right? What is the maximum index that we can get to? 2. Yeah. So when you have something of this form, right? Something like y is equal to ax square plus bx plus c. It's very similar to this, right? It's just that you may not have a bx term over here, but you could have something like it. But because in this particular case you have w1 and w2, in this case you have both w1 and w2. This particular thing is a polynomial. Will look like a, if for example you had something like this. Let's say you had MSC is equal to, or let's say I simply put y is equal to ax plus b. This is a simple straight line. But if you have y is equal to ax square plus bx plus c, then you basically have a parabola. It looks like this. This is like 8th standard mathematics, 9th standard mathematics case. I'm not reinventing the wheel here. This is how the nature of this particular curve will look like. It'll look like this based on the value of a and b. It'll look like this, or look like this, or look like this. It depends on the value of a and b. The point that I'm trying to drive here is that the value of when an equation looks like this, it your final outcome will basically the curve will more or less look like this particular form. Will look like a parabola. We call this as a parabola. But when you have y is equal to ax1 plus bx2 plus c, so in this case, how would your curve look like? Anyone? What would this be? It'll be a plane. In this case, it'll look like a plane. Yeah. So this is x1, this is x2, and this is y. This is how the plane would look like. If you don't know about this, it's okay, folks. It's absolutely fine. I think you just need to kind of sing along and just learn that when something looks like this form, when you fit a linear regression equation with multiple features x1 and x2, you're essentially fitting a plane. Yeah, just learn that. Similarly, when you have y is equal to ax1 square plus bx2 square plus cx1 x2 plus d, when something looks like this, if this looks like a parabola, what would this look like? Anyone? What would this look like? This is again same x1, x2, and this is y. Any guesses? If this looks like a parabola, how should this look like in 3 dimensions? Not a circle. Yeah, it look like a bowl. Yeah, you're right. Basically, look like a bowl. Think of it like a bowl. A parabola in 3 dimensions. It's like a bowl. Think of it like a doll. Yeah. So that's how this is going to look like. Okay. The point that I'm trying to drive here is that this equation that you see over here basically looks like this. It's just that instead of x1, x2 is essentially going to be w1, w2, and here it is going to be MSE. That means for different values of w1 and w2, you're going to have different kinds of errors. If you pick this particular value of w1 and this particular value of w2, you'll have a certain amount of error, right? You'll have a certain amount of error. Similarly, if you pick different values of w1 and w2, you're essentially going to get different values of MSE. I want to pick a certain value of w1 and w2. I want to pick a certain value of w1 and w2 in such a way that I get the lowest possible error. I want to pick a certain value of w1 and w2 such that I get the lowest possible error. Okay, how do I get that? The simplest of the simplest math tells us that if you were to kind of get the lowest or the minimum most point, the best way to do it is you differentiate this particular equation. Here, this is the part where things can get a little tricky, guys. So if you haven't understood all of this, it's okay. This was just like a background. But what we are saying here is that if you want to find the minimum value of, so I want to find the values of W and W2 such that my MSE is minimum. That's the fundamental point. So how do I get this? The way I'm going to get this is by differentiating my MSE.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective as it is taught by IIT professors and industry experts.
And equating it to 0. Similarly, dou MSE by dou W2 equal to 0. So I'm going to differentiate this equation 2 times with W1 and with W2. We call these as partial derivatives. This is the part of AI which requires you to learn a little bit of math. This is all 10th standard mathematics, guys. We are not learning something which is beyond 10th standard by any means, right? So it's okay if you're struggling here a little. The point is that to get to the minima, to get to the minimum most value of this particular sphere, What I'm saying is that I want to get to the minimum most value of this particular sphere. I want to get to here. I want the values of W1 and W2 where the sphere is at the bottom most. Why the bottom most? Because when it is bottom, that means my MSE is minimum. How do I get there? The best way to get there, according to certain concepts of math, is that the best way to get there is by computing partial derivatives. So you can compute the partial derivatives like how you see here, dou MSE by dou W1 and dou MSE by dou W2, and that way it will give you, if you compute the partial derivative of this equation and partial derivative of this equation with W2, you're going to get two linear equations. You're going to get two linear equations. So two linear equations with W1 and W2, so two equations and two unknowns. Then you can solve for W1 and W2. Two equations, two unknowns. So you will get basically equations that look like this. So you'll get basically something like 8W1 plus 5W2 is equal to 0, and 6W2 minus 5W3 is equal, 6W1 minus 5W2 is equal to 8. You'll get two equations like this. I mean, these are arbitrary equations, of course, that I've currently put. With these two equations, do you think we can solve for W1 and W2? Absolutely. What you can do is you can just add. So you can simply cancel 14 W1 is equal to 8. So W1 is equal to 8 by 14. If W1 is equal to 8 by 14, take W1 and substitute it back in this equation or any one of these equations, you will get the value of W2. So 5W2 is equal to minus 8W1. So W2 is equal to minus 8 by 5W1. And so W2 is equal to minus 8 by 5 multiplied by 8 by 14. So this is my W2 value. So this is W1 and W2 values correspondingly. So with these values of W1 and W2, what we are saying is that work with that values of W1 and W2, this network will give me my best possible model. With the values of W1 and W2 that I kind of was able to extract here, I will be able to build my best possible network or best possible linear model in this particular case. Let me just repeat that once again for the benefit of everyone. There are a few parts that I've skipped, and we'll learn about those in more detail as we go along. But simply put, what we are saying is that I hope all of us have been able to follow until here, right? So there is historical data. This is historical data, right? This is historical data. I already have this data with me. So I'm trying to fit a linear equation, this is my model. I want to find those values of W1 and W2, which will give me my lowest possible value or my best possible model. So if assuming W1 and W2, these are going to be my predictions. So if my model were to be perfect, that means this error that I compute, mean squared error, has to be the lowest. So if my error has to be the lowest, then what I need to do is that I need to make sure that I compute the best possible values of W1 and W2 such that my MSE is minimum most, because they are the only two variables here. There's nothing else over here. Based on the values of W1 and W2, the value of MSE will be determined. So if my W1 and W2 should be in such a way that my MSE is minimum. Generally speaking, this equation basically looks like this curve, right? Because for different values of W1 and W2, as my W1 and W2 values are going to change, my predictions, as my W1 W2 values are going to change, the error is going to change as per this particular paraboloid that you see over here. So but I want to get to the bottommost point. I want to basically get the W1 and W2 values in such a way that my MSE is the minimum. I want to get those W1 and W2 values such that the MSE is the minimum. How can I get there? The best way to get there is by computing partial derivatives. Why am I computing partial derivatives? Because when you compute a partial derivative or your first order derivative, Vishal, both mean the same. When you basically compute your partial derivatives, what you are computing is you're basically computing the slope of the equation. The slope of the equation simply means that, at this particular point, if you see the slope, there is no slope, there is no tilt of that particular equation. If you compute the tangent in this direction and in this direction, in both directions, the slope is almost zero, right? So that's what I'm saying. I'm saying I want to get to a point where my slope is zero. So when you actually when I actually perform the partial derivatives of this particular equation, you're going to get two equations. I don't know if these are the equations. These are random equations that I put. Because these are second degree, when you solve, you're going to get first degree equations. So you get these two equations. You solve for these two equations, you'll get W1 and W2. So what I'm saying is that these W1 and W2 values are the values that are going to give you your least possible error. Least possible error means best possible model. That is the complete science behind whatever we've just done. Okay, this is just assuming W1 and W2, just two weights that we've solved for right now. Are all of us okay until this particular point? So that's a problem that we're going to learn as we go along. We will learn about scenarios like global minima, local minima, saddle points, and all of that. But in general, what we are saying is that because in this particular case, because with just W1 and W2, it is pretty straightforward. It's always going to look like a parabola. But at times you may also have at times you may have multiple minima, right? When you have more number of weights, you may have multiple minima, and that's where a problem gets a little tricky. We'll get there, Siddharth. We'll talk about that as we go along. The problem might not be so simple when we do deep learning. When we do neural networks and actual deep learning, the problem may not be so trivial. The calculations may not be so simple. Right now, we're just assuming two weights and no hidden layers, so it's pretty straightforward. But when you have hidden layers and when you have everything else, things can get a little more trickier. And that's exactly where your issues of local minima might also come in. Do these kind of equations really help us in corporate world? I think my take on it is very different. I mean, I think at the end of the day, you're learning a concept, uh, and data science and ML and AI, the concepts that we're currently learning, they're all a combination of math and techniques and computer science and business. So it's a combination of everything. Um, we haven't discussed something over here that requires us to learn engineering mathematics, right? So we haven't learned something that is completely out of the world. We're just doing 10th standard mathematics. So just to kind of give you an intuition, all that we've discussed right now is just 8th, 9th, 10th standard math, and then we'll try to keep it at this particular level. I mean, the idea is not to go down a research route. The idea is not to make this math heavy and sound overly cool or overly complex. No, that's not the point. The idea is, and on a daily basis, you're not going to do any of this. This is basically just to understand the concept of what is actually happening under the hoods. Under the hood, how is the problem getting solved is basically what I'm trying to explain. uh, we can actually solve these problems even without knowing all of this, but I think because we're investing some time in learning, let's kind of learn it the right way. That's my opinion, Parvesh. But to be honest, I mean, we can also solve all of this even without learning all of this. I mean, I can simply say that, hey, look, you can the way you actually solve for this is by using a specific function in Python or TensorFlow, and then you can get it up and running with it. But I don't know if that will really serve the purpose. I can simply do functions in Python, but that way I don't think I would really be imparting a lot of knowledge. Now think about this. Given this kind of a setup, this kind of a scenario, now that we've learned how to actually solve for a single layer neural network, and now that we've been able to solve for a very very simple problem like what we see on the screen, the next question is, how do we learn when we have multiple hidden layers? When we have multiple hidden layers, the problem is all the more complex, because then you're not simply solving for W1, W2. This equation is just not going to be W1, W2. This equation will be way more complex. If this equation becomes way more complex, this curve is not going to look like a parabola anymore. this will be a way more complex surface, right? Take a sheet of paper, hold it on both sides, and twist the paper in either direction, right? So take a piece of paper or a piece of cloth, and then you twist it from either sides in different directions. The kind of surface that it creates is the kind of is the kind of surface that you're going to have. We call these as hyperplanes, right? This is a simple plane, but imagine somebody is holding this plane from this direction, and somebody is holding in this direction. You're twisting it here in this direction, twisting it in the other direction from either side. Think of the kind of surface it will create. So you'll see a lot of bumps and a lot of crests and a lot of troughs and all of that, and we call those as hyperplanes. So when you have more weight, when you have more weight, and more complex equations get created. More complex equations means that this will not simply be a parabola or a paraboloid anymore. This will be a super complex surface. When this becomes a very, very complex surface, the solution is not going to be so trivial. So there we will have to make a lot of approximations. We will have to make a lot of approximations. So the point that I'm trying to say is that as deep learning as you keep adding more and more layers, the problem you're is going to become more and more difficult to solve. You will require more and more computational power to solve those problems. That is why somebody asked me yesterday, why do we need GPUs to solve deep learning problems? The reason we need GPUs to solve these problems is because when you're solving a 10 layer deep neural network, and in each layer, if you have, let's say, like 50 or 60 hidden layers, sorry, nodes in each layer, imagine the number of weights that you're solving for, and imagine the kind of complexity that is under the hood. It'll be super duper complex. And then when it is super duper complex, when it becomes so difficult, the amount of what do you say, the amount of computational power that is required, your CPUs will not be able to provide that. And that's exactly where GPUs come in. And GPUs will help us solve them in a much more efficient fashion. Yeah, so I mean, you guys can actually go through it and let me know if these are the two equations. You've gone the additional mile to come up with these equations. So yeah, I mean, you can actually solve for these two equations. You'll have a lot of online solvers. Like for example, you'll have a lot of simultaneous equation solvers online. You can just plug in your stuff. So something like this, 400 W1, and then the other one was y. I'm just putting x and y for simplicity. X. Yeah. So the values of x and y are. Man, who cares about all of this? Give me the answer. Yeah. See, there you go. So your W1 is 15 by 8 and your y is 5 by 4. W1 is 15 by 8 and W2 is 5 by 4. So 15 by 8 is how much? 15 by 8 is approximately around 0.9. Sorry, 1.9ish. And then 5 by 4 is 1.25. 1.25. Yeah. So you could use W1 and W2 values. So we've been able to kind of sort of represent the neural network model or the linear regression model using the neural network framework. And then we've also learned how the coefficients of the neural network of the linear regression model essentially translate into the weight of a simple perceptron, a neural network, of course, without a lot of hidden layers. And then we've also learned how to actually go about solving for a simple linear regression problem, like how you would solve like how you would solve a classic single layer perceptron or a single layer neural network. And then we've learned, the process of how to actually solve for a linear regression problem, and then how you could how partial derivatives are really going to help, and eventually we've computed the weights and all of that. We've also learned that adding yeah we've also learned the impact of adding um, newer and additional hidden layers in between. We've also learned that adding additional hidden layers is going to increase the complexity of the model and actually going to help us capture more and more patterns, because we're doing some kind of feature engineering, automated feature engineering by taking linear combination of features, and that way, once we kind of capture the linear combination of those features, we can then build a model which is slightly more complex. And we learned that over here, when we said that adding these two additional nodes is going to basically help us add more complexity to our model. Uh, Building a model with just raw features is uh, is is going to be lesser accurate than a model which is enhanced with additional features in this particular case. Uh, so this is where we are. We still haven't really dwelled into the depths of neural networks, but we're getting there. I think we're slowly building up to it. We will get there. Now, I hope we're all okay until this particular point. I hope the learning is. I hope we're all sort of fine until this particular point, and we sort of understand where we're headed towards. Brilliant. So back again. Now, let's just go back here, and then let's just start looking at how the hidden layers are going to help us enhance the model. Until this particular point, we haven't really added any hidden layers, but then we'll start slowly learning about how hidden layers are going to help us start solving problems. So, but before we get there, I'm just going to add one more additional challenge to you guys. If you're solving for a classification problem, let's say you have x1, x2, same, but instead you have, let's say, your y, but this time your y is, let's say, a 0 or 1, right? You don't have a numeric outcome, but instead you have a 0 or 1. uh, your simple model will look still like this. Simple perceptron would still look like this. You have x1, x2, and then you have y, but this y in this particular case is not going to be straight a linear combination. It's not going to be a simple linear combination. It's not just simply going to be W1, W2. It's not simply not going to be W1 X1 plus W2 X2, because if it is W1 X1 W2 X2, you're then simply going to get, you're simply solving a linear regression problem. But if you want to convert this into a probability, if you want this to kind of your predicted value, if you want it to be either 0 and 1, one of the things that you will then need to do is, if you wanted to sort of return a probabilistic outcome, one of the things that you need to do is you got to apply you basically need to apply a sigmoid transformation over here. Hence your outcome will, instead of just being y, you'll have to apply something like this. It's going to be 1 by 1 plus e to the power of minus uh, with a sigmoid transformation, w1 x1 plus w2 x2. Yeah, nothing very different. It's just that except for the direct outcome over here, it's going to be w1 x1 plus w2 x2. Similarly, these things are going to change. Here you're not going to compute MSE. Here you're not going to compute MSE, because if it is a linear regression problem, you can compute MSE. But if it is a classification problem, if it is a binary class classification problem, Mayank, you're absolutely right. If it is a two class or a binary class classification problem, then you're not going to compute MSE. What is the error that you're going to compute? What is the error that you're going to compute here? You're not going to minimize MSE, because mean squared error works really well if it is if it is a linear regression problem. If it is a classification problem, and if you're trying to validate the outputs, if you're trying to compute the errors that have occurred, you would then be doing it via confusion matrix is at a much later point, Kundan. But to actually build a model and optimize for W1 and W2, we compute something called as log likelihood. Or you will also come across something log likelihood or maximum likelihood, right? You might also come across something called as log loss. These are different terminologies for the same thing, but essentially what we are trying to optimize for over here is that we are trying to optimize uh, for basically a binary loss. We're not trying to optimize for a numeric loss, but rather a binary loss. Okay, everything will be the same. It's just that instead of doing an MSE, we would be using another function called maximum likelihood or log loss. That's the point that I wanted to drive. Okay, cool. Back again here. So now, so we have a simple x1, x2, two inputs, and instead of a direct output, let's say you have a hidden layer. You have a hidden layer, and these hidden layers are basically like this. Um, the best way to, and similarly from here to here, and from here to here, and then these outputs are then going to simply help us get from here to there. Okay. Um, Now, this is your the most obvious way of sort of representing this is from a naming convention standpoint. Well, different people represent these names differently. uh, from a naming convention standpoint, people call this W11 because it goes from the first node of this layer to the first node of this layer, and this is called as W12 because it goes from the first node of this layer to the second node of this particular layer. This is going to be W21 and W22. Yeah, and then you could basically call this W3 and W4. That's a decent naming convention, so to say. um, Now, as I said, the value of h1, and I'm going to call this h2, and this is your final output layer. This is, let's say, y, right? So anyone, what is going to be the value at h1? W11 times x1 plus, because W11 times x1, this is from here to here and this as well. So these are two inputs that are coming in. Similarly, W21 times x2. Similarly, for h2, the value is going to be W21 times x1 plus W22 times x2. And your value at y, your output is going to be, what is going to be the value at y? W3 times h1 plus W4 times h2. Remember one point, that until this particular point, we haven't added any kind of a bias term. We haven't added any kind of an intercept term. Remember intercept? When we talk about linear regression, we say y is equal to mx plus c. We haven't added any of the c terms yet. We will add that as we go along. Let's not worry about that right now. But just remember that you will have one more term everywhere. So instead here, you're essentially going to have C1, C2 plus C3. Essentially, you're going to have one more constant terms all throughout. Yeah, so let's, for now, for simplicity purposes, I'm not really taking them into considerations. Okay, for the purposes of the simplicity sakes. So this is what your values at H1, H2, and Y are typically going to look like. Okay, the way you could, H2 is going to be, I'm really sorry, guys. Thank you. Thank you. Who can it? Parvesh, thanks so much, man. Yeah, this is 2-1. Sorry, W12. W12. Perfect. So the way this is also represented, right? You could also basically represent the value of h1 and h2 with, in some form of a matrix representation as well. And we will learn that as we go along. So people also represent it with w dot x, summation sigma w into x, where w and x are two vectors, right? W1 x1 is what they also refer to this as. Uh, Essentially, what I'm saying is that this could basically look like this as well. So you could basically have one row, two columns. Sorry, W11, W21, and then you can have X1 and X2. So when you do this, this is basically one row, two columns, and two rows, one column. This would basically return one single value for you. You could represent it using a matrix representation as well. Similarly here as well, W12, W22 times X1, X2, and here this is going to be W3 and W4 times H1, H2, and then you can simply represent it using a numeric representation as well. This is a matrix product, matrix multiplication. Now, assuming that because in this particular case we just have like two weights flowing into H1 and H2, it sort of becomes very easy. But at times what may happen is that because there are multiple weights, you might have multiple weights, and this might actually become much bigger, and this might actually also become much larger as well as we go along. So your weight matrix can also become larger, your X1, X2 also might become larger. Net, the point being that the best way of kind of visualizing these matrices and these computations is by using matrix representations. So you will see that as you go along in a lot of places, in a lot of literature, you will see that instead of just representing the computation using a simple math like this, people prefer representing it using matrix representations. That way, it's sort of easier for people to understand that you have two weights and two x1 x2s, and or rather two inputs and two weights. So the combination is what we see over here. Also, what people generally do is that instead of representing it this way, they also say that the hidden layer values are w11, w21, w12, w22, and multiplied by x1, x2. So when you do this, this is basically a 2 by 2 matrix, and this is a 1 by 2 matrix. Sorry, 2 by 1 matrix. So this would return again h1, h2 values. This would basically return h1, h2 values. You can also represent this whole thing. I mean, this layer computations can simply be represented like that. Okay. Yeah. So that's the other thing that I wanted to sort of represent as well. Cool. I hope we're all clear until this particular point. Now, going back to the computations that we just saw, just a second, just want to clear some space. So to make it more easier for us to understand, at times what people also do, because to kind of make the math a little more, rather the feature generation. So H1, H2, as you observe, are like the intermediate hidden layer values that are basically getting generated. And we all know that the reason why we are doing this is because H1, H2 are basically going to give us additional complexity, are basically helping us add additional layers or basically additional features that are getting created at the background. And that's one of the benefit of having your hidden layers. So instead, what people also do at times is they say that, okay, why should I just do a linear combination? Can I not just apply some kind of a function on top of this? You know, instead of just doing a linear combination, I'll apply some kind of a function on top of this. Right? I'll apply another function on top of this. And instead of just taking the outcome as it is, I'll apply some other function on top of this. Right? So why do I just want to take the values as is? Why do I just want to take a linear combination? Instead of just doing a linear combination, I can actually do much more than just a linear combination. I can actually take a linear combination and apply a function. So if you remember your support vector machines or from your previous learning, one of the things that support vector machines does is that SVM adds certain functions in between that helps us or performs something called as a kernel transformation. Do you remember something called the kernel transformation? A kernel transformation is basically nothing but instead of just using the features the way they are, you transform your features into a higher dimension. You apply a function and you transform your features into a higher dimension. By doing that, what happens is that you gather some kind of an additional non-linearity. You basically get some additional non-linearity into your data, or your model starts to represent more non-linearity. And the way you achieve that is by adding these kind of additional functions. So instead of just taking a linear combination, you take a linear combination. Additional to that, you apply some kind of a function. These functions that we apply.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
These functions that we apply are called as activation functions. Okay? Why do we apply these functions? Again, the reason why we apply these functions is because even if you don't apply those functions, the combinations are still linear. So you will really not get the kind of benefit that you want. So if you really want to capture a lot of non-linearity, that means then you require functions which are more non-linear in nature. So rather than just doing a simple addition and multiplication, if you're able to apply more complex functions, like for example, apply a sine transformation or a tan, a hyperbolic transformation, apply some kind of complex transformation functions on top of your existing data. That way, what you will get is instead of just fitting just basically fitting y is equal to w3 h1 plus w4 h2. You're basically fitting y is equal to some complex function times w3 h1 plus w4 h2. Here it is simply not a linear combination, but because you're applying an additional function, this model, the final layer, could actually be a much more complex representation of your input layer. So that way you're capturing more non-linearity within your data. Does that make sense, everyone? Do we all understand why we are applying an activation function over there? The reason why we apply activation functions is because it will help us capture more non-linearity. Hidden layers already are helping us capture non-linearity, but if you want to capture more amount of non-linearity, larger amount of variability within your features, you apply more functions. If you apply more functions, then your your models are even more complex. Yeah, does that make sense? So just to kind of give you an intuition, if for example, in a simple linear model representation without a hidden layer, let's say forget about a hidden layer. Here, let's say I'm applying an activation function. Let's say the activation function is a sign transformation. Let's say the activation, or rather, forget about a sign transformation. Let's say I'm using, let's say, a square transformation. This is x1, this is x2, this is w1, this is w2, and this is y. If I did not have an activation function here, what would we have? We'll simply have y is equal to w1 x1 plus w2 x2. Simple linear model. But when I put an activation function over here, I'm saying square this thing. Now my function is going to be w1 x1 square plus w2 x2 square plus 2 w1 x1 x2 w1 w2 x1 x2. This. Now if when you compare y is equal to w1 x1 plus w2 x2, when you compare these two, this is the first one and this is the second one, can you tell me which of these two models is more complex? Everyone, the first one? Do we all agree that the first one is more complex than the second one? Correct, exactly, right? So more complex because you're able to capture, this is more non-linear, right? This is just fitting a line. This is basically fitting a curve. So between this and this is much better than this model. This is simply fitting a simple straight line, while this is actually like a curve, like a parabola sort of a thing, because it's second degree. So this will basically look like a parabola, something like this or something like this. So clearly this is a better model than the other one. Yeah, that's the whole point about applying activation functions. So when you apply an activation function, suddenly what happens, data which was previously just getting represented in a straight line, or a model which is just fitting for data in a straight line, now suddenly starts to fit for a more complex dimension, more complex shapes. If you apply an activation function, what may happen is that your your model performance time may go down. That means the computations will become more complex because you'll need to apply more and more functions. So the time that is taken for actually doing the computations is higher, but it'll increase accuracy because you're building a more complex model. Yeah, cool. So, and imagine instead of just applying that activation function at the last layer, by the way, we are already applying an activation function for the last layer in the case of a classification problem. Can you tell me what function are we applying in the last layer? That for a classification problem, we are already applying an activation function. A sigmoid activation. Absolutely right. A sigmoid activation is also another activation function because you're trying to get that non-linearity. Yeah, as simple as that. Because if you just do w1 x1 plus w2 x2, it's a simple straight line. But if you apply the if you apply the transformation, what it does is it basically transforms that into a sigmoid curve. This is a non-linear function. That's the whole point of applying activations. Patterns that you couldn't capture earlier with simple linear combination can be captured using activation. Yeah, I mean the choice is ours, right? Sigmoid is one activation function, but then there are a ton of other activation functions that one can apply. The question is, can I apply any activation function? Yeah. So the question is, So can I apply any possible activation function? I mean, can I apply any activation function? Like, for example, can I apply a sign transformation? That means anything that comes out of a node, I'll apply a sign transformation to it. Or anything that comes out, I will just, let's say, apply some kind of a cosine transformation to it, or a tan transformation to it. Can I apply any transformation that I want? Can I apply any activation that I want? Well, while we would want to apply anything that we want, there are certain traits that an activation function should have. There are certain fundamental traits that an activation function should have. And one of the traits that an activation function should have is the fact that they should be differentiable, they should be continuous, and all of that. There are certain mathematical traits that an activation function should have. The reason why it should be differentiable is because we are computing. If you remember, we are computing. We're computing some kind of partial derivatives in between. So we want to make sure that we apply a certain kind of functions which make our computations also easier. You don't want to kind of put all possible load on the computers. You want to apply such kind of functions which make the computations also a little easier. So you can apply any function you want, but it's just that you have to keep certain things in mind. Things like, firstly, whatever function you apply, you have to make sure that the functions are continuous and differentiable at different points. You don't want to apply discontinuous functions. Like, for example, you don't want to apply something like a modulus transform or other kind of transformation. You want to apply functions which have certain specific traits, and one of those is the fact that they have to be differentiable. And there are certain other key elements that we have to take into consideration. People have gone about uh, identifying different kinds of activation functions. For all you know, this is an active area of research, right? As we speak, there is probably some guy sitting on some corner of the world trying to figure out what is, trying to research a new activation function. So you can come up with your own activation function someday and put it against your name. I will be proud to say that you were a part of my class back then. The point being that activation functions are an active area of research. Everybody comes up with newer activation functions, and there's so much that's going on in that space. Uh, but historically and empirically, people have done a lot of research and they've identified a certain set of activation functions which are very, very effective. And let's take a look at what those really are. So, why do we need activation? The same thing again, guys. So why do we need activation functions? Like, for example, if you just had x and y, and if the data looked like this, you cannot really fit a straightforward model. But when you apply a transformation, like, for example, if you do apply the square transformation, suddenly now the data in third dimension is nicely separable. So you can then draw a simple straight line, and then you can separate the red points from the purple points from the blue points. Same thing, right? More complex models. You can actually build more complex models using activation functions. The ones that you see on the left side, these are all the kind of very, very popular activation functions, starting from identity transformation, meaning doing nothing, right? Identity transformation basically means do nothing. F of x equal to x, that means just pass the values the way they are. Then you have binary step activation functions. Then you have sigmoid activation functions, tan h activation functions, ReLU, rectified linear units is what you mean by ReLU. You have something called as leaky ReLU, which means leaky rectified linear units, and then a softmax activation function. Out of these, we kind of know a few already. We have, in some form or the other, got exposed to a few activation functions. A few we will learn as we go along. Now, when you have an activation function, the question is, uh, should you apply the activation function? We'll learn about these activation functions in a second. But the question is, do you apply the activation function for individual nodes, or do we apply the same activation, or do we apply different activation functions for one node and another activation function for another node? Well, you can try to apply different activation functions at different nodes, but imagine if you have a very, very large you can also apply an activation function on the output node. You can apply different activation functions at different places. But when you have larger networks, it becomes really difficult to track down which activation function is applied at what node, and it becomes really difficult to tune your models. So the popular belief and the popular and most deep learning frameworks, they allow you to apply an activation function on the complete layer, not on a single node. So that means if you choose an activation function, the activation function is the same for all nodes of that particular layer. Yeah. So that way, what happens is that it'll be easier for us to track, number one, and number two, it'll make it more. Um, it'll make your model more. The computations are actually also going to be much easier. And you will realize why that is the case when we really learn something called as backpropagation. We learn about a concept called as backprop in a couple of days. Probably by the next session, we're going to start learning backpropagation. There we will learn what is the best way to apply activation functions. But in general, the common approach is that we apply back activation functions across the complete layer, not on a single node. So let's go back. Let's start understanding what each of these activation functions are. The most obvious one is an identity activation function. So identity activation function basically means do nothing. Whatever the value is, just pass the value the way it is. No, applying no function is an identity activation function. Yeah, that's essentially what an identity activation function is. Then the next is a binary step activation function, a step function. So the second one is basically a binary step activation function. So basically, it's a step. It's called as a step function, right? Uh, that means you are always going to return a value between for any value under 0, you will return a value 0. For anything greater than or equal to 0, you will always return 1. So it's like basically a thresholding function, right? This is very popularly done in the case of it's actually done in the case of logistic regression. Before people applied the sigmoid transformation, the binary step activation function is actually was the go-to approach, right? Let me show you what I mean by that. Back in the day, when people were solving classification problems, so we know that y is equal to w1 x1 plus w2, or let's say w1 x1, something like, let's say y is equal to mx plus c was your linear equation. And then what people did was they said that, okay, whatever may be the value, because if you were to solve classification problems like this, for example, you had income and you were predicting if somebody would make a purchase or not, right? um, let's say you were to predict if somebody is going to make a purchase or not based on their income. People with lower income did not make a purchase, people with higher income made a purchase. But if you were to simply fit a linear equation, a straight line would basically go like that. So then this equation would basically be purchase is equal to uh, m into income, some constant value c. But beyond a certain value of income, your purchase will go beyond 1, because if you look at a higher income value, the prediction will basically go much beyond 1. And for a lower income value, the income will actually go much less than 0. The prediction of purchase will become much less than 0, because this will range from minus infinity to infinity, but I would want this to range from 0 to 1. The way people did was they said, okay, doesn't matter if the prediction, if the m times income plus c was greater than a certain value, was greater than a certain value p, then we will always return a 1. If it is less than or equal to certain value, then we'll always return a 0. That way, instead of fitting a straight line, they always used to fit a, something like a thresholding function like that. Yeah. Then later people realized that, hey, look, this is not a great way of going about it. That's when the sigmoid function came in. Yeah, the P is something that we will have to experimentally identify, right? You will set different values of P and identify the accuracy. You'll set one value of P, see what the accuracy is, set another value of P, identify what the accuracy is. So P is something that you will have to empirically identify. Yeah. But the point that I'm trying to drive here is that originally people used to do things like that. But then later on, people realized that, hey, look, this is not a great way. And that's when they came up with a sigmoid function. The other point is whatever we are seeing over here, the binary step function is also very, very similar, right? It will always return a certain value beyond zero. In this case, it is zero. If it is less than zero, it will always return a zero. If it is greater than or equal to zero, it will always return a one. So if, for example, in a hidden layer, if, for example, you've applied a binary step function, for whatever may be the reason, if you've applied a binary step function on a hidden layer, if the h1 value that you've computed, if this value that you've computed is, let's say, a positive value, the binary step function would basically return a one. If it is less than zero, then it would return a zero. That's essentially what this function is basically going to do. Does that make sense? So just to kind of take one small example, let's do a quick example and then we can move on to the next one. Small example on this. So let's say we have a hidden layer, W11, W12, W21, W22, W3, and W4, X1, X2. This is H1, H2, and this is, let's say, Y. So if X1 is equal to 10 and X2 is equal to 5, and if W11 is equal to -1, W22 is equal to 2, W12 is equal to 3, and W21 is, let's say, is equal to -3, then compute the value at H1. If compute the value at H1, also compute the value of H1 with identity activation, and compute the value at H1 with binary step activation. Can we quickly do this? So the binary step activation, by default, the threshold is 0. So just to give you an idea, this is how the binary step activation looks like. This is the binary step activation. If anything it is less than 0, it is 0. Anything greater than or equal to 0, it will return 1. Cool. So quickly, what is H1, guys? So H1, the formula for H1 in this particular case is going to be W11 times X1 plus W11 times X1 plus W21 times X2. So W11 in this case is -1. -1 times X1 is 10, and W21 is -3. So -3 times X2 is 5. So this is basically -10 minus 15, which is -25. So H1 with identity activation is -25, and with H1 with binary step activation, H1 with a binary step activation is going to be, remember, going back to the binary step activation, if the value is 0, less than 0, it will return a 0. If it is greater than or equal to 0, it will return a 1. So in this case, it will return a 0 because it is less than 0. So basically, the point is the output from this particular node is not going to be -25 with a binary step activation. This will basically return a 0 from here. So if you see, I'm computing H1, W11 into X1 plus W21 into X2, W11 into X1 plus W21 into X2. So look at what are the inputs to H1. Inputs to H1 are W11 and W21. So then what you're going to do is W11 into X1 plus W21 into X2. This is pretty straightforward. There is no complexity here. So you simply substitute W11, W21 and X1 values, and then you will get -25. This I'm assuming is pretty straightforward, Krishna. So the value at H1 by default is 25, -25. But then when you apply a binary step activation, because when I said identity activation means applying nothing, right? But if you select a binary step activation, if you've chosen that, hey, look, my layer in between is going to have a binary step activation, then in that case, what's going to happen is, because this is returned minus 25, you will apply the binary step activation on top of this. So you are going to apply the binary step activation function on top of this value, Krishna. So on when you apply the function, so the binary step activation says that if the value is if the value is in this particular case uh, greater than less than 0, it'll return always a 0. If it is greater than or equal to 0, it'll return a 1. So is the value greater than 0 or less than 0 here? The value is less than 0. Because it is less than 0, what will it return? The function will always return a 0. This will always basically return a 0 if you apply a binary step activation function. With the binary step activation, what happens to h2, anyone? Yeah, sure, good stuff. What will happen to h2? Quickly, can somebody compute what is the value at h2? H2 is going to be W12 times x1 plus W22 times x2. So W12 times x1. W12 is minus 3. Sorry, 3 times 10 into 3 plus W22 is 2. So 2 into x2 is 5. So 30 plus 10, this is going to be 40. So h2 is 40, but with binary step activation, it would return 1. Cool, everyone? So let's go back again. So this is one function, one of the many functions that you could apply. Now, the question is, when should I choose binary step activation function? Now, there is no rule of thumb as to which one should be picked when. Now, the decision of which one we should pick is based on the kind of problem that we're going to solve. If, for example, you're solving, um, in general, what people have observed is that while you have the option of picking so many different activation functions, in general, people have seen that for any kind of problem, ReLU or leaky ReLU in general really helps, right? Sigmoid and TANH and the others have a lot of issues. But for hidden layers, you can apply ReLU or leaky ReLU, and they seem to be actually performing really very well. We will learn about ReLU as we go along. But again, these are like different options that you have. You can pick whatever you want, and then you will have to try out seeing which functions work in which layers. There is no rule of thumb of saying, okay, this is the kind of data, so you should apply these activation functions or whatever. Different activation functions work well for different kinds of problems. Just like, for example, if you've learned a lot of machine learning models, right? You've learned linear regression, you've learned random forest, decision tree, bagging, boosting, whatnot. Can you tell me which one should be used for what kind of data? Do you know which one should be used for what kind of data? There's nothing like that. There's no rule of thumb, right? These are different techniques that you learned, and for all kind of classification problems, you try out one or the other and see what works the best. Similarly, even here as well, you have these as options. These are like hyperparameters. You will pick one or the other to see what works the best. In general, what people have seen, right, for most problems, ReLU or leaky ReLU sort of give you the best kind of outputs. You don't have to do a lot. You don't have to sort of think a lot. You can just pick ReLU or leaky ReLU, and then they are sort of the one of the best. We haven't looked at what ReLU is. We'll come to it ReLU in a minute. But we've done binary step activation. This is sigmoid activation. We all know sigmoid activation. We've been applying sigmoid activation in the last layer forever now. I mean, since the day you've learned logistic regression, you've already been using sigmoid functions. So this is nothing new to us. But you can also say that, hey, look, I want to apply a sigmoid activation even somewhere in my hidden layer as well. You can say that, hey, look, I want to apply a sigmoid activation in my hidden layer also. You can also do that. That is fine as well. Yeah. So you can, by default, we've been applying sigmoid activation in the last layer. When you're solving a binary class classification problem, we've been applying a sigmoid activation in the last layer. But you can also apply a sigmoid activation to hidden layers in between. What would a sigmoid activation do? If you apply a sigmoid function, what will it do? It will always return values between. What values will it return values between? Sigmoid will always return outputs between 0 and 1. Absolutely correct. Yeah? Sigmoid always returns values between 0 and 1. Yeah. Binary will always only return a 0 or 1. If the value is less than 0, it will return a 0. If the value is greater than 0, it will return a 1. But with sigmoid, it will return values between 0 and 1. Whatever may be the value, input value, the output will always be between 0 and 1. That's the beauty about the sigmoid activation. You see this? Irrespective of whatever the input value is, the output will always be between 0 and 1. That's basically a sigmoid activation. Then there is something called as a tan H activation. There's something called as a tan H activation function. So the tan H activation function, basically it's called tan H, means tan hyperbolic X. This is a hyperbolic trigonometric function. Hyperbolic functions basically are you know, they're very similar. This tan H activation is actually very similar to that of sigmoid activation. If you actually observe this curve and this curve, they're exactly the same. There you go, exactly the same. The only difference is your sigmoid returns values between 0 and 1. You see, the minimum most value is 0 and the maximum value is 1. While in the case of tan H, the minimum most value is -1 and the maximum value is +1. Yeah. So that's why tan H is a shifted version of a sigmoid function. It's very similar to that of sigmoid function. It's just a shifted version of a sigmoid function. While your tan H activate sigmoid returns values between 0 and 1, tan H returns values between -1 to +1. Yeah. So let me show you what I mean by that. So let's say, for example, in this particular case, yeah. So cool. So for example, if you want to apply an H1, so the value of H1 in this case is -25. We all know it. So then when you apply a tan H activation, let's say for example, you apply a tan H activation, look at what the tan H activation, tan H of -25 is going to be. So let's go back here. So you look at the formula, 2 by 1 plus e to the power of -2 power x. The way, actually, I think the right formula for this, we can come back to, we can actually look at this later. The actual formula is this: e to the power of x plus e to the power of -x by e to the power of x minus e to the power of -x. This is the actual formula of tan H activation. So if you apply if you apply -25 to it, so this is basically going to be e to the power of 25 plus e to the power of -25 by e to the power of 25 minus e to the power of -25. So compute what e to the power of 25 is. This will always return a value that will range between -1 to +1. Come what may, it will always return value between -1 to +1, whatever it is. You can compute what e to the power of 25 and e to the power of 25 is, and then you'll figure it out. So the point that I'm essentially saying here is that irrespective of whatever may be the value, this tan H activation will always return a squashed value, a value that is between 0 and 1. See, I want you to sort of look at it this way. See what it is doing. See what these functions are doing. You are getting raw values for as inputs. From x1 and x2, you are getting raw values. And then you are multiplying those raw values, and then you're getting another value over here. At h1 and h2, you're basically getting another value. By applying these activation functions, what it is doing is that these activation functions are basically transforming these numbers into much more handleable values, because x1 and x2 can be very large input values. But when the moment they come in, what you're doing is that you're applying these activation functions and you're actually squashing them. You're actually making these values much smaller. The moment they become much smaller, what happens is that they become more computationally more handleable throughout the complete process, because larger values make the computations more difficult.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
So by reducing those values and by making values more smaller, it is making the computations more easy. Secondly, by applying these non-linear functions, you're adding a lot of non-linearity as well. Okay, that's one of the reasons why these activation functions are really very helpful. Do not look at these as, okay, in this particular scenario let me use tan H, in this particular scenario let me use sigmoid. I think the way you should look at it is, hey, look, I have these set of options with me, and when I'm solving a particular neural network problem, I can try out few of these and then come up with the best possible. I can attempt each of these, treat each of these as equally useful, and then come up with the best possible combination of my activation functions. There is no rule of thumb of saying for this kind of data these activation functions are going to work. I mean, there are a few heuristics, but I wouldn't want you to look at it that way. I think the best way to look at it is, hey, there are a bunch of activation functions that I can use. There is a kind of architecture that I can build. I will try different combinations of architectures and different types of activation functions and then come up with my own architecture that will work best, that will come up with the least possible error. So look at it that way, Sushira. These are just different options that you have. Amandeep, so we will do something at output node also, re-engineering and output. Yeah, absolutely. Even at the output layer, you can. So like for example, in the case of a classification problem, binary class classification will apply sigmoid transformation. If you are solving a multi-class classification problem, then you would apply a softmax activation function. So yeah, I mean, you will be trying out different activation functions even in the final layer. It's generally not normal to apply a lot of activation functions in the last layer. We apply activation functions in the last layer only if you want your output to sort of be formatted in a certain fashion. Um, where generally what people do is they apply a lot of activation functions on the hidden layers. Only if you want your outputs to be rather between 0 and 1, or you want to do some kind of normalization, only then you apply some kind of activation functions in your last layer. Can results also be compared between different functions? If Tom has a question, if compressed in such a way, yeah, absolutely. So the way you're going to do it is, Tom, you'll apply a certain kind of an activation function, build a network, build your model, and see the accuracy of the model. If the model is great, then great. If it is not great, then you go back, you change the activation function, and then again see the output of your model. So you will evaluate how well your model is performing based on the output and the accuracies of your model. If your model accuracy is great, then your activations are great. Else you will have to come back and change something to make the model more efficient. Just like your decision tree algorithms, just like your boosting algorithms, we're going to do the same exact thing. Let's go back. This is the other activation function, guys, called as ReLU, right? ReLU stands for rectified linear units. Right? Rectified linear unit. Right? That is what ReLU stands for. Um, if you are if you're familiar with diodes, and how pulses are passed via diodes, you would kind of relate to this. This is some kind of a diode, rectifiers, right? So these are very similar to that. So the point simply being that what rectified linear units do is, if the value is less than 0, it'll return a 0. If the value is greater than 0, it'll return whatever the value is as is. So it basically kills negative values. That's what your ReLU does. The ReLU will always return values from 0 to infinity. What if the input into the ReLU activation is a negative value, it will kill the negative value, it will return a 0. If it is, it will only return a positive value. If the value is positive, it will return the value as is. If it is negative, then it will return a 0. That's essentially what this does. So if it says, if it is 0 for x less than 0, x for x greater than or equal to 0. That's essentially what your rectified linear units do. So what it basically does, this is this rectified linear units are primarily chosen they are the best choice for to be applied in the hidden layers. In most cases, what we see as ReLUs are probably the best. And there is one more variant of ReLU called as leaky ReLU. What people have observed is that at times, if you sort of apply, at times if you sort of apply the actual ReLU, it kills negative values. So to kind of not kill the negative values and to sort of keep the computations going, because imagine what may happen is, for example, H1 and H2 both return negative values, then the output of both of these is zeros. And if you applied a ReLU, then output of both of these is zeros. Then what happens there is that then there is no value that is going to go ahead. the y is also going to become 0 then in that case. So the complete network will become stale. So to kind of not do something like that and to kind of keep the network going, what you do is you kind of let you let a little negative value go through. You don't completely let the negative value go through. You just let a small negative value go through. The way I think you should try and understand ReLUs is that if there are any negative values in the system, ReLUs tend to kill those negative values. So when you're doing the computations, ReLUs basically kill negative values. That way, what happens is that they tend to only keep positive values, and that way, your network tends to converge much faster. Or in the computations of your in your computations of your weights, rectified linear units actually help much faster because they kill the negative values very very quickly. Just learn that in research, what people have understood is that ReLUs are actually super good. There are scenarios where we might need negatives too, and that's exactly the reason why we have leaky ReLUs, just so that you let a little negative values go through. Because if the complete thing is positive, and if you do not have any negative values, then the network might not really have any kind of negatives in it, and they might not be canceling forces. So that's one of the reasons why it's always good to have leaky ReLU, use leaky ReLU as well. So ReLUs and leaky ReLUs are actually most popularly used. But then, yeah, I mean, I'll try to give more intuition in our next session. Okay. Okay, let's go on. Then this is softmax activation. Softmax activation is basically like your sigmoid activation only, sigmoid function only. This softmax activation is actually used in the output layer, especially when you're solving a multi-class classification problem. Your softmax activation basically helps us always return values between 0 and 1. Like for example, imagine a network that looks like this. Think of a network. Now, you're basically returning 3 outputs. So it's a super complex network, basically because there are too many hidden layers in between. But then you're essentially returning 3 outputs. Let's say this is y1, y2, and y3. You're returning 3 outputs. And let's say you're solving a 3-class classification problem. So, but y1, y2, y3 are all going to be values which are going to range from minus infinity to plus infinity. They all will range from minus infinity to plus infinity, right? So because they're going to return from minus infinity to plus infinity, the problem is then going to be that because you're solving a classification problem, you want the outputs to be squashed between 0 and 1, and you want them to be like probabilities. So the best thing to do in that case is apply a softmax activation in the last layer. In this layer, apply a softmax activation. So when you apply a softmax activation, what it will do is it will return values. So for example, if this is 100, 50, and 50, let's say the outputs are in that particular fashion, your softmax activation, what it would return is it would return 0.5, 0.25, and 0.25. It'll basically do something like that. It'll do some kind of normalization of your final outcomes. Whatever are the values that are coming in from this particular layer, with the softmax activation, they become a little more. They all then sum up to 1. They all will then sum up to 100 to a probability score of 1. They get normalized. That's the beauty about softmax activation. The only place where softmax activation is generally used is in the last layer. Just like how we applied a sigmoid transformation for binary class classification, when you're solving a multi-class classification, you apply softmax activation. Right. Irrespective of 3 class, 4 class, n class, how many ever may be the classes, the last layer, if you apply a softmax activation, the outputs will always be between 0 and 1. And they will all sum up to, let's say, all the outputs will then sum up to 1. Yeah. So a multi-class classification problem can be like you're looking at an image and you're predicting if it is a cat, dog, a mouse, or let's say something else. So in this case, cat, dog, or mouse, you're essentially predicting is the image a cat, dog, or a mouse. So you're getting 3 probabilities, but then you want to squash all of them between 0 and 1. That's where you apply a softmax activation, and then it will give you values like 0.5, 0.25, 0.25. So 50% chance that it is a cat, 25% chance that it is a mouse, and 25% chance that it is. Hope that clarifies. Are we okay with this, everyone? We've probably come in the learnings of neural networks. Probably we've come to a point where we don't have to reinvent the wheel.
Um, Luckily for us, it is an established fact that applying rectified linear units or ReLUs could actually be uh, fairly help. We probably don't have to try something overly complicated. We will just apply a softmax activation or a sigmoid activation at the last layers if you're solving a classification, a binary class classification or a multi-class classification problem. That is a choice that we will still apply, but the choice of rectified linear units or leaky rectified linear units, leaky ReLUs, in general is like an obvious choice these days. Most folks who actually build a classification or any kind of a network, they simply go with ReLU activation functions in the hidden layers. That way, it doesn't make it really complex for us. So it's not a big decision to make. Irrespective of the models that we're using, activation functions with ReLUs are actually much better. We learn about something later called as vanishing gradient, and that will help you realize that vanishing gradient problem is something that is a huge issue with sigmoid activation and tanh activations, and that's one of the reasons why ReLU activations are actually much better. Are we okay with this, everyone?
uh, ELU essentially looks like this, right? So, for example, anything that is positive, it's the same. You get X, but anything that is like negative, in the case of let's say a regular rectified linear unit, you'll simply have a 0. But in the case of leaky ReLU, you have something like this. In the case of ELU, you have something like this. So this exponentially changes. So to simply put, this basically looks like this. So, if I were to mathematically represent it, ReLU is 0 when X is less than 0, or rather, ReLU of X when X is less than 0 and X when X is greater than or equal to 0. Leaky ReLU of X would simply be 0, 0.01 times X when X is less than or equal to 0. When X is less than 0, and when X is greater than or equal to 0, you simply return X. And on the other hand, you have something called as ELU, exponential linear unit, right? Of X is simply as simple as it is X when X is greater than or equal to 0. But this is basically, something like e to the power of minus X when X is less than 0, something like that. And this basically e to the power of minus X. So yeah, this is not this curve, right? My bad. I think I should correct this side of the curve. Let me just quickly correct it. In the case of ELU, it looks like this. This is the exponential part. So think of it like this: a curve that basically goes like that. This is So this is going to be it is like leaky ReLU. It's a slight variant of this. That's it. Think of it as a slight variant of this. That's about it. Yeah. Okay. Cool. Cool. So yeah, that's it. There are other activation functions as well. Like for example, there's something called as swish, and this is basically that was invented by Google researchers. They say that this is X into sigmoid of X. So sigmoid, this varies between 0 and 1, right? And this can be anything. This can range from minus infinity to infinity. So effectively, this value can range from minus infinity to plus infinity. That means this is a small non-linear function that we are trying to apply, X into sigmoid of X. That's what is swish. And it sort of looks like this, basically. Yeah, you're going to have negative and positive values in a way. So even people have observed that even swish is also sort of very, very popular. But then while these are popular hidden layer activation functions, these are all hidden layer activation functions. ReLU and variants of ReLU are very, very popular hidden layer activation functions. For last layer activations, so let me put it this way: hidden layer and output layer. For hidden layer, you have ReLU, leaky ReLU, ELU, swish, and then you also have tanh, and these are all like hidden layer activation functions. On the output layer, you have like sigmoid. You can also use sigmoid here, by the way. You have sigmoid and you have softmax. These are the popular output layer activation functions. Even identity. I mean, you can use identity anywhere. Identity is not applying an activation function. You can essentially not apply an activation function. That's also a choice. But basically, yeah. But from an efficacy standpoint, on the hidden layer side, these are like super effective. And on the output layer side, these are super effective. I mean, you would apply an identity activation if you're doing regression. If you're solving a regression problem, that's when you'll not probably have an output layer activation. So this, in a way, this is also okay for regression outcomes, and this is for a classification outcome. That's basically what it is. So guys, remember, just a quick point. So whenever somebody says they're applying a sigmoid activation, remember that this can be visualized like this. This can be visualized like this. So think of two parts. The first part is where you're doing a summation, and the second part is where you're applying the sigmoid. So that means when you're doing the summation is x1 w1 plus x2 w2. That's what you're applying first. And then you're applying the sigmoid transformation. So then it is basically a sigmoid of whatever outcome this is. So this is x1 w1 plus x2 w2. So visualize it like that. Okay, cool. Anyways, I think again, guys, I want you to intuitively solve this. So I mean, you can let math do the magic, but let's try and solve this intuitively first. Let's first solve this problem. What is x1 w1 plus x2 w2? Anyone? So x1 w1 is 0.8 into 0.1. So this is basically 0.8 into 0.1. This is 0.08 plus 0.2 into 0.6, which is 0.12. 6 to 12. So this is 0.12. So this will be 0.2. Brilliant. So the output from this, so this value is 0.2. So this is sigmoid of 0.2. Now tell me something. Logically, if you looked at the sigmoid function, the output of sigmoid ranges from what to what? The output of sigmoid ranges from 0 to 1. So if the input is minus infinity, then we're essentially saying the output will be 0. And as you go along, and it becomes like positive infinity, when the input is like plus infinity, the input is x. Input is positive infinity. This is 0 and this is 1. So the output becomes 1. That's essentially how this curve looks like. What is this value? What is this point? The line that I just drew. This is 0.5, guys. So when the input is 0, the output from my sigmoid activation would be 0.5. That is essentially what is going to be 0.5, right? It's as simple as this, right? Basically, this function is telling me that it's essentially saying this is 1 by 1 plus e to the power of minus x, whatever this x value is. If this x is plus infinity, 1 by 1 plus e to the power of when x is plus infinity, this is going to be infinity, so this value will be 0. 1 by 1 plus e to the power of minus infinity will again be plus infinity. When my minus of plus infinity, and in this particular case, this value will become 1. So the point that I'm trying to drive is when the value is from minus infinity to plus infinity, the input is either 0 or 1. So when the input is like very, very close to 0, what will be the output? Will be close to 0.5. Absolutely right. The output will be close to 0.5. Will the output be greater than 0.5 or less than 0.5? It will be slightly greater than 0.5. The reason being that the input that I'm passing is a positive input. So it will be slightly greater than 0.5. That's the intuition, because it is positive. No? So positive means it will be on this side. For this side essentially means slightly greater than 0.5. Yeah, that's basically what the output should typically be. So if you actually solve it using the sigmoid, 1 by 1 plus e to the power of minus whatever the value is, minus 0.2. If you actually solve it using NumPy, let's not worry about this too much for now. Import NumPy as NP, and this is essentially 1 divided by 1 plus e to the power. E is np.exp minus 0.2. Sorry, this is e to the power of minus x, so this is essentially that. So it's 0.549 if you see.
So the output is essentially going to be 0.549. 1 by 1 plus e to the power of minus x. Yeah. Cool. Anyways, that's as simple as how activation functions typically work in this case. So I wanted to visualize it like this, guys. So whenever we talk about applying an activation function, it's always first the summation, and then the summation goes into that activation function, whatever that. So just remember it that way. Cool. That's as far as our activation functions is concerned. So let's go back here. So if I were to sort of talk about how how we can actually learn a perceptron algorithm, we've already gone through this. I'm just running through the slide for now. So what the slide is, what we're saying is we start with some kind of inputs and weights. That means your W1, W2, W3. We start with some form of weights, and then we go through the whole thing. We basically run our data through it. We compute what the error is, and then based on the error, we come back and we change the weights so that we would want to make sure that we reduce the error. Same thing like your linear regression problem. So what we are going to do is we're going to initialize our weights with some random values, and then with those random values, we run a forward pass. But when we run a forward pass, we get a prediction. But based on that prediction, we get an associated error with that particular prediction, because your model is either too good or too bad or whatever. You're essentially going to get some kind of an error. If the error is extremely high, then what you do is you go back and you update your weights. You run some kind of an update function. Let's not worry about this function right now. Some form of an update is what we run to our weights, to our W1, W2, W3, how many ever weights are there. We run an update. We change the weights a little. We don't know in which direction, we don't know what, but we essentially perform some kind of an update. And once the update is done, then you again go back. Hit and trial, Prashant, is one way of changing the weights. But of course, hit and trial will take us forever. So there are different algorithms that we will learn that will make it easier. And what you do with once you start learning the weights, once you start changing the weights, you see that, let's say, if the output is getting better, you end. If it is not getting better, then you again go back, and then you again change the activation, and then you again change, let's say, your weights. So you keep iterating through this process until you find the right kind of weights. So yeah, that's basically the typical process of your learning algorithm or your perceptron training algorithm. That's it, guys. Think of biases. So in your linear regression problem, what is the importance of an intercept? Why is intercept important in your linear regression algorithm? A bias is the same thing here. Think of bias as the same as your intercept in your linear regression algorithm. So for example, you also train so in the case of a linear regression problem, just to kind of throw some kind of an intuition, error, think of it as error, Rohin. But I think intuitively, from a business standpoint, this is why intercept is super important, and training an intercept value is super important. So let's say I'm predicting sales, and I'm saying I'm going to predict sales as a function of money spent on ads, and also you're trying to predict sales based on the number of stores. We saw the same example the last time as well. So if you're going to say train a linear regression algorithm on this, so your linear regression could say sales is equal to 10 times ads plus 5 times number of stores. Okay. Now, for some reason, money spent on ads. This is basically, when I say ads, that is money spent on ads, or the number of ads. Think of it as number of ads. So let's say on any given day, if your number of ads are 0, and if your number of stores are also 0, then what your linear regression algorithm is saying is that your sales are going to be 0, which sort of doesn't make sense, because you're probably not just running your sales via your stores. Stores is probably one of the ways of running your business. You're probably running your business with, let's say, your stores, you have a web business, you have an e-commerce platform with which people can come and purchase products. So the number of stores that we talk about is not the only feature that could determine, or these two are not going to be the only features that will determine the sales. Exactly, there would be some minimum sales that would happen. Yeah, I mean, if there are no ads and no stores, the sales are going to drop, but that doesn't mean my sales are going to be 0. So to compensate for that some minimum sales, I want my model to have some amount of bias by default towards my sales.
That's basically where I train a bias, or in the context of a linear regression, we call it as an intercept. That's as simple as it. And that's the same thing as your intercept. Okay. This was one of the questions that was asked to me in one of my interviews. Why do you need an intercept in a linear regression problem? So yeah, I mean, I think so. Basically, constant is the same, right? Constant is the same as an intercept. When you say plus c, that is the intercept term, and that is the same as bias in this case as well. So when you say y is equal to mx plus c, the c is nothing but the intercept. C is nothing but the constant. It is interpreted differently at different places. So right. So we may not account for some features, and for all of those additional features, you're essentially training one metric that kind of captures everything else. That's like a catch-all. Think of it like a catch-all. So for features that you do not have as a part of your model, you're essentially training another interceptor. Cool. That's basically where bias comes into the picture. Brilliant. So let's go back. Let's go back again. So that's what we're saying over here as well. So when you say bias, so when you say x1, x2, x3, x4, and when you say bias, that's essentially the same thing. So we're saying sales, ads, money via e-commerce platforms and all of that, plus a constant. Bias is nothing but a constant. Now, this is the process that we would ideally want to follow. That you start with some random values, you calculate, you go through the models, you try and make a prediction, and based on the prediction, you compute the error, and based on that error, you realize that, hey, look, there's a lot of errors, so I need to go back and change my model. Changing a model essentially means changing the weights. So if I have to change the weights, I don't know which direction to change. Let's say there's a known way to make that change and make the change in some fashion. And once that particular change is made, then we again come back and retrain the model using the updated weights. At times the weight may work in your favor, may not work in your favor. Again, you go through this process once again. So you iterate through this complete process, let's say 10, 15, 100, 1,000, 2,000 times based on the data that you have, based on the volume of data you have, based on how long it is taking for you to learn the new weights. You run through this complete process. If you're doing a hit and trial, you will just probably be going in circles, and it might take you infinite times. Theoretically speaking, it will take you infinite times to reach a good model. So you need a more robust approach towards updating weights. So one of the ways is called as gradient descent. We will learn about that later on. But technically, there is an approach towards updating the weights. Yeah, I mean, so broadly, this is like at a very, very high level. What we've been talking about until this particular point is like those fundamental components of AI and neural network. We haven't really dug into the depths of it. Right now, we're going to do it in the next few minutes. But to kind of give you that high level view, by now you must have understood that, hey, firstly, you can, with the components that we sort of spoke about, you can do a lot of nonlinear data processing. And Vishal, to your point, the reason why we would want to add the activation functions is to capture nonlinearity. Without activation function, you're essentially training a linear regression problem. So the activation functions give you that nonlinearity, the ability to capture nonlinearity. So organic learning, because the learning process is very, very similar to like how the to let's say how a human brain typically captures these patterns. And secondly, there's a very, very robust approach towards generating features internally. Remember we spoke about that. You can sort of generate features internally by adding multiple hidden layers and everything. So that kind of adds to the whole complexity of the model and helps us capture more complexity.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Fault tolerance, the reason why we're saying it has sort of a fault tolerance is because there are certain techniques when we talk about, let's say, retraining, or rather when we say that we'll probably go back and update the weights. So this process of going back and updating the weights is actually pretty good, because we're simply not saying that, hey, we'll start with a set of weights and then we'll stop there. Rather, what we're saying is that we're going to run this multiple times until we get to a certain level of error, until we reduce the error to a certain extent. So that's the whole point of fault tolerance, because there is fault, but then I think the best part about that is, you have an internal way of sort of repairing that particular approach as well, just like how a human brain works, so to say. Yeah, so these are like broad brushstrokes of the benefits of neural network. Of course, the benefits are like way too many. These are just a few ways of sort of representing the benefits. Organic learning is the way we sort of build our neural network, because it's based on neural topology, our neural nervous system. So the learning is actually quite natural. The learning comes very, very naturally to the algorithm. So that way we're saying that it's quite organic in nature. I don't know why I would want to call it organic, but yeah, they've named it that way for some reason. Cool. Now comes the actual part, right? Great. Now that we have these components, we've like at a 10,000 feet level, we've understood what is a neural network. We know what are the components that go into a neural network. By now, you guys must have understood that this is not some kind of a sorcery. We are not doing some kind of a magic here. It's not that deep learning models are any different from, let's say, your traditional ML models. Deep learning models are very, very similar to the traditional models. In fact, to train a deep learning model is actually more difficult because of the kind of complexity that you have. There's too many things that you have to manage. So don't expect the platforms to sort of take care of everything for you. At the end of the day, there is a lot of scope for a data scientist to pick the right choices from his or her side as well. Picking the right activation function, picking the right architecture of your deep learning network, and whatnot. So what that leaves us with is, okay, this is all great, but does it mean I'll have to write code for all of this every time? That does it mean I have to actually create a graph and everything? The answer is, well, you can, but then it's going to be extremely time taking. So there are a few pre-built libraries that we have, like what you see on the screen. These are few of the many libraries that are there outside today. For all you know, these are not the only libraries. These are the popular libraries, let me put it that way. These are like, I'll probably say the most popular libraries what you see today. And again, even within these, what we are currently observing is that there are sort of two libraries which have two deep learning frameworks which have become more popular over the last few years. One of them is TensorFlow, and the other is PyTorch. They've sort of become super popular over the last few years. And of course, TensorFlow has the advantage of a head start. TensorFlow was one of the first movers into this field. TensorFlow is from Google, and they are the ones who actually, for the first time, implemented deep learning frameworks, and they've open sourced it for the larger audience to use. On the other hand, PyTorch is from Facebook, and they've open sourced their deep learning framework that was built internally. So similarly, a lot of these other frameworks have come from different organizations. Keras is again an open source. These are all open source projects. Interestingly, even NVIDIA has their own deep learning framework, and they're all super complex, super useful to use. Right now, out of the frameworks that you see on your screen, TensorFlow and PyTorch are the ones which are really popular. So TensorFlow is, like, as I said, the open source software library for numerical computations. They're not only for deep learning. I mean, I think for any kind of numerical computations, TensorFlow has become like super popular. Yeah, I mean, these days you can do anything with every library. NL, natural language processing, classification, forecasting, object detection, computer vision, everything is possible using every library in some form or the other. There are two really cool functionalities from TensorFlow, and one of the reasons why TensorFlow has become so popular is because TensorFlow is built for enterprise grade solutions. It is not just built for research level solutions. It's actually an enterprise grade. It's not like R. Let's put it that way. R is not built for enterprise grade applications or solutioning. Python is slightly better at it. R was never built for it. On the other hand, TensorFlow is not like that. TensorFlow was built primarily with the outlook of not just TensorFlow. As a matter of fact, all the other libraries that we're talking about, they're all built with the outlook of making these models operationalizable,
So like for example, you have like these two these two plugins from TensorFlow called TensorBoard and TensorFlow Serving. TensorBoard is like, imagine you have like a complex neural network and you want to understand what are the values inside a particular node, what are the values that are going from one node to another node, what are the weights, what is the error like. So you want to, let's say, dig into more details of the neural network that you've built. You can use TensorBoard. If you have time, we'll probably try and explore TensorBoard in our session sometime. TensorFlow Serving, on the other hand, is basically an web service, a web framework that is provided by TensorFlow to operationalize TensorFlow models. Yeah, by the way, thanks for pointing this out. Majority of these libraries are all libraries for Python. Majority. That's essentially why I'm saying majority. Like for example, DL4J is deep learning for Java, right? So that's what DL4J stands for. So majority of these libraries are based on Python. TensorFlow is based on Python. So TensorFlow is not another tool. TensorFlow is essentially a library in Python, just like how a scikit-learn is. Similarly, Keras as well. So the thing about Keras is Keras A is like a deep learning framework, and Keras is also a high-level API on top of TensorFlow. So, for example, what I mean by that is, so you have, let's say, TensorFlow, and let's say you have Theano, CNTK. These are all different, libraries that are available, and Keras sort of sits on top of this. So Keras is like a high-level API on top of Theano, right? Ideally on top of Theano. Originally, it was built for Theano. Theano is another deep learning framework. These are all DL frameworks, DL libraries. So if you want to just work with plain vanilla Keras, then you're essentially building deep learning models using a framework called the underlying framework called as Theano. But then what these guys have done is the folks who've actually built Keras, they've become so smart. They said, okay, they've sort of separated this out very well. So they've seen that, okay, there is a lot of traction for TensorFlow, and there's other libraries coming through. Like for example, there's something called a CNTK by Microsoft. This was for Microsoft. So Keras sort of became that high-level API, wherein they said that, you know what, you can just write your code in Keras. So don't worry about what the underlying framework is. You just write your code using the Keras API. We will take care of which one. You can simply switch, saying, hey, look, I want to work with TensorFlow, or you can switch to Theano, or you can switch to CNTK, just by changing one simple parameter. So your code will remain the same. If you simply say, I want to work on TensorFlow, or you're going to say, I can work on Theano, or you can work on CNTK. You can do whatever you want. So the moment Keras came up with that cool functionality, people realized that, hey man, this is really awesome. So people started using Keras because like Keras is like super easy to write deep learning code in. That means to build a network, it's like very, very easy using Keras. So suddenly what happened is TensorFlow was very popular and Keras became very, very easy to code. So people started to use this as a combination. So this combination of Keras plus TensorFlow became super popular. So right now, when somebody says I'm working on TensorFlow, most people are actually working on TensorFlow via Keras. So the combination of Keras and TensorFlow has become like super, super popular. Most folks today, they work on Keras using TensorFlow as the backend. And the good part is that what people have very, very often mentioned is that working with TensorFlow is like super difficult. At least the version 1 of TensorFlow was like super difficult. The version 2 has become much more easier. But working with Keras and TensorFlow together has become like super, super easy right now. So we will realize it when we actually start writing code that it's not very complex. It's not all that complex. So what we are going to do in our session is we're going to do a lot of Keras plus TensorFlow combination. You'll see that a lot of implementations are basically a Keras plus TensorFlow combination, and it's not just in our session. In general, also Keras plus TensorFlow as a combination is like super popular, even in the market out. So remember, at the end of the day, what happens, folks, here is that whenever we call something as a deep learning framework, every deep learning framework is essentially going to be based. They have broadly two components under the hoods. One is the underlying mathematical libraries, because they would be using a lot of mathematical libraries under the hood. Right? When I say I'm going to use TensorFlow, I am simply not saying I'm going to use TensorFlow, because TensorFlow internally uses a lot of underlying mathematical libraries like BLAS and whatnot. There are a ton of mathematical underlying libraries that enable doing the algebra and linear algebra and all of that efficiently. So long story short, the mathematical library side is one side of things, and the other is the interfacing with the developer. So let's say like for example, when you say CLF is equal to decision tree classifier in scikit-learn, when you say decision tree classifier, this is just the front end call for your function. Under the hoods, there are a lot of mathematical functions that are being called. So what Keras did was Keras kind of separated these two up. They said that this is great, this is Theano, the underlying math engine is Theano, but they said the front end engine is going to be Keras, and we're going to use it as a general purpose front end for every other thing. So one is I can use it for Theano, the other I can use it for TensorFlow. I can also use it for, let's say, other stuff as well. So they built connectors for each of these functions. That's what they've done. So that's the model that they've followed, and that's how it is sort of easy for us to, as a developer, it becomes really easy for us, or a data scientist, it becomes really easy for us to switch between doing different libraries under the hoods. I hope that makes sense, Dave. Okay, cool. So yeah, I mean, Keras has, as I said, recurrent neural networks and convolutional neural networks. Again, same stuff. Whatever TensorFlow can do, even Keras can do the same thing. The beauty about Keras is that, the way you write code is that you kind of stack one layer on top of another. So you build like your first layer, the input layer, then you build your first hidden layer, then the second hidden layer, then the third hidden layer, then your output layer. So you define each of these layers separately, and then you sort of combine all of them together. As simple as that. That's basically how your Keras typically works. So that's essentially what they mean by stacking layers one on top of another. PyTorch, on the other hand, has started becoming very, very popular over the last 1.5-2 years. Let me be very honest. Today, PyTorch is giving a nice run for the money for TensorFlow as well. Today, there's a huge community for PyTorch as well, and apparently PyTorch also is pretty good, pretty easy for us to sort of learn and start going. Now with so many libraries coming in, the question is, which one should I learn? Now, I don't think the question should be which one you should learn, because there are so many frameworks. By now, you must have understood that these are all just frameworks. This is code at the end of the day. If you understand the underlying math, and if you understand how you can implement with one of the frameworks, you can comfortably implement the same using other frameworks as well. So I don't think the question should be, should I learn PyTorch or should I learn TensorFlow? I think the question should be, how do I learn deep learning? Can I implement deep learning using PyTorch, or can I implement deep learning using TensorFlow? The answer to both the questions is yes, you can. Pick any one and learn it. And once you learn it, and then you can always switch between these frameworks as you go. So suddenly you might start working on a project where you're required to use PyTorch, or maybe the other team members are very proficient in PyTorch, so you might have to learn PyTorch. But it doesn't matter. At the end of the day, you have to start somewhere. And I think TensorFlow and the Keras combination is actually a tried and tested combination. PyTorch is very new in the market, new kid on the block, very, very promising kid, a very, very promising framework. So if you have some time later on, please feel free to pick that up as well. But yeah, I mean, if you honestly ask me, should you learn everything? The answer is no. There's no point in learning everything. Just pick one framework and just go through it. Go through one pass of it, you will understand how to implement. Once you're sort of confident of implementing it once, you can always switch between frameworks. It's not really that big of a deal. Oops. So the next is, of course, DL4J, deep learning for Java. This is surprisingly, this is a deep learning framework for Java, and this is quite popular in the Java world. I mean, for ones who come from Java world,
who want to sort of implement this, you can comfortably implement it using Java. It's quite popular as well. Um, the other cool thing about the reason why this is sort of become like super popular is because when you're working with Spark and when you're working on Hadoop, because the underlying framework of Spark is all JVM based, it's all Java based, that's where DL4J took off. That's where deep learning for Java became very, very popular, because Spark under the hoods is all Java and Scala. It all runs on JVMs and runs on Scala. And DL4J is a deep learning framework that is built for Java. So it became super easy for them to adapt DL4J to work on a distributed computing framework. So you could sort of use it for Hadoop or use it for Spark. So DL4J runs really very well on any of these if you want. The deep learning library and framework is the same. This is much more than just a library. I don't want to call it a simple library. This is a framework. The reason why we're calling it a framework is because it kind of gives you a structured approach towards building models. It's not a simple function. A library is a combination of a few functions. This is not just simply a function. Like, for example, in the case of a decision tree classifier, it's a simple function or a method. You just apply it and then you get going. But here, that's not the case. This is the reason why we call it a framework, is because it kind of gives you a combination of approaches towards solving a problem. Scikit-learn, you can call it a library, but essentially it's an ML framework as well. Scikit-learn also in some form or shape is a framework, because it kind of gives you the complete suite of solutions for machine learning in Python. Calling it a library is probably a very technical term from a Python way standpoint. But the reason why we call it a framework is because it gives you much more than just functions. It gives you functions, but along with it, it also gives you an approach towards, okay, so when you're building a solution, along with this solution, also apply this particular method. So it's a combination of methods that you'll always have to apply to arrive at an outcome. Yeah, I mean, it's not a collection of packages or a libraries, Priyanka. It's one library. When you do an installation, you would see it, right? You would essentially have to do Conda install TensorFlow. One library. It is one single library only. It's not like many libraries. The framework, because you're essentially doing much more than just applying a simple function. I want you to just understand that, because deep learning is not just as simple as just calling a simple function. Cool. Yeah, and the other one is MXNet. Somebody asked me how can I implement deep learning in R. So here you go. MXNet is one way of applying deep learning in R. But I'll be very honest with you. Somebody who's asked me, what should I do for R? I'll be very honest with you. I think applying deep learning in R is, I think the ship has sailed for R. To be very honest, I think the ML ship has sailed for R. I don't think there's any point in focusing on R, to be very honest, because as a programming language, R has really fallen very, very has fallen behind by a few, almost a decade now. So I don't really see R becoming like another tool where you could start applying other complex approaches. You can try, but for experimental purposes. But I think the ship of R has sort of sailed. Right now, the focus is on Python and significantly on Scala as well. So yeah. I mean, again, as I said, MXNet also you can do the same things. You can apply do computer vision, that's imaging, natural language processing, forecasting, speech recognition, whatnot. You can essentially do everything. All these libraries in some form or the other give you the capabilities to do almost everything. If you sort of draw a Venn diagram, almost everything overlap on top of another to almost around 70-80%. There'll be probably some stuff which is very specific to a certain library, but net all libraries in some form or the other have the same approaches. Brilliant. So let's talk a little about TensorFlow, because that's going to be our primary tool of choice or primary library / framework of choice for the rest of our session. When I say session, what I mean is the rest of our course. I think it's important to understand why do they call it TensorFlow, and firstly, what do you mean by tensor? Right? You must have heard of a scalar and a vector. Tensor is something very similar. A scalar is a single number. Vector is an array of numbers. Tensor is basically, think of tensor as a slightly more complex, a generic representation of the same thing. Yeah, let's say a tensor can be a single number, a simple scalar, or a vector, or it can also be, let's say, a matrix of numbers, or it could also be, think of it as a cube, right? A three-dimensional array of numbers. That is also a tensor. So these are all different tensors. In the case of a tensor, you don't have direction, you just have magnitude. In the case of a vector is a two-dimensional array, rank 1, we call it as a rank 1, because it has only one single dimension. Values just move in one single dimension. In the case of a matrix is two-dimensional, or the rank is 2, because you have rows and you have columns. And in the case of a tree tensor, all these are tensors, they're all n-dimensional arrays. So popularly, the three-dimensional tensor is something that has, think of it as a three-dimensional, think of it as a cube. Yeah, think of it as a cube. You have different values. So you have rows, columns, and you also have depth, right? X, Y, Z, all three dimensions is what you have. So to represent a particular number, that's essentially a tensor. So in the case of neural networks, what you would observe is that tensors are like really popular ways of referring to values. We don't call it a vector or a matrix, because if you start referring to something as a vector, something as a matrix, then it could get too confusing. So tensor is like a generic word that people use to sort of represent any kind of an array in general. So a tensor with two dimensions is basically a matrix. A tensor with three dimensions is, let's say, a 3D array, or a three-dimensional array is a three tensor. A tensor with one dimension is, let's say, a vector. A tensor with no dimensions is a simple scalar. That's what a simple tensor is. Tensor is like a generic term for everything else. The other point also is that these frameworks, all these deep learning frameworks, one of the things that is very, very common in all of them is they all work on computational graphs. And when we say computational graph, basically it's basically like representing a simple mathematical computation as a graph. So as you could see here, in this case, A and B are two values, and they sort of flow into a particular mathematical operation. And then that flows into another mathematical operation, and there's another input. And then the output is basically H. So if you kind of convert this whole mathematical operation into this whole thing into into a mathematical equation, it sort of becomes AB, right? Because we're essentially multiplying these two. So AB, and you're adding C to it. So AB plus C is what is H. So anyone quickly, what's the outcome here? A into B is 200 plus 30, 230. That's the basic outcome in this particular case. In the case of your TensorFlow, we call each of these computations as a computational graph, and each computation or every computational graph is executed inside a particular session. So it's called basically like a session. So every computation, this is a computation, and this computation is happening inside this particular session. For jargon's sake, it's not something that we should really worry about. But what we are saying is that all computations, when they happen inside a particular session, they have the values can be they can be used internally. Across sessions, variables are not shared. Inside a session, variables are shared, or variables are accessible to each other. Across sessions, variables are not accessible. That's basically what we mean by session in this particular case. So yeah, a node is a mathematical operation. Like, for example, this is a mathematical operation, this is a mathematical operation, and the values that basically get passed, they are all tensors. So this is a tensor. Like, for example, this is a tensor, this is a tensor, this is a tensor. These are all tensors. Popular programming elements in TensorFlow are you have something called as constants, placeholders, and variables. Constants, as you wanna are constant values. something that doesn't change. Placeholder values are values which are typically going to get assigned during an execution. They are like arbitrary constants. They're placeholders, as in they are not really, you know that there's a value going to come in there, but it's just that you haven't assigned any value to it right now. So the value gets assigned during execution. And a variable is, again, you simply say, X or a Y. These are simple variables. So we'll look at how they are very different as we go along. Like, for example, in this case, constants are program elements whose values do not change. So you simply say tf dot constant of 10. As simple as that. Placeholders, on the other hand, placeholder are, you simply say that, hey, look, there's a value that's going to come into it, but this value will come in at a later point. You're saying that there's a value that's going to come, but this value will come in at a later point. They are also actually a form of a variable only, but it's just that you're defining what type it is going to be. You're saying, hey, this is a placeholder, and expect a float 32 value coming through, or expect a string value coming through into this. Right? You're saying X and Y, and you're saying that expect a float or a string value to come through. So you're calling this as a placeholder value. So you're sort of booking that slot and saying this is what is going to come through. Then you have an actual variable, right? In this particular case, you have an actual variable. So right now what you're saying is that W in this particular case is a variable. So like, for example, right now TNA is called TF dot variable of 3 and TF float 32. What you're saying is that right now the value is 3. I can change this value later on. I can change this value to something else. Currently, the value of this particular weight is, or this particular W is 3. It can become something else later on. These values can change as they go along. That's what a regular variable, just like how we all know what a variable is. Let's quickly do a small, I just wanted to kind of show you how the whole variable things work, and then we'll dig into more depths. It's not that I want to kind of start using them right now because we really don't know how to use a TensorFlow library, but I just wanted to introduce you to those constructs. Let me just quickly open. There you go. So yeah, okay. So if you see, my TensorFlow is now up and running. So I've done an import TensorFlow as TF, and as you can see here, if you observe here, I'm essentially creating these as constants. Right, I'm just constant 1, TF dot constant of 3, 3.5 Sparta, and then false. So these are our different constants that I'm assigning. And as you could see here, when I print what these constants are, TF dot tensor, this is an int32, TF dot tensor 3.45. There is no shape. Observe that there is no shape because these are single values that you see over there right now. If, for example, you do something like this, right now, if you observe, the first one is TF of tensor 1, 3, because I have two values and the shape is 2. 2, comma, just like your Python tuples. So 2, comma essentially means it's one-dimensional array. And if, for example, if I pass this as a list of lists, then this will automatically be a tensor 1, 3, 3, 4. The shape is 2 by 2. Pretty straightforward, nothing very complex, just like a NumPy array, two-dimensional NumPy array. This is also a tensor. It's just that this is again shape of 0. I mean, no shape because it's a scalar in a way. Same is the case with the others as well. This is Boolean type. This is string type. Yeah, I mean, just give me a second. I'm trying to. That is basically, it's a version compatibility right now. So basically, I've ended up installing a version 2 of TensorFlow, and that's essentially the reason why supported in the long term. TF.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
There you go. So yeah, I'll have to be a little careful right now. What's happened is, again, this is basically the TensorFlow version issue. So I'll have to be careful moving forward. One of the things is that the TensorFlow has TensorFlow has actually changed the version very recently from V1 to V2 right now, because this notebook is in the version 1. I've just simply turned on the V1 compatibility of TensorFlow, and the V2 functions are currently disabled for now. But moving forward, we'll have to be careful of how the V1 V2s are sort of taken care of. But yeah, I'll make those changes. Actually, it was supposed to be a V1 V2 compatibility notebook. From these, I'm not able to find that. Cool. Anyways, for the purpose of the session, let's go ahead. I think it doesn't really matter. It shouldn't really matter to us, because I just want to kind of introduce these concepts to you. So yeah, right now what I've done is I've just created these 4 constants, and I've just said session.run. But then I've essentially wrapped them inside a list, and I've asked it to simply do a run. So it has returned a list of all these values, nothing else. But look at this here. So I'm defining 2 methods over here, or 2 graphs. Think of these as 2 computational graphs that I'm sort of creating here. And I'm calling something called as addition, and I'm calling it as multiplication. And I'm doing a session.run, and addition and multiplication have simply been returned. So this is basically 50 plus 10 and 20 plus 20. 20 times 20, it has simply returned a value, as you can see over here right now. Now, the thing here, of course, is that when you talk about the same, similar stuff over here as well, as you can see, I'm just passing a couple of lists over here. These are 2 tensors with dimension 1, 2 constant tensors with dimension 1. And what I'm doing is I'm simply adding them, and I'm simply multiplying them. And as you can see here, the values are simply being returned as simply the multiplications of corresponding values. 1 into 5, 4 into 2, 3 into 3, 4 into 2, and 1 into 5 again. So it's simply corresponding value multiplication. Essentially, 2 vectors are being simply multiplied right now. That's all that we see in this particular case. Nothing really out of the world. Here is where the interesting part comes in. Now I'm defining, let's say, 2 string values as constants, and I'm just running an addition on top of it. As you can see, a string addition, string concatenation typically takes place. Same stuff. Now here's where I'm defining a placeholder, right? Defining a placeholder right now. So when I define a placeholder over here, I'm saying A, expect an int 32 value to come through. And now I'm saying B is equal to A into 2. Right? B is, let's say, another outcome. B is now, let's say, the output of A, whatever this A into 2 is. I'm saying B is simply nothing but A into 2. Oh, so this B is just Unicode, guys. Okay, it's just saying it's a Unicode text. That's what it is. Again, so here if you see B is equal to A times 2, and I'm simply saying A session.run, I'm saying run this particular thing. But along with it, what I'm also saying is that I'm saying assume the value of A as 10. Remember, A is a placeholder value. So I'm assigning the value of A during the execution. The value of A is, in this particular case, is being applied during execution. So when I run this, the value of A is assigned as 10, and the value of B is computed as 10 into 2, and the value is returned as 20 in this particular case. That's the beauty of the placeholder value. Again, if you ask me what is the value of A right now, the A value is still a placeholder. It is still an empty value. There is nothing inside it right now. It is still a placeholder value. It only assumes the value of A as 10 in the execution of this particular session. Yeah, when you run this, what essentially it is doing is it is simply executing B. B is simply nothing but a multiplication of A and 2. A value is 10, so it is simply running the value of B and returning the value of B. So in this particular session execution, the value of B is 20. That's all that it returns. I'm simply asking it to return B. So when I say B plus B, return it as 40. So it is executing this. I hope that makes sense. So it is simply executing this particular piece of code that you see. But when it has to execute this, it needs what the value of A is. So if, for example, if I don't pass this, it'll throw an error, invalid argument error. It says you must feed a value for a placeholder, tensor placeholder with type 32. Right? So I'm just going to pass that, and when I pass it, it just simply gets executed. Same thing here as well again. Again, I've assigned this as a placeholder value. Same thing, I'm executing name1, and I'm taking for this particular execution, assume the value as Sam. Okay, that's it. So now look at this here. Again, I'm saying variable 1 is TensorFlow dot variable of 30. This is a variable now. Global variables initializer. This is basically simply initializing all the variables. This, what it does is whatever the variable I've assigned, it assumes, it basically initializes that particular variable. It runs the initializer first, and then the variable 1 is sort of available for me everywhere. Moving forward, the variable 1 is sort of available for me everywhere. You can ignore these two for now. Just don't worry about this as much, because in this particular case, I've assigned the variable and I'm trying to access this particular variable, but this particular variable doesn't exist because it is uninitialized, so to say. According to it, it is uninitialized. So one of the things that you need to do is you need to basically initialize your variables before you start using them. And the way you initialize them is by running those few lines over there that you need to initialize the global variables initializer, and then you need to run the session. These are just some extremely simple basics of the whole thing. Prem Sundari, the notebook is available in your new learning management system, so please refer to it. It is available there in your module 2. Everybody, this notebook is available to you guys already in your LMS. Okay, great. Okay, now that we've sort of at a very high level sort of got ourselves introduced to TensorFlow. Not that we know what TensorFlow is. It's just that we, at a very broad level, we sort of know what this TensorFlow is. What we are going to do moving forward is that we're going to start leveraging again these fundamentals, very simple fundamentals that we just kind of that we just kind of learned right now, and then we're going to build on top of this. We're essentially going to start building neural networks. But of course, to start building neural networks, we need to know how to build a neural network in the first place. So right now, what we're going to do is we're going to go back to our fundamental concepts of neural networks, and we learn how to actually train a simple neural network, how to actually build a neural network. Forget about TensorFlow and everything. What we're going to do is we're going to first start to train a simple, extremely simple neural network, like how you see on your screen right now. This is a very simple neural network, guys. Right? Simple perceptron. Right? It's a simple perceptron model, not multi-layer, a single layer perceptron model that we have currently. Okay. And essentially, this is basically like y is equal to w1x1 plus w2x2. That's basically what we're training over here. Something like this. So you have, so what we're essentially training is you have 2, x1, x2, w1, w2, and this is y. That's it. There is just a summation over here, and there is basically an identity activation function. That means no activation function. So in this case, y is equal to w1 x1 plus w2 x2. That's all that we are training over here. Given a specific value of x1 and a specific value of x2 and a specific value of y, I'd want to find the corresponding values of w1 and w2 in such a way that my model gives me the lowest possible error. Right? Let's say the x1 value is 10 and the x2 value is 20, and the y value is, let's say, has to be 30. Can someone tell me what should w1 and w2 be? Yeah, absolutely. w1 and w2 should be 1 and 1 respectively. Nothing very complex, right? Similarly, if I want this to be, let's say, if I want this to be, this is 10, this is 20, and if I want this to be, let's say, 29.8385, then what should w1 and w2 be? God knows, we don't know what those need to be right now, right? There can be any numbers. We can assume them to be something, and then we can basically you can assume some value of w1 and you can compute the corresponding value of w2 and all of that. But if you were to do it the actual neural network way, how do you go about solving this particular problem? So we're going to come back, and the aim is going to be for us to actually start to train this simple model. Yeah, this simple, very simple model that you see over here. So for example, x1 is 2, x2 is 5, and I want a y as 31. So in this particular case, I want to simply train a neural network model, and I want it to build until the error is 0. So if you see at this particular value of w1 and this particular value of w2,
almost at this value of W1 and this value of W2, the error becomes 0. That's what I'm saying. Similarly, if I have a x1 is let's say 10 and x2 is let's say 20, and I want my output to be 30, this different values that we've tried, we still haven't been able to completely come to a solution, but we have a framework to come to a particular solution in this particular case. So these are different approaches of coming to an outcome, guys. So like for example, 1 and 1, you see, right at word go, you hit the 0 because you're initially starting your W1 and W2 with 1. So you don't really need to optimize any further. You started with 10 and 20 and your Y is 30. And you're saying W1 and W2 is 1 by default. So the error starts at 0. But if, for example, instead of 1 and 1, let's say you started at 2 and minus 1, that's where things become a little tricky. So you have to keep trying until you basically come to a particular point where you see that the error becomes 0. So we keep running it. Let's say in this case, I've run it 50 times. I can run it 100 times probably, and I can hope that it kind of the error sort of becomes close to 0. Still, the error is -7. The error is actually extremely high right now. So yeah, let's not worry too much about it. We'll come to what these details are later on. But fundamentally, what we want is we want to essentially try out different approaches before we come to our solution. We'll first learn how to actually design this simple equation that we see on your screen right now. We learn what goes into it, and then we'll come back and then actually go through this particular piece of code and understand how this is implemented. This is without using any TensorFlow or anything. This is simple, plain vanilla mathematics that we kind of come up with this, where we are trying to solve for this neural network, this simple neural network that you see. Okay, so let's basically get started. Let's talk a little about why I think we've talked about this at a very broad level in our the earlier session, where we said why do we need hidden layers, and then I kind of gave you a very intuitive explanation of why we need hidden layers. And I think another approach or another way of looking at this is what we're going to talk about. Essentially, a limitation of single layer perceptrons. Like for example, why this simple models like these, right? Why these simple models are not good enough to solve the complex problems that we're essentially talking about. Like for example, when you look at data like these, like data like this, right? This is basically an AND gate. If you think of it, this is actually like an AND gate because you have X and Y, and when both are only one, you have a blue. Everything else is when only either of them is one, you don't actually have them as blue. So this is like an AND gate. In the case of an AND gate or even an OR gate for that matter, this is linearly separable, right? It's basically as simple as just drawing a line and saying that I can separate my the blue dots from my green dots. So in these cases, essentially, I will not require something really complex. All that I will need is I'll need a simple line to be drawn in between these two sets of points, and that can be solved using a single layer perceptron. Like for example, that can be solved using a simple logistic regression classifier. You don't need complex models to solve problems like these. But take for example the XOR gate, right? So the XOR gate is you have when both are ones or both are zeros, you essentially have the output as ones. Every other time you have a zeros. Like for example, imagine your data looks like this. You have two blue dots and two green dots, and they're in the way they are. Forget about AND gate, OR gate, XOR gate, whatever. If the data looks like this, this is linearly separable. But if your data looks like this is not linearly separable. Right? This data is not linearly separable. And for scenarios like these, is where you need a multi-layer perceptron. And it's basically for scenarios like this. These scenarios require a multi-layer perceptron, because multi-layer perceptrons then will add activation functions. So the moment you add an activation function, then this data, which is basically currently represented in 2 dimensions, might start being represented in a higher dimension, or you can apply a more complex function to start to separate these data points, to start to separate your blue points from your green points. You will probably draw a circle or probably draw some kind of a curve that can separate the blue from the green in some form. Because with simple single layer perceptrons, you're simply drawing a line, and that may not be possible. That may not be enough in most cases. So the point that I'm trying to drive here is that single layer perceptrons are great when you have linearly separable problems. But when you have linearly separable problems, you don't even need a perceptron. I mean, you don't even need to come this far. There are other models, like for example, your simple single layer perceptrons are nothing but your linear logistic regression classifiers. They will do really very well. Linear models or your linear regression models or your logistic regression classifiers, they are good enough to solve problems with when data looks like this. But when data is non-linearly distributed, that's where you require multi-layer perceptrons, because that's where you can add more hidden layers, add more activation functions, and make things a little more, make your model a little more complex. Yeah. So yeah, I mean, that's one of the primary reasons why, of course, your single layer perceptrons that don't really fly as much. That's where you really start to see more and more multi-layer perceptrons being built. Let's take this simple use case, right? And I'll probably give you all a minute to just go through it, and then maybe we can probably discuss about this as we go along. I'll give you all a minute. Just read through this particular problem statement of this particular use case. It's basically as simple as saying, hey, look, right now I have like I essentially I have an e-commerce firm. I have multiple ways of reaching out for my products, and right now I'd want to do that. I want to increase traffic. The end goal is to increase traffic. But then if I were to increase traffic, one of the challenges that I have is I want to do my marketing, but I want to do my marketing via multiple sources, right? Like for example, you can do it via email, direct, paid ads, referral program, social media, or organic search. You can essentially do this marketing via multiple ways. The problem here is that you can either use just one of the platforms for publicity or use a variety of them. You can basically use one of them or many of them. Basically, you can pick whatever. The point, of course, here is that you can right now, everything has its own advantages and disadvantages. Like for example, in the case of paid ads, there's money involved. In the case of referral programs, you have to reach out to existing people. For social media, you need to hire a digital marketing company. For emails, again, you need an email marketing team that can start doing it. So at the end of the day, you want to increase sales, but the thing is, you want to increase sales at the cost of there is some amount of money that you will have to invest into each of these different cases. So at the end of the day, if I were to sort of try and evaluate how much sales am I going to get based on the money that I spent on emails, or money that I spent on direct ads, paid ads, or referral programs, or social media, or organic search, what I need to do is, of course, upfront, I need to start projecting this. I need to make a projection. I need to make a prediction of saying, okay, if I invest X amount of money on email marketing, or if I invest X amount of marketing on paid ads, or if I invest X amount of money on, let's say, referral programs, how much sales am I going to get back? I need to make a prediction like that. I need to start making predictions of the sales that I'm actually going to get as an outcome, because I don't want to invest on everything. I mean, investing on everything is like basically burning money. So I want to invest in such a way that I can maximize my margins or maximize my sales in whichever form or shape. So to do that, one of the most important things that I have to see is I have to evaluate firstly which of these approaches gives me the most amount of benefit. Now, see, by the way, these are not the only ways, right? Each of these is, of course, again going to have its own subcategories. You will have multiple subcategories. You'll have multiple other ways of starting to market towards people. The point that I'm trying to drive here is when you're trying to solve a problem like this, right? If you think of it, it becomes like super difficult for us to sort of predict sales. And at the end of the day, I want to predict sales in this complete problem. I want to predict sales. So it becomes super complex because I have multiple parameters to look at. I have multiple inputs. I have money that is being spent on emails, referral programs, paid ads, direct social media, organic search. I essentially have multiple ways of targeting my customers and multiple ways of multiple ways of targeting my customers and of course driving sales. But at the end of the day, when I would want to solve, if it is, let's say, emails only, or if it is only referral programs only, then based on my historical data, I can tell you how much money to spend on referral program. Or if it is just direct media or direct marketing, or let's say if it is just social media, I can come up with some ways of based on historical information, I can make some kind of prediction using a simple linear regression or something. But when I have so many different parameters coming in and so much of interplay, like for example, your social media might also impact, let's say, your direct marketing, or your direct marketing may impact, let's say, your organic search, or social media may impact your organic search. So you don't know, and there's a lot of interactions that can happen between all of these as well. Like for example, somebody might get an email, but then they might some other time actually start visiting via some kind of an organic search. So there's a lot of interactions that happen between each of these features as well, or each of these inputs as well into predicting sales. So doing these predictions upfront on historical data with simple models is not possible, and that is exactly where we start requiring, the benefit of complex neural networks, or essentially your neural networks where you have multiple hidden layers in between, multi-layer perceptrons. That's essentially where your multi-layer perceptrons and your feed-forward neural networks are going to be coming very, very handy. Single layer perceptrons are good enough for, let's say, a single, when I'm making a prediction of my sales just on the basis of one or two inputs. But when I have multiple inputs, that's where things get very, very challenging. And that's where you require more complex approaches to solve problems. That's where multi-layer perceptrons can become more useful. Yeah. So yeah, before actually, let's talk about your fundamental differences between your multi-layer, single-layer perceptrons and multi-layer perceptrons. We all know this. We don't have to sort of redo this thing time and time again. Single-layer perceptron, of course, no hidden layers. Multi-layer perceptrons have more than one hidden layer. Except for one input layer and one output layer, there is at least one hidden layer. You have one input layer, one output layer, and you have at least one hidden layer in between. That's basically what is referred to as a multi-layer perceptron. Also, and if let's say this one hidden layer becomes, let's say, many hidden layers, 20, 30 hidden layers, that's when we start calling it deep learning models, because your network is like extremely deep. That's when we start calling it, instead of calling it multi-layer perceptrons, we start calling it deep learning models. And by the way, each of these nodes that you see here is a neuron. And when you talk about a neuron, you have multiple inputs coming into the neuron, because if you see, just take this particular circle that you see here, or this particular neuron that you see here, there are multiple inputs coming in. And when multiple inputs come in, what you do firstly an aggregation, and then you apply an activation function, and then you give an output. Same is the case here as well. You have multiple inputs coming in, you run an aggregation, you apply an activation function, then you return an output. So every neuron is doing this. Every neuron is simply nothing but one circle inside your neural network. So every neuron is performing an aggregation and applying an activation function and passing the value to the next layer. So there is some kind of computation that's happening at every neuron, some kind of information that is basically getting generated at every neuron. So think of these as signals. There are signals coming in, and based on multiple signals that are essentially coming in, what you're doing is you're passing a few signals, you're transforming a few signals, you're applying some kind of changes to a few signals, and then creating newer signals. And in combination, all these signals put together again will create another signal. So think of what simple input of signals can actually achieve for us at the end when you run them through a multi-layer perceptron. The point being that multi-layer perceptrons are actually pretty good. That's the point that I'm trying. Yeah, I mean, broadly speaking, this is like the we've already spoken about this. For the sake of the slide, let's just go through this. You have an input layer, hidden layer, output layer, same thing. Yeah, this one point is that here, if you observe in this particular case, there's also a bias that's getting trained, just like your constant. If you observe, the bias term is 1, but the weight is W0. So I'm training W0 because there is no input coming through. The input is always 1. The input is constant. Just I'm training a W0. W0 is nothing but a constant.
So W0 plus W1x1 plus W2x2. So W0 in this particular case becomes like your intercept. So the weight in itself becomes like your intercept or your bias or your constant value, so to say. 1 W0 plus W1x1 plus W2x2 becomes the value in here. Okay. Same here as well. Again, I'm training another bias term in this particular layer as well. Yeah, so this is all straightforward. Yeah, there's nothing really out of the world in here. We all understand this pretty straightforward. So going back to that solution, what is going to happen is that at the end of the day, I want to predict if somebody is going to make a purchase or not. Or I can also predict, I mean, in this case, there are two outputs. You can also predict, let's say, sales. You're predicting if somebody is going to make a sale or not, or make a purchase or not. Or you can also predict, let's say, one single neuron, the amount of sales. So all these go in as inputs, and these inputs essentially will then make one single prediction for you. Which is, let's say, you're predicting the sales or predicting if somebody is going to make a sale or solve it as a regression problem or a classification problem based on the scenario. Here, let's take this another example. Suppose you have the following data set, right? Let's say you want to predict somebody's final results of, if somebody's going to fail or pass. 0 is essentially fail and 1 is basically pass. And I have this information, the amount of hours that somebody has studied and the amount of midterm marks that somebody has achieved. So I want, based on this information, I want to predict if somebody is going to make it through their final term or not. So in this particular case, if you observe, again, based on the input that we have, I have two inputs, are studied and midterm marks, and based on this, I want to predict if somebody is going to actually make it through their final term or not, based on this information. Now, of course, I want to first learn that I want to learn the patterns that basically go through this. Firstly, this is what has happened historically. This is historical information that I see. I've captured this historical data set. But based on this historical information, what I would want to do is, if let's say there's a new kid who's studied for 25 hours and who has scored 70 marks in their midterm, I want to predict if the person is going to, I want to predict what is going to happen to this particular person. Pretty simple. This is a binary class classification problem where I'm trying to train my model on the historical data, and I'm trying to predict on this particular simple data set. That's all that I'm trying to do. Like for example, in this particular case, take this simple example. So what I have is, this is R studied and this is midterm marks. And let's say for whatever maybe the reason, I've decided that I'm going to go with a multi-layer perceptron that looks like this. And I have multiple weights, W1, W2, W3, right? 3 different weights flowing in from different directions. And of course, based on the weights that I have over here, it's not just W1, W2, W3. This is, of course, this is my bias. This is X1 and X2, 2 inputs bias. I'm going to have 1, 2, 3, 4, 5, 6. Essentially, I'm going to have 6 weights in here because I have 2 inputs over here, 3 inputs from here, and then 2 inputs in here. So I essentially will have 6 inputs, 6 weights. And what I'm going to do with these 6 weights is, based on some random values of weights, I'm going to make a prediction to start with. I'm going to start with some random values of weights and I'm going to make a prediction. Let's say the target value is 1 and 0. Let's say I end up making a prediction saying the value is, let's say, the probability of passing is, let's say I make a prediction of 0.4, and let's say I make a prediction of 0.6. The value that somebody would pass, the value that somebody would fail. Probability of somebody would pass is, let's say, 0.4. The probability that somebody would fail is 0.6.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
So whatever may be the reason for that particular student, 35 marks and 67. So if you go back to the historical data, 35 and 67 is the first kid. This person has actually cleared the exam. this person actually cleared the exam. But we made a prediction that from our model, we said that there is a 60% chance that he would clear the exam and 40% or rather 40% chance that he would clear the exam and 60% chance that he would fail the exam. So if you now look at it, there's a collective error that is associated to this particular model. I initially made a prediction. My prediction says that the person is only 40% likely to clear the exam. But if you compute the error, there's an error of around 60, 0.6 error on this node and 0.4 error on this particular node. There's a significant amount of error in my model with my first record in itself. It's just simply this particular data point in itself. So now what do? My challenge right now here is that I made a prediction, but that particular prediction is incorrect. So now what I need to do is I need to perform some kind of a correction to my weights in such a way that my prediction gets corrected. So I can apply some kind of a change to my prediction. So that's change to my weights. So how do I change my weights? I'm going to perform these weight changes based on how much error is being contributed by each of these nodes. Based on how much error each of these nodes is basically contributing, that is the amount of correction that I'm going to make on those weights. So what does that mean? What do I mean by that? So when I say I want to make a correction, like for example, in this particular case, if I'm making a negative, if I'm basically getting a value of 0.4 over here, and if I'm getting a value of 0.6 in this particular node, the reason I have a 0.6 in here could be driven because of one of these three weights. Because I'm getting values from these three places, but one of the weights is significantly high, hence the value in this particular node is extremely high. So I have to reduce this and I have to increase this. For me to do that, I need to basically target that particular weight over here that is causing this value in this node to be very, very high. So I have to perform some kind of a magic over here, such a way that I propagate this error backwards into my network, especially in the direction where in that particular direction which is causing the model to make errors. Yeah, I have to pass that error back in such a way that I pass it back in such a direction which is actually causing that particular error. So that process of propagating the error backwards into the network in the direction of the error causing weight is what is referred to as backpropagation, right? So the backpropagation essentially is there is an error that is at the last layer of my network. What I would want to do is I want to capture that particular error and then propagate that error backwards into my network and see which nodes are causing in that particular order, whichever nodes are causing the higher amount of error, I would want to pass the error backwards into my model. When I pass the error backwards into the model, firstly, I will know which nodes are causing higher amount of errors. Once I know which nodes are causing the higher amount of errors, then accordingly, I will change those weights to basically make sure that the contribution of those particular nodes or those particular weights is minimized in my final outcome. Yeah. So that process is what is referred to as backpropagation and weight updates. Okay. So once I let's say perform that particular step, once I let's say perform the backpropagation and once I do my weight updates, what is going to happen is there is some math that goes on. We'll come to that math in a minute. But there is some amount of mathematics that goes in the background, and what that math basically causes is my errors now start to minimize because I have made some changes to my weights. The weights that were originally W1, W2, W3 or whatever have now become W4, W5, W6 because these are updated weights now. They are not the same weights. So these new weights, now if you observe, they are basically making a prediction that the person is now 80% likely to pass an exam and the person is 20% likely to fail the exam, which is much closer to what it was previously. Previously, we were making a prediction of 0.4% and 40% and 60%. Now we're saying 80% and 20%, which is much closer to reality because in reality, the person has actually cleared the exam. So now if you compute the error, which is 1 minus 0.8 and 0 minus 0.2, so the error is actually much lower than what it was earlier. Earlier it was 60% and minus 40. Now it is 20 and minus 20. So relatively the error has now gone down. But to again still perform the same step, to still make this model more better, what I would do is that I'll again perform the same step. Now I still have the error. I'll again identify which nodes are causing the higher error. So I'll propagate the error backwards and identify which nodes are causing the higher error. Now, until where am I going to propagate this error? Am I just going to propagate the error until the previous layer? No, I'm going to propagate the error all the way until backwards, all the way until the first layer. And then based on which nodes are causing the high error, accordingly, I will change those corresponding weights. Because when I change the weight, automatically the contribution of that particular node becomes smaller. The moment the contribution of that node becomes smaller, uh, automatically what will happen is that it will directly impact my outcome, and that way my outcome will become more closer to reality, more closer to the actual prediction. But what we did to the exactly, so the Prashant, that's exactly where I'm going to come to. What we did to the final to actually update the weights is what we are going to talk about in a minute. I'm just kind of telling you the life cycle of this particular problem, right? So we'll talk about the back propagation right now, right? So I make a prediction, the prediction is incorrect. I want to basically pass this error backwards all the way until the beginning. But how do I do it? Right. So let's take a simple example. Let's not worry about all of this as much. Let's actually talk about, let's take this simple network. Let's start working with the actual data in itself. Okay. So right now what you're seeing in this particular case is you are seeing two inputs. Actually, let me actually copy this, make a simple, just going to paste this here for our reference. So yeah, this is our network, right? These are my trainings. Training data is, let's say, 0.5, and my 0.5, 0.1. 0.5, 0.1 basically meaning the input 1 and input 2 are 0.5 and 0.1. The weights are like how you see here right now, the 0.15, 0.2, 0.25, 0.3. So these are the weights like how you see the way they are right now. And what you also see in this particular case, you also basically see is that the biases are 0.35. That means bias contribution of weights is both 0.35 and 0.35 in both cases. Similarly, 0.6 and 0.6 in both cases. So you have the weights and everything. You have the network. H1, H2 is the hidden layer. O1, O2 is your output. And what you're saying is for an input of 0.05 here and 0.1 here, the actual output should be 0.01 and 0.99. That is what the actual output should be. For 0.05 and 0.1, we want the neural network output to be 0.01 and 0.99. Now, of course, two steps, forward pass and the backward pass. Forward pass is where you actually go through and compute the error and see how bad the model is, or how close it is to the actual predictions, the actual values, and then compute the error and pass that error backwards into the network. So what's going to happen right now? By the way, the other point that I forgotten to mention over here is that the hidden layer has a sigmoid. Let's say we're applying, let's say, a sigmoid activation in the hidden layer. Let's say we're applying some kind of a sigmoid activation in the hidden layer. Okay. So the first one is the forward pass, right? So if you look at the H1, this is why I kind of copied this here. So right now what you observe is here is that you want to compute H1. H1 is nothing but this value. H1 is nothing but, if you observe, it is I1 into W1, because you have a line going from I1 to H1. So I1 W1 plus I2 W2 plus B1. So it's I1 W1, I2 W2 plus B1. That's exactly what we're saying. So I1 W1, I2 W2 plus B1. That's what we're seeing. So I1 W1 plus I2 W2, I1 is 0.15 and W1 is 0.05, I2 is 0.2, sorry, W2 is 0.2 because W2, this line is 0.2, and then the value is 0.1, and then we have B1 which is 0.35, so the value is 0.3775. That's essentially what we get here as H1 output. So the H1 output is 3775 in this particular case. So W1, W2, W3, W4. So these are the values that you see over here. Okay, brilliant. Similarly, this is the value at H1, but mind you, that's not the output at H1. That is the value which is computed, the half of H1 is that. But the output from H1 is going to be a sigmoid transformation. Remember, I'm applying a sigmoid transform. So all that I'm going to do is whatever is the net H1, which is 0.3775, I'm simply going to apply a sigmoid transform. The moment I've applied a sigmoid transform over here, the value simply become 0.59, because 1 by 1 plus e to the power of minus 0.3775, it is 0.59. So the output to H2 carrying out the same process for H2. Similarly, even if you compute the same for H2, if you want to simply do the same for H2, you can actually do it for H2. H2 is going to be same one. So W3 H2 plus, sorry, similarly for H2 you have values coming in from here and here. So it is going to be I1 W3 and I2 W4. So it's going to be I1 W3 and I2 W4 and plus B1, or rather in this case plus B1. It's simply B1 because it's the same value that's going to come through in this case. So if you do the same computation and then you apply the sigmoid transformation, the output of H2 is going to be 0.5968. 0.5932 and 0.5968 are the values from output of H1 and H2. So the values that are going to come out from H1 and H2 are 0.5932 and 0.5968. I hope all of us are clear until here. Are we okay until this point? Superb. Now comes the next step. The next step is another pass. There's another forward pass. The forward pass is where I'm going to pass the value of H1 and H2 and then compute O1 and O2. Great. Let's go ahead. Let's do the same. So if you do this here, net O1, again, so net O1 and out O1, same process. So W5 into O1, W5 into H1 that you see here, and W6 into H2, W6 into out H2, same values. So 0.5932 into 0.4 and 0.45 into 0.59, 0.45 into 0.59 plus B2. This line, you also see this line going through it. So this is B2. B2 is 0.6, 0.6 into 1 because the value is by default 1 here. So you have 1.1, and then you again apply a sigmoid transformation because again, even the outside layer is also a sigmoid transform. This is a classification problem. So the outer layer also is applied, and we are also applying a sigmoid transformation here. So when you perform a sigmoid transformation, again you get a 0.75 at the end. Same for out 2, it is 0.7729. Yeah. So right now, forget about everything else. We are not applying any kind of softmax or anything. We just applied a sigmoid transformation. Forget about doing softmax or anything, just for simplicity purposes. Ideally, what should have happened is we should have applied some kind of a softmax. If it is a classification problem, we should have done some kind of softmax at the end to sum up the values to 1. But that's okay. In this case, we're not doing anything. We're solving it something like a regression problem, so it's okay. Let's not worry too much about it. So you have output 1 and output 2. They are supposed to be 0.01 and 0.99. We've got output 1 as we've got output 1 as 0.75 and output 2 as 0.77. Nowhere close to what they're supposed to be. Nowhere close to what they're ideally supposed to be. So now what do I do next? I made a prediction with the current weights, and mind you, these weights that you see are randomly initialized. They are not initialized with any rocket science. They're randomly initialized. Okay. So now there is an error. Then the error that we are seeing, if you were to compute the error, is, if you observe the error, the way that we are computing this particular error is we are not simply computing a actual minus predicted value. We are doing a mean squared error. Look at this. Mean of the squared error, actual minus predicted whole square divided by 2. So 1 by 2 into actual value minus predicted value. So error at O1 is going to be whatever was predicted at O1. O1 was 0.75. So 0.75 minus 0.01, the whole square divided by 2. We don't care even if there is a 2 or not. There is no 2, it doesn't matter because this is just a constant anyways. So 1 by 2 into 0.01 minus 0.75 the whole square. Similarly, at error at O2 is going to be 0.99 minus I think that was also 0.7513, 0.77. 0.99 minus 0.77 the whole square divided by 2. Same error. And this is 0.27. This is 0.023. This is relatively smaller. The error in this particular case is much smaller because this is for O2 the value is actually much closer than O1. The O2 value was supposed to be 0.99 and we made a prediction of 0.75. So the O2 value is much closer than O1, hence the error contribution via O2 is much smaller than O1. So the overall error is a summation of these two, which is 0.29, right? The overall error in this particular case is 0.2983. Great, wonderful. Now what do I do from here? Now what we do from here is I need to pass this error backwards into my model. So when I say back propagation, I'm not going to literally pass the error back, but what I'm going to do is I'm going to pass this error back in such a way that I'm going to pass it more towards the nodes that are contributing to the error most. So if you go back, firstly, before we move any further, are we okay until this particular point? Are everyone fine until this point? I hope you're all clear with the forward pass. This is where the forward pass ends for one single data point. Okay, brilliant. Now comes the tricky part. So now what I'm going to do is I'm essentially going to find a way to pass this error backwards into my model. Now you tell me, we've been doing all this computation, right? You tell me, between O1 and O2, which is contributing to the error more? Is O1 contributing to the error more or O2 contributing to the error more? Yeah, O1 is contributing to the error more because O1 is much far away from the prediction. O2 is much closer to the prediction. Clearly, see, O2 is 0.023, O1 is 0.27. So O1 is contributing more to the error than O2. So what that means is, whatever correction that I have to make, the correction will have to be primarily in the O1 direction because O2 is okay. O2 also I will have to make a correction, but the correction that I have to make on O2 side is going to be much smaller than the correction that I'm going to make on O1 side. O1 I'll have to make a drastic or rather larger change on the O1 side than on the O2 side. Do all of us agree to it? Super, brilliant. That's the exact mindset that we're going to carry from here. Right now you're able to say that O1 is contributing more error than O2 because the numbers are pretty straightforward for us to understand. The moment I say, okay, now we've decided that O1 is contributing more to the error. So now between H1 and H2, that is contributing values to O1, which of these two is contributing more? Is W5 contributing more error or W6 contributing more error? W6 has a higher weight, but is W6 actually contributing more error? That depends on what are the values of H1 and H2. Because we need to go back and check what are the values of H1 and H2. Because net output of H1 is 0.3775 and net output of H2 is 0.59. Also, the H2 weight is also very, very high. So between W6 and W5, the error contribution by H2 is actually much higher than H1 towards O1. Does that make sense, everyone? So what I will have to do is between W5 and W6, W6 will have to be reduced significantly than W5. Are all of us okay on this? Yeah, I'm going to repeat this. So look at this. So firstly, what is contributing to O1? Not just because the weight is higher. Weight is higher is one of the reasons. Just weight being higher doesn't necessarily mean O1 value is high. Why is O1 high? O1 is high because the weight is high and also the contribution from H2 is also high. If you look at H2 is 0.59 and H1 0.5968 and H1 contribution is 0.5932. So between H1 and H2 is contributing more, and along with H2 contributing more, W6 is also very, very high. So which means that when I multiply the values of W6 with the outcome of H2, O1 is getting more inputs via H2 and W6 rather than just H1 and W5. So technically between these two, W6 is contributing more significantly. So for me, what I will have to do is I cannot directly change H2, but what I can change is I can change W6. So W6 will have to be significantly reduced. I know that for sure. Does that make sense? This is the mindset. Now, for us to individually track each of these weights all the way until the back, imagine how complex it could get. I mean, if you were to manually do it and individually do it, it will be super complex. Yeah, exactly, right. I mean, funny, you're absolutely right. And you're like spot on. So right now it is like just one hidden layer, so I'm able to do it manually. But what if I have, let's say, like 20 hidden layers or 10 hidden layers, and in each hidden layer, if let's say I have like 40 nodes and 20 nodes, then life's going to be like super difficult because I cannot manually track them down. That's exactly where we need to take the help of math, right? That's where we need advanced mathematical concepts. That's exactly where derivatives come into picture. What derivatives and derivatives give you is partial derivatives basically give you the gradient, or rather the contribution of the impact. So when I take the gradient at O1, gradient of error at O1, it will show that the contribution of W6 is much higher than W5. Similarly, when I take the contribution of H1, it will say that W2 contribution is much higher than W1. So the point simply being that when I start taking more and more when I start bringing in concepts of derivatives, and when I start bringing in concepts of computational graphs, things can become much more easier to handle. We can start representing all of this as mathematical equations, and that way things become more easier. Computationally, they become easier, not from an understanding standpoint. Understanding standpoint, things become a little more complex for us. But computationally, things become easier. Let's actually look at it. Let's actually look at what we are doing here. Cool. So I just hope before we get into the actual math, I just want your intuition to be at the right place. Intuitively speaking, we are going to go back and correct those weights which are contributing higher. That's the sole purpose of this exercise. I hope all of us are on the same page here until this particular point. Brilliant. Okay, so let's get to the actual stuff. Now, we've computed the complete error. Now comes the actual part. So let's take this O1. Let's take O1. There's an overall error. This is basically an enlarged diagram. So the diagram that you see in this slide is essentially an enlarged diagram of the O1 neuron that you see here. So if you see, there is a total amount of error, and that error is contributed by firstly O1, and O1 is basically contributed by net O1, because net O1 is simply nothing but, again, which is contributed by W5, W6 and B2. Right? So if you think of it, what is causing what? If E is high because O1 is high. O1 is high because net 1 is high. Net 1 is high because net of O1 is high because either W5 or W6 or B2, one of these is high. So I have to start tracking back what is causing this error, and that's essentially what backward pass is going to be all about. So the way that I'm going to look at it is, at the end what I want is, I basically want, how much is E, what is the rate of change of error with respect to first W5, what is the rate of change of error with respect to W6, and what is the rate of change of error with respect to B2. Yeah. So what I want to understand is, between W5, W6 and B2, I want to understand what is the rate of change of error. When I say rate of change of error, that means which of these weights is actually contributing the highest. Okay. So when I say rate of change of error, it's typically represented by a derivative. So what I'm saying is that I want, in a lot of ways, what I am essentially asking for is, I'm basically saying, so we've computed an error over here, right? So this error term, I want to compute, so D or dou doesn't matter. Dou is basically a partial derivative because there are multiple things that are coming through. I cannot make a complete derivative. So I'm going to simply say dou E by dou W5 is what I want to compute. Similarly, dou E by dou W6 and dou E by dou B2. So the error contributed by W5, error contributed by W6. Let's for the moment, let's not worry about this too much. The computation of this is very similar to the other one. I want to compute dou E by dou W5 and dou E by dou W6. But you have to remember something, that if you look at that diagram previously in the previous slide, dou E by dou W5, if I have to compute dou E by dou W5, I cannot compute it directly. So the way I'm going to compute it is A is first directly dependent on O1. So what I'm going to do is I'm going to make use of a concept called as chain rule in differentiation. Simply put, what I'm saying is that dou E by dou W5, or the rate of change of error with respect to the W5 weight, is nothing but rate of change of error firstly with respect to output of O1. So I'm going to say simply out O1 multiplied by rate of change of error at output O1, rate of change of output O1 with respect to net O1, because this is changing as a dependent of net O1. I hope you all understand what is the difference between net O1 and output O1. Net O1 is simply a summation. Output O1 is the sigmoid transformation. Okay, I hope you all understand the difference between net O1 and output O1. Yeah. Okay. So then this is going to be dou output O1 divided by dou net O1, similarly multiplied by dou net O1, or rather dou net O1 by dou 5. Dou net O1 divided by dou W5. That's essentially how I represented the whole thing. This is basically from a concept called as chain rule in mathematics, in differentiation, partial differentiation. If you're not fully aware, it's okay. All that I'm simply saying is that, hey, look, I want to compute how badly the error is being contributed by W5. Similarly, I want to compute how error is being contributed by W6. But how do I do that? The best way of doing it is I compute dou E by dou output O1, dou output O1 by dou net O1. So I want to identify how output is getting contributed by net O1. Then again, similarly, how net O1 is being contributed by W5, or how net O1 is being impacted by W5. And when I multiply all of that, I'm going to get how dou E is getting, or rather how my total error is getting impacted by W5. That is what this is simply going to be. Similarly, I'm going to do the same thing for dou E by dou W6 as well. So if I were to put it into actual math, this is how it's going to look like. So don't get terrorized by it. It's not very difficult. It's the same thing. So dou E total by dou out O1, dou out O1 by dou net O1, dou net O1 by dou W5. Same exact thing that we just did. This is the same exact equation that we kind of put together over here. Nothing very complex. So we are simply calculating the rate of change of error with respect to change in W5. So when W5 changes, how much does the error change is what I'm trying to compute. Because if I know that if W5 is contributing heavily, then I will change W5 more. If I see that change in W6 is contributing heavily to the outcome, then I will change W6 heavily. So to make that decision, which one has to be changed with how much, I first have to identify which one is contributing how much. And that's what I'm currently doing right now. I'm just trying to firstly compute how much is the error being implemented. So now here is where I'm going to start computing each of these terms. So firstly, dou E total by dou output O1. For that, what we need to start doing.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
I'm going to start computing each of them separately. So firstly, how do I compute my error? How do I compute my error? It is 1 by 2 into the actual values, whatever my actual values were in the previous case, which is nothing but, okay, target O1, let's call it target O1, minus the whatever my predicted O1 was. Predicted O1 is simply nothing but output O1, the whole square, plus 1 by 2 into target O2 minus output of O2, the whole square. Guys, this is exactly the same as, computing the error here and computing the error. I just put the equation together. Earlier, this is how we computed the error. So now what I'm saying is I'm going to compute dou E by dou output O1. I just have to partial differentiate this whole thing with respect to this. That means everything else will remain constant. So basically this term will simply vanish because target O2 and output O2 are, I'm assuming these are constant. So this whole thing will vanish. This whole thing will become 0. And I have to simply do a partial derivative over here. So 1 by 2. So 2 by 2 is what it is going to become into target O1 minus output of O1. And this will simply get cancelled. And I have to differentiate this one. And that will be minus 1. So simply put, minus 1 of target O1 minus output O1 is what is going to simply be. So that's as simple as that. Minus of target O1 minus output O1. That's what this is, as simple as that. Okay. And I simply substitute the values and I can't compute what that one is. Target O1, I know what the value is, and output O1, I know what the value is. I can simply compute what that is. That way I've completed dou E total by dou output O1. So I've computed this one. This one is complete. Now I need to compute this one. Okay, brilliant. So let's move forward. I think, yeah, see, look, I understand, Funny. I mean, you're absolutely right that we need folks to understand partial differentiation, but that's okay. If you don't understand partial differentiation, it's fine. The focus is not to kind of understand understand step-by-step math. The focus is for you to intuitively understand what we're trying to do here. So that's the reason when I make a computation here, just understand what I'm trying to do there. What I'm trying to do is I'm simply trying to compute the rate of change of error. So probably you understand Funny, but the others probably might not everyone might understand, and you're absolutely right. So if there's anyone who doesn't understand partial differentiation, it's okay. But yeah, just try and get the hang of what we're trying to do here. Yeah, and if you're unable to understand, please do ask. I'll be happy to explain. Okay, so let's get to the second one. So the second one is dou output O1 by dou net O1. So for me to firstly compute this differentiation, the first thing that I have to do is I have to first understand how output O1 is being computed. How am I getting output O1? Anyone? If you go back and see, firstly, the output O1 equation is simply nothing but a sigmoid transform. If you go back and check the this one, see, output O1 is a sigmoid transformation of net O1. It's exactly a sigmoid transformation of net O1. So let's go back. This is going to be simply 1 by 1 plus e to the power of minus net O1. That's essentially what output O1 is. So now I have to differentiate output O1. So dou output O1 by dou net O1 is going to be a partial differentiation of this whole thing. So when you do a partial differentiation of this thing, especially your sigmoid transforms, there is a pretty straightforward way of doing a sigmoid transform. So sigmoid, sigmoid into 1 minus sigmoid. Basically, that is what your sigmoid differentiation of sigmoid transformation. Let's say you have a sigmoid of x, and you want to compute a differentiation of this. It's as simple as sigmoid of x into 1 minus sigmoid of x. That's essentially what the output is typically going to be. So partial differentiation is going to be. Okay. And I think to compute something like that, as you observe here, it's the same thing. So output O1 into 1 minus output O1. You simply do a output O1 into 1 minus output O1, which is basically a sigmoid into 1 minus sigmoid. And then when you compute, you're going to get basically a value for your net O1, your dou output O1 by dou net O1. That will be basically a second term. So this term is also done. This is going to be output O1 into 1 minus output O1. When you do the actual partial differentiation, you're going to get output O1 into 1 minus output O1. So two terms are done. The last term is net output O1 with respect to W5. So if you see how net output O1 is getting computed, which is nothing but, W5 into H5 plus W6 into, I think, W5 H5. Oh, sorry. When I say H5, what I mean is H2. Let's go back one step. So W5 into H2 plus W6 output H2 plus W6 into output H1. W5 into, this is going to be output H2, W6 into output H1 plus B2. That's what your net output O1 is. So net dou output O1 by dou W5. Again, when you see a dou W5, this is going to get cancelled, this will all get cancelled. What you will simply be left with in this particular case is going to be simply output of H2. That is all that you're going to be left with in this particular case, because everything else simply gets cancelled because you're doing a partial differentiation with respect to W5. And that value is as simple as this one, output H1, which is 0.5932. So that's basically a third term. Once you have all these three terms, then you can simply do a multiplication of these three terms and you'll get a simple value out of this. This, my dear friends, is just dou E total by dou W5. Dou E total by simply dou W5. Similarly, you'll have to do dou E total by dou W6, dou W7, dou W8. For all the errors, basically W6, W5, W6, W7, W8, you'll have to basically do an error correction for all these four weights to start with, right? So you have to do the you'll basically have to compute how much each of these are weighting contributing to the outcome, contributing to your error. Once you know how much they're contributing to the error, now you go back and you try and correct your actual values. Now you go back and you correct your actual weights. So the way you go back and correct your actual weights, before I move forward with the actual correction of the weights or updation of the weights, are there any questions here? Yeah, I mean, I was just expecting these questions about, do I really need to learn the math? I mean, the choice is yours, guys. I mean, the choice really depends on you folks. At the end of the day, you're not going to do any of this math with hand for sure. Let me tell you that. Nobody is going to question you on any of this math in any of your interviews. Trust me, because if somebody is questioned on the math, firstly, the interviewer is it's quite likely that the interviewer probably will not be able to pen this down in the interview itself. So the intention is not for you to learn the math. Please, you don't have to learn the math, and don't fret about trying to mug this up or trying to actually master this. What you really need to understand is just understand how we are solving the problem and what it takes to actually solve a deep learning problem. Right? Given an axe, anybody can knock down a tree. But what we're learning is what it takes to actually solve it the more structured way. Given a TensorFlow algorithm, TensorFlow framework, and a couple of functions, anybody can put a neural network together. That's not the point of this whole session at all, and that's not the point of this learning process at all. So I mean, if that was one of the expectations, then we will get there. We will get to that in a couple of classes. But what we are going with, before we go there, we're simply trying to master, the fundamentals of trying to solve a deep learning problem. At the end of the day, you are not going to do any of this. At the end of the day, you are not going to make any of these updates or whatever. You just have to understand that, hey, look, there's a weight update that's happening. Hey, look, in this particular step, there is an error computation that's happening. That's all that you need to know. But to really master a deep learning algorithm, if you really need to tune the deep learning algorithm, you really need to understand these fundamentals, because You need to know which error, what weights are contributing. You need to know what nodes are dead nodes. Suddenly what you will realize is that your network just doesn't seem to learn anything, because there are certain neurons which are simply dead because of the activation functions that you've used. Everything is simply returning zeros, and there is no learning that is happening. There is, when your back propagation is happening, nothing's learning through the process. Everything is simply dying. So you should be able to go back and say that, hey, look, my errors are being my error is very high because the neurons are dead. And the neurons are dead is because the activation function that I've used is incorrect. So I have to change that, and then everything else would get corrected. That's essentially what you need to do, and for that you need to understand the math. So I'm not saying you need to learn the math, but just try and understand the math. That's all that we're saying. Just put some step towards learning. It was like in my master's degree, when I was actually solving for my when I was doing my data science course for my master's, the deep learning back propagation was like a guaranteed question in our semester paper, and we all had like I think the question was for like around 8 marks or so. So yeah, I mean, no wonder it's like it's definitely not a 12th grade question, but yeah, it's definitely worth 7 or 8 marks. Just kidding, but yeah, that's the fact. So Tom, yeah. So what dou E W by dou E total by dou W5, what it simply says is, it basically tells me the rate of change of error with respect to change in W5. So simply put, if I change W5 a little, how much is it impacting my error? Is it significantly impacting my error, or is it positively impacting my error, or negatively impacting my error? So for me to understand that, firstly, if this value is positive, what it basically says that, okay, a change in W5 means there's a positive impact in error. So if I change error W5 a little, that means the error is getting impacted by 0.082 times. Assume it that way. We can think of it that way. Yeah. Every unit increase in W5 is increasing, let's say, your error by, let's say, 0.082 units. Think of it that way. So what that would help me achieve is that, firstly, it will give me a magnitude of how much my error is being contributed by the W5. Similarly, how much my error is being contributed by W6, 7. So if you see here, in this particular case, W5 is basically contributing by 0.082. Similarly, W6 and W7, W8, W9 must be contributing in whatever forms or shapes. Based on that, what I'm going to do is I'm going to update my weight. So what I'm now doing is I'm saying my new W5 is what is nothing but my current value of W5, whatever the current value of W5 is. What is my current value of W5? My current value of W5 is 0.4. So current value of W5 minus whatever this particular value is, whatever this gradient is. So I'm saying, because this is positively impacting, what I'm going to do is I'm going to reduce this a little. How much do I reduce it by? I'm going to reduce it by the gradient, whatever this particular gradient is. N is a small multiplier. Think of N as a very, very small multiplier. Let's not worry too much about N right now. N is like we call N as learning rate. So what N basically does is N sort of tries to shrink the impact. So don't worry too much about N right now. We'll talk about N later on. Simply put, what I'm doing right now is I'm just trying to because this has a positive impact on my error. W5 has a positive impact on my error. That fact is established with a very high value here. So now what I'm going to do is, okay, because the error is heavily contributed by W5, so I'm going to reduce W5 a little. So if I reduce W5 a little, I will expect my error to get reduced. So that's what I'm doing over here. So I'm reducing W5 by the gradient in itself. I don't know how much to reduce it by. I can reduce it by some random number, but instead of reducing it by some random number, I'm reducing it by some particular value which I've already computed. I'm saying, okay, just use the same value and then reduce my W5 by that much. So now my new W5 is 0.3589. So moving forward, use this as my new W5. So instead of 0.4, which was originally, now use 0.35 as my new W5. Similarly, the same with W6 as well. W7, W8. I'm going to change all my values from what they originally were. So for example, W6 originally was 0.45. Now I've made it 0.40. W7 was originally 0.50. Now I made it 0.51. Because if you see W7, I've increased W7 and increased W8. I've reduced W6 and W5. By doing so, what I am essentially doing is I am trying to tweak values in such a way that my output is much closer to what I actually want it to be. Ashok, as I said, ignore n for now. Don't worry about n. Assume n as some random number for now. N is like a constant value. Forget about n. We will come back to n later on. I'll talk about n later on. N is simply called as a learning rate. Larger the value of n, faster it becomes. So we'll talk about learning rate later on in more detail. But simply put, just understand that currently this is how we are updating our weights. Is everyone okay until this point? Are we fine until here? Do you all understand how the weights are being changed? Okay, good. Cool. Okay. So far so good. Lot of math going on in here. But yeah, basically just like how we've kind of updated 5, 6, 7, 8. Similarly, we will have to do something very similar with W1 and W2 as well. Similarly, dou E total by dou W1. Just like how I've computed dou E total by dou W5, I will do dou E total by dou W1 and dou E total by. Similarly, it's the same thing, but multiple components in here, right? That way, what will happen is right now, all my values will simply get updated. All my weights, not the I1, I2 value, they will remain constant, but my weights will now get updated. With the new value of weights, ignore all of this. So this is W1, W2, W3, W4. They are also now updated. With the new value of weights now, I'm going to go back and rebuild my model. So basically, these are my new weights. W1 is now 0.14. W1 is instead of 0.15, it is now 0.14. Similarly, W2 is 0.19. W2 is 0.19. W3 is 0.24. 0.24. And this is 0.29. W4 is 0.29. So all the weights have reduced a little. What if we have to increase it for reducing the error? Yeah, I mean, see, if you see that all W1 to W4, all the weights have reduced. But if you comments look for W5 to W8, look for W5. W5 has reduced, W6 has reduced, but look at W7 and W8. W7 is 0.51. W7 was 0.50 earlier. And W8 is 0.56. W8 was 0.55 previously. So W7 and W8 have actually increased. Does that make sense? So it's not always the case that everything is reducing. These are reducing, these two have reduced, these two have increased. Again, Chetan, this is the third time I'm repeating. N is a random value. For now, ignore n. N, just assume n as a constant value. N is called as a learning rate. We will come back to n later on. Don't worry about n for now. So last but not the least, of course, now that the errors have now all these values have now been updated. So now what would you expect? You computed an error, and based on the error, you updated the weights now. So now you're going to run through the model. You're going to run the forward pass again. So when you run the forward pass again, what would you expect? Would you expect the error to be high or low? Error to be reduced. Absolutely right. So with the updated weights, when you run your forward pass again, previously the forward pass gave us an error of around 0.2983, but with the updated, after the first round of back propagation, the total error now has become 0.2910. It has become 0.2983 to 2910. Now you may ask me, dude, this is not a significant reduction. Absolutely yes, this is not at all a significant reduction. But if I run this 100 times, but if let's say I run this 1,000 times, do you think the error will then significantly reduce? Absolutely yes. If you run the same process 100 times or 1,000 times, the error will then significantly reduce. So point being, when you run multiple forward pass and back propagation steps, that means your model is basically learning continuously, learning and updating weights, learning and updating weights, learning and updating weights. When this continuously happens, what happens is that almost after around 10,000 times, the error almost drops to around 0.40354 or 50, I don't know, 4 zeros almost 0.4035. It's almost as close as to zero, right? So when you run this like 1,000 times, 10,000 times, that's where things become much closer. Things get much closer to your actual predictions. Great question, Deepak. How much time will it take to run 1,000 predictions, 1,000 more times? If you implement it with simple Python, with simple data, like this example, this small example will probably take a few milliseconds, probably a few seconds, maybe 3-4 seconds maybe, to run it 1,000 times or 10,000 times. But imagine you had, let's say, instead of one data point, imagine you had, let's say, 1,000 data points or 100,000 data points, and your network had like 20 layers, and your each layer had like, let's say, 30 neurons. Then in that case, training that could take anywhere between a few hours to probably even a day at times, depending on the infrastructure that you have, depending upon the data that you have, depending upon the size of the algorithm. Training a deep learning algorithm can take anywhere between a few hours to a couple of days. And if you have, let's say, the compute you have, let's say, for example, instead of using a CPU, if you have a GPU compute, that means if you have a graphic card in the system, and if you instead of using regular TensorFlow, if you start using TensorFlow GPU version, then things can be much faster. You can accelerate things a little more. So that triggers us into a different line of conversation altogether. But the point being that deep learning is a time-taking affair. It's not something that's going to happen in like a jiffy, like a decision tree classifier. So yeah, cool. So we computed dou E by dou W5, dou E by dou W6, dou E by dou W7, and dou E by dou W8. So this is nothing but rate of change of error with respect to each weight in last layer. This is all in the last layer, right? Basically, rate of change of error with respect to each weight in the last layer. Now, once you compute all of this, this is just a part of the process, part of the problem solved. Now I need to update my weights. So now is the next step, where I am going to do the update weight. So for example, what I'm going to do is, let's take, for example, I have weight 5. The new value of weight 5, I'm just going to call it plus, just for notation purposes. The new weight 5 is going to be the old weight 5 minus some value. I just put a minus over here for sign purposes. Essentially, what I'm doing is I'm subtracting a particular value from the previous weight. Now, what will this value be? This value is going to be dependent on the gradient that we computed. So these are all nothing but these are all called as gradients, or in very rudimentary terms, these also can be referred to as slopes. Higher the gradient means more contribution of that particular weight towards the error, right? So higher the gradient means more contribution of that weight towards the error. Lower the gradient, negative gradient, means that weight negatively impacts the error. That means the error is going to be lower with that particular weight. So if, for example, if there is a positive gradient, if the gradient is positive, I'm going to simply put a positive value over here, so that what will happen is I'm going to reduce that particular weight, because this will be a positive value. So let me just remove this. So the current W5 minus a positive value, hence my new W5 is typically going to be lesser than the old W5. So that way, what I'm doing is, because dou E by dou W5 is a large value, I'm reducing W5. On the other hand, let's assume, for example, dou E by dou W7 is actually a negative value. What do you mean by a negative value? Negative value simply means that the weight W7, an increase in W7 is reducing your error. So I want more of W7 because more of W7 means less of error. So if I want more of W7, and if this is a negative value, I'm going to substitute, put this negative value as it is in here. So if this is a negative value as it is, negative of negative will become positive. So my W7 in that case is going to look like this, W7 minus of a negative value. So minus of negative value is going to become a positive value. So my W7 is going to go up, my W5 will come down. That way, I'm adjusting my weights based on the gradients that I've computed. So simply speaking, what I can actually do is instead of sort of putting some random value, what I can actually do is I can just simply put dou E by dou W5, dou E by dou W7, and so on and so forth. I can simply substitute it by the gradient. So my weight update is simply nothing but, or my new weight is simply nothing but my old weight minus, or the current weight minus the gradient contribution of that particular weight. Now, the thing is, of course, that if I directly put this value, at times we don't know how large or how small this number is going to be. So what people generally do is they generally scale these values down. They say that, okay, don't use the direct value, multiply it by some large value, but multiply it by a smaller value, right? So sorry, multiply it with a slightly smaller value. We call this as eta. If you remember, you saw this as n earlier. The science behind using this is that this is simply called as a learning rate, and this value is typically between 0 and 1. It's a small value. So what you do with that is, because this, we don't know how large or how big this particular value is going to be. So what this will do is basically scale this value down, scale the gradient down. That way, what will happen is the weight updations are not going to be extremely erratic. The weight updations, this is a simple multiplier. That way, it'll help me scale down the value a little so that my weight updations are not going to be significant. So you basically take baby steps rather than just making one large update. You make smaller updates slowly so that you don't make any large erratic movements in your weight updates. That's it. So what has happened right now is I've computed the error and then I've updated my weight. So now that I have my new weight, what do I do? So in the previous thing, going back here, now W5 and W6, W7, W8. So now all W5, 6, 7, 8 have been updated from 0.4, 0.45, 0.5, 0.55 to some new values. Similarly, W1, W2, W3, W4 will also be updated because I need to perform backward prop even for them. And I need to update those weights as well. Once all these weights are now updated, I have the same network, but with different weights now. Now what do? I again run the forward pass with these values. Now when I run the forward pass, that is basically computing all the O1 and O2 values, then I would see again recompute the error. This time I would ideally expect the error to be reduced. The reason why the error would reduce is, of course, because we have updated the weights in the directions of a lower error. So that's where the error is likely to reduce. And this process is going to continue until, of course, you get to a particular point where the error is as minimal as possible. I wouldn't say zero, but as minimal as possible at least. Okay. So basically what's going to happen is that if you do not have the eta, it's not n actually. Actually, it is represented by a Greek letter, either an eta or an alpha or other terms. In certain cases, it is also simply represented with other constant. But yeah, just for lack of a better term, in our case, it is represented by as an n. In our slides, it is represented as n. So doesn't matter, whatever works. So the learning rate, it is also referred to as learning rate or a step size or shrinkage. Different terms to the same thing, everything mean one and the same. If you ever implemented gradient boosting machines, one of the parameters that you will have is a learning rate or a shrinkage. You will definitely have this as one of the hyperparameters in gradient boosting machines.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
So it's the same thing here as well. What you're doing here is, and or if you implemented linear regression using Python, even there you would have something like this. Anyways, long story short, what this eta essentially here is doing is that it is trying to control the update, right? It is trying to control this particular update step. At times, what may happen is based on the numbers that you have, the dou e by dou w5 or dou e by dou w7. See, this particular derivative, this partial derivative or this gradient could be extremely large values, right? It could be very, very high values. So to control those large, if this is a very large value, then what will happen if without the eta, w5 minus that large value, what that might do is it might actually make a huge update to the weights, right? It'll apply a huge update to the weights, and applying a huge update to the weights could have its own challenges. Like for example, when you update a lot of weights at the lot of updates at the same time, the updates of all the weights might actually counterbalance each other, and they may actually start having negative impacts on your complete model. We'll talk about that, about why that could happen in some time. But in short, what may happen is large values of etas could essentially have a negative impact. I mean, large values of the gradients or large update steps might actually have negative impacts on the model, because your model error might actually start increasing. Because if this is a very large number, then when you subtract the error, subtract that particular large value from the weight, instead of actually reducing the weight, you might have actually reduced the weight so much that now the weight is contributing again positively to the error. So you want to basically control the way you're updating the weights. You don't want large updates to happen at the same time. You want baby steps, and that way eta will help control those large updates. Eta will simply be a value between 1, 0 and 1 that you will set at the beginning, and that will control the updates of your model weight updates. Do we have to pass any limit of error that at least we need less than this? No, so that's not how it works. Again, it's very similar to, guys, again, it's very similar to how you would train any classification or a regression model, right? How would you train a classification or regression model? You would have a certain level of error in your mind, and you will keep training until you hit that particular error, right? So you will keep training until you hit a level of precision or recall or whatever. Similarly here as well, you will keep training until the error goes down. Now, whatever that error is, you can measure that error in terms of recall, precision, or whatever, or you can measure that error in terms of log loss or any of the other errors. Just like training any other model, nothing new to this. Okay, let's go back. So once you basically train once you run your backward pass and you update all your steps, you update all your weights, what is likely to happen is that, of course, the error that of course was like around 0.29 at the beginning, 0.29 at the beginning almost plummets to around 0.4035 after 10,000 steps, because at the beginning it was around 0.2983. After the first update, it has come down to 0.2910. It has definitely decreased, but the reduction doesn't seem very large. But that's okay, because you don't just do this once or twice. You do it like hundreds of times until the error goes down significantly. So once you hit a certain error that you're comfortable with, then on that particular point you stop the model training, and then you say that, okay, this is after these many number of iterations, my model is able to do well, and you stop there. How do we know the target error? What do you mean by target error, Naresh? I mean, see, when you're training a classification model, do you know what should be the best error? Do you know how much precision or recall do you want at the beginning? You would never know, right? It's as simple as that. I mean, you're training a classification model or a regression model. It's as simple as that. So you train the model, you try and compute the precision or recall. If you're happy with the precision or recall, then you go ahead. Else, you don't. So just like how you train a classification or a regression model, you would train this particular model as well. Yeah, correct. Cool. Okay. Looks like everybody's comfortable until this particular point. So let's move on.
Great. Now comes the point of, okay, this is all great with pen and paper. Right now, until this particular point, we've been training this model with pen and paper. It's wonderful that we've been able to train this with pen and paper, but how do I actually implement this, right? How do I get this up and running with regards to, these, if for example, if I have to keep updating each of these weights continuously, then that's like a huge problem, right? Because then if I have 10,000 weights, then computing a derivative for 10,000 weights, then again identifying how much to update it by, all of this could become very, very challenging. So that's exactly where, instead of manually trying to update each of these weights, what we instead do is we start to leverage techniques like we start to leverage optimization techniques, like for example a gradient descent, or there are a couple of other algorithms that are there which can basically help us perform these weight updates very, very quickly. So for example, right now the weight updates that we are doing over here, the math will remain the same. Whatever we are doing is exactly gradient descent in a way, but from an implementation standpoint it becomes much easier. So we'll just try and understand what gradient descent is. You will just realize that whatever we've been doing until this particular point is already gradient descent, right? So a gradient descent, again, as I said, is one of the most popular optimization strategy used in ML. It is used basically while training your model, and what it helps us do is it helps us do your weight updations. So basically gradient means higher the gradient, the steeper the slope, and the faster the model learns. So let's try and understand what we really mean by a gradient descent. So let's go back to the, if you have, let's say, a linear regression model, y is equal to mx plus c sort of a line, or instead of mx plus c, for y is equal to beta naught plus beta 1 times x sort of a model. In this particular case, what you have is that if you train this particular model, there are two parameters that you will have to, of course, figure out. One is beta naught and the other is beta 1. And between beta naught and beta 1, we have to identify the best possible value in such a way that the error is the lowest. So when you say error, what is error? Error is nothing but your mean squared error, right? 1 by 2 or 1 by n into summation of your actual values minus your predicted values, the whole square. So I is equal to 1 to n. If you have n data points, for each data point you compute the actual value and you compute the predicted value and you take a square. As simple as that. Or simply put 1 by n into summation of actual values. Predicted value is simply nothing but beta naught plus beta 1 times x, the whole square. And I told you that this error term, if you think of it, how in this particular equation my unknowns are beta naught and beta 1 are my unknowns. So I need to find the best possible values of beta naught and beta 1 where my error is minimum. I need to minimize this whole equation because I want the lowest possible error. So I want the best possible values of beta naught and beta 1 in such a way that my error is the minimum most. If you sort of think of this, it's the same thing that we are doing here as well. Instead of beta naught and beta 1, in this case, we are computing something else. Instead of beta naught and beta 1, we are computing W1, W2, W3, W4, W5. In this particular scenario, I'm computing W1, W2, W3, W4, W5. The error is the same concept, the actual minus predicted value, the whole square, same error term. So what we did from here, if you remember, was we did something very similar. We said we'll compute the derivatives and equate to 0, dou e by dou beta 1 equal to 0. You compute the derivatives and you would equate it to 0, and then you'll get two equations, and you'll basically have to solve two simultaneous equations to compute the best possible values of beta naught and beta 1. What your gradient descent does is it tries to solve this particular problem, this optimization problem. This is an optimization problem, right? Because I want these parameters or the best possible values of these parameters such that my error is the minimum most. When you solve the optimization problems, we call this as an objective function, and the activity that I want to do is minimization. So my objective function is this error, and the minimization is what I want to have perform over here. So here comes one way to solve it is using direct derivatives, and the other way of solving it is using gradient descent, which is an optimization algorithm. What gradient descent tries to do is, again, if you remember this particular equation, if you think of it, it basically looks like a bowl. This is because this is of a parabolic form. Think of it as this is a second degree polynomial in beta naught and beta 1. Hence, this basically looks like this looks like a bowl. So you have beta naught, you have beta 1, and then you have error on this particular axis. So I basically want to find those corresponding values of beta naught and beta 1 on this axis and this axis respectively, such a way that the error is the minimum most. That means I basically want this corresponding value of beta naught and this corresponding value of beta 1, where my error is basically 0. So I want this possible value of beta naught and this possible value of beta 1. So such that the error is the lowest, because at this particular point is where the error is the lowest. Okay. I hope that sort of makes sense to everyone. Are we okay until this particular point? Is everyone fine until here? Cool. Okay. Now, cool. Okay. So I'm going to move forward. We haven't still spoken about how it would reduce the error. I'm still saying that particular scenario which I would desire. I mean, I still haven't told you how to get to a point where the error will be lowest. I want those particular values of beta naught and beta 1, because at this particular value of beta naught and beta 1, my error is going to be the lowest, because this is where, if you think of it, think of your bowl. Across my y-axis, I want the lowest point. The lowest point is nothing but the bottommost point of my bowl. So I want that particular point, or the base of my bowl, because that's where the error is lowest. Right? Think of it in 3 dimensions. So the way for you to kind of assume this is, if let's say I represent the same thing in 2 dimensions, it will make it easier. So what I'm simply going to do is I'm simply going to make this into 2 dimensions. Imagine you're solving for y is equal to beta naught times x. You're not solving for, let's say, the full equation. Let's say you're simply solving for beta naught times x, and your error is going to be 1 by n into summation of actual values minus beta naught times x the whole square, right? So this is basically going to look like this. This is simply going to be because I do not have multiple parameters, I just have beta naught and I have error. This will essentially look like this. So I have error and I have beta naught, and this is basically how my error function is typically going to look like, because this is a parabola. This is a simple parabolic form. Cool. Again, I want the lowest possible error. Where is the lowest possible error at this particular point? So I want the corresponding beta naught value. I want this beta naught value, but I don't know what that beta naught value is. I want to compute. I intend to compute that particular beta naught value. So how do you do that? So the best way to do it is you start with a random beta value. You start with a completely random beta naught value. Let's go with a random beta naught value. So let's say you start with a beta naught value that's over here. So at this particular point, you're simply going to come here. You start with a random beta naught value, whatever this beta naught value is, you start here. That particular beta naught value, when you substitute here, you're going to get a corresponding error. When you substitute that particular beta naught value, that beta naught value is going to yield a certain error. In this case, is the error high or low? In this particular case, is the error high or low? The error is very high, relative. In this particular case, the error is high, guys. Beta naught value may be low, but the error is high. So now the question is, I want to change, I wish to update my beta naught value. I want to update my beta naught value from whatever the current beta naught value is with some kind of a term. I don't know what that term is, so that I get closer to lower error. I want to get closer to the lower amount of error. How do I do that? So the best way of doing that is I compute the gradient at this particular point. And I compute the gradient. So what do you mean by gradient? Remember, gradient is simply nothing but the slope. Dou E by dou beta naught. I simply compute the error or the gradient at this particular point, dou E by dou beta naught. When I compute the gradient, I'm essentially going to get the slope of this particular equation, or slope of this particular equation at that particular point. Slope of the tangent is what we call it, or simply the slope of that particular equation. So if you observe in this particular case, the best way of also trying to imagine it is if you kind of think of this particular line. This line simply looks like that. The slope is nothing but this particular angle, the cosine of that particular angle, sorry, the tan of that particular angle. Trigonometric ratios, trigonometric components. So whatever this particular angle is, tan of that particular angle is what is referred to as slope, or also simply put as beta naught changes, as beta naught increases, your error in this particular case is negatively increasing because it is increasing. Your error seems to be increasing, right? So in this particular case, so your beta over here, the slope in this particular case is a negative slope. If you compute simply, it is a negative slope. They call it as a negative slope. On the other side, if for example, in this particular case, if you compute, the slope is a positive slope. So simple 10th standard mathematics, guys, nothing really complex over here. Or simply put, if the angle is between 0 to 90, the slope is positive. If the angle is greater than 90, the slope is negative, or this particular value will return a negative value. So in this particular case, this will return a negative value. So what we can do is now I wish to update this particular weight. So the way I can update this weight is I can simply say that, hey, look, your new beta naught value, or your new beta naught value is going to be a current beta naught value minus the slope, dou e by dou beta naught. And remember, this is a negative value. Your beta naught is dou e by dou beta naught currently is a negative value because you're on this side, negative slope. If this is a negative value, what will happen to your new beta naught value? Your beta naught is equal to beta naught minus of a minus value. So your beta naught, is it going to move to the left or to the right? Your beta naught is simply going to increase, right? So your beta naught is going to increase. So is it going to move to the left or to the right? The your new beta naught will move to the left or right? Absolutely, yes, it will move towards the right side. So now what has happened is originally your beta naught was here, but now your beta naught was here at this particular point. Right now it has moved from, let's say, here to here. This is your new beta naught value now. At this particular point, if you compute the error, look at the error. The error is over here right now. Is the error lesser or higher? The error is much lesser than what it was earlier. So you moved from here to this particular step. You moved through that particular curve and you've come here right now. What do you do again here? You again compute the error. You again compute your gradient at this particular point, right? Again, is the gradient in this particular, again at this particular point, positive or negative? The gradient is again negative, right? Now that the gradient at this particular step is negative, what do? You do the same step again. So your beta naught, new beta naught is going to be your current beta naught minus dou e by dou beta naught. Again, what's going to happen? Again, the same thing. Again, you're going to move from here to here. So you'll compute your dou e by dou beta naught over here again. Again, you'll move from here to here. Again, you move slightly towards the right side. So you're now over here, let's say in this particular case. What has happened right now? Your beta naught has moved from here to the newer step. What has happened right now in this particular case? Error is again lesser. Absolutely, yes. Reduce the error. Until when will I keep doing this? Until the slope becomes 0. When will the slope become 0? Absolutely, when we hit the minimum. When the gradient will become 0 here, because there is no slope anymore. Here, if you compute, there is no slope because your tangent is sort of sleeping. The angle is 0. So at this particular point, your slope. So you will keep reducing your beta until you come to this particular point. So I'll continue to do this until I hit this particular point. Now, somebody might say, hey, look, this is all great, but what if I started on the other side? What if I started on this side? Well, great. I mean, if you've started on this side, then the gradient is going to be positive. If the gradient is going to be positive, you again do the same thing, dou e by dou beta naught. This gradient is going to be positive. Here it's negative on this side. The gradient here is positive. So if you substitute a positive value here, beta naught is equal to beta naught plus is equal to beta naught minus a positive value. So at this particular case, here is where you started your beta naught with. So you've reduced your new beta naught because this is a positive value. Any value minus a positive value will reduce that particular value. So your beta naught will move in this direction. So you're going to come here. Again, same. Again at this particular point as well.
your gradient is positive. Same, from here to here again, your gradient is positive, from here to here. So you will again continuously keep dropping until you reach your bottommost point, or also referred to as a global minima. This is basically referred to as a global minima. Is everyone fine until this particular point? Do we understand this? This process of reducing the error continuously until you hit the global minima is what is gradient descent. So because you're descending by the gradient, descending as per how your gradient decides. If a gradient is positive, you move here in this direction. If a gradient is negative, you move in this direction. If a gradient is positive, you move in this direction. But technically, this process of descending as per gradient is referred to as gradient descent. Are everyone fine with this until this point? Brilliant. Okay. So now going back to the biggest learning out of all of this process is this update step. Doesn't this update step look very similar to what we did a while ago earlier? Similar, or is it exactly the same? Isn't this exactly the same? Except for this one single term that you see there. Except for the eta term, everything else looks the same. That's it. So all this while, whatever we've been doing was gradient descent. But we were trying to do it intuitively. But technically, when we say we are doing something like that, what was happening is this. At the background, the error was simply getting reduced. Right. Okay. So yeah, just imagine you can actually solve a linear regression problem also using the same approach. I hope you all can see the screen right now. Same thing, nothing very complex. I hope you can see these red points over here. These are like the red points, red dots. And that's like your equation. Those are like your data points. You have your x1 and x2. So just to kind of add some context. So just to kind of add some context, these points that you see over here are like your data points. And what we are saying is that, hey, look, we'll start with a random equation, random linear equation, minus 900 minus 0.1 times x. So I'm randomly initializing my beta naught and beta 1 time. I'm randomly initializing beta naught and beta 1. And I'm saying, I'm trying to predict the price of the house with respect to the size. This is my y that you see over here. This is y. And what you see here is nothing but my x. Now on this side, on the other side, there are two parameters, theta naught and theta 1, or beta naught and beta 1, doesn't matter. At the end of the day, they are the same. So you see theta naught and theta 1. What you see, this is called essentially as a contour plot. But basically, the way I want you to imagine this is basically like a bowl. Think of this like a bowl, right? If you see, the larger circle is basically the topmost layer of the bowl. And as you come closer, you get to the bottommost side of the bowl. So think of it like, I'm unable to write on this for some reason. Yeah, so think of this as basically this is like the bowl. This is how the bowl is. And this is the bottommost layer of the bowl. I hope it's basically like this. So think of folding that particular sheet as a bowl, right? And what we're saying is that we're starting this with this random equation where we're saying your y is equal to beta naught plus beta 1 times x is, or in this case, theta naught and theta 1. That's how I've represented it. This is like an old slide that I have. And y is simply nothing but my price, and x is simply nothing but my size of the house that I'm trying to figure out. Cool. So we started with a random line where beta naught value is equal to 900 and beta 1 value is equal to minus 0.1. I started with some random values to start with. But then I want to find those particular values of beta naught and beta 1 such a way that my error is the lowest. So with beta naught as 900 and beta 1 as minus 0.1, I was at this particular point in my error. You see this point? This is where I was on the error. I want to get to this bottommost point. I want to get to this particular point here because that's where the error is the minimum most. All of us are clear until this point? Do you all understand this chart? So I'm representing my linear regression line here, and this is my error plot, or your parabola, so to say. Brilliant. Okay. So now let's see what happens. Now what I've done is I've run one round of I've computed the error at this particular point, and I've made a change. So if you see at this particular point, the
value of theta naught and value of theta 1 are correspondingly over here. Now I make a small change. I make the update based on gradient descent. Look what has happened. I again make a small change. Look what happens. I again make another change. Now see, as I'm getting closer and closer, look what's happening to the blue line on the left side. Yeah, my best fit line, see where it is landed. My best fit line has got me to the bottommost point in that particular bowl. I hope this makes sense. Does this make sense, everyone? This is exactly what is happening with gradient descent. So you start with random points, completely random points, and then you start moving forward one step after another based on gradient. And as you keep making progress, you will see that your error keeps reducing, and as your error keeps reducing, your line keeps getting better and better. And at a particular point, you would see that the error is the lowest, and your line is sort of the best possible line across the data points that you have. This is gradient descent, right? Visualized in a way. Okay. That was for linear regression, and if it can work for the same concept, instead of linear regression, we are applying it for, because the error function is the same, instead of applying it for linear regression, we are going to apply it for your you're essentially going to apply it for your neural networks. But mind you, the only difference is line of best fit means that particular point where your error is the lowest. So the only difference is that between your linear regression and your and your neural network is applying gradient descent. The only challenge is going to be that in your linear regression, you just have beta naught and beta 1. But in the case of neural networks, in the case of beta naught and beta 1, and in the case of neural networks, the betas are actually going to be much higher, much larger, right? You're going to have 15, 20. Like, for example, a small network as big as this has how many? 1, 2, 3, 4, almost has 8 parameters that I have to tune. So imagine the same equation in 3 dimensions. The same equation in 3 dimensions looks like this. But imagine in 8 dimensions, how will this bowl look like? Imagine how that surface is going to look like. It will be super distorted. So take a piece of paper and twist it from both sides. That is how that plane is going to look like. So when your plane looks so distorted, what happens is that instead of having one minima, you may have multiple minimum points. Because think, if you twist a piece of paper or twist a piece of cloth, you will have many crests and troughs. You'll have one bottommost point, but you might have many crests and troughs. So if you were to sort of visualize it from like one dimension, it could look basically like this. This is basically visualizing it in one single dimension. You may have many crests and troughs. And the challenge that it would throw is that you may, because you are trying to solve using gradient descent, the challenge that it might throw is that you may start here and then you would descend, you would hit the bottommost point, and here the slope is 0. So dou E by dou W at this particular point is 0. So you'd basically stop here and say that, hey, look, this is the bottommost point. But in reality, that is not the bottommost point. So this point is referred to as local minima, because it is the minimum point, but in that locality, in that neighborhood. But in reality, you may have a larger minimum point somewhere else. So you need certain approaches. While the gradient descent algorithm is great, descending via the gradient is great. You technically want to descend to this particular point. But the issue would be that with many such minimum points, there is a likelihood that you might get stuck at a few places. You might simply get stuck over here, or you might get stuck here, or you might get stuck here. You might get stuck in a certain locality. And what that locality could do is it would cause you a lot of issues. It could basically get you stuck in that particular place, and you would require certain other techniques to get you out of that particular point. So you need certain techniques that can kick you out of that particular place rather than getting stuck in that point, right? So there are techniques like, for example, we use something called as momentum, we use something called as inertia, and blah blah blah. There are like 5-10 other techniques that we will learn as we go along with neural networks. The reason why you need to learn, so going back to the point of why should I learn all of this, is because at the end of the day, when you start building your neural network, you will have to set these parameters.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective as it is taught by IIT professors and industry experts.
Right? You'll have to set these parameters. What parameters will you set if you don't know what these really mean? I mean, how can you even tune an algorithm? How can you tune a decision tree if you don't know what depth? How can you tune a linear regression algorithm if you don't know what beta naught, beta ones, or whatever are? Right? It's basically parameters are nothing but hyperparameters. When I say parameters, that means when you've tuned the decision tree algorithm earlier, you must have set minimum observations in the leaf or depth equal to 4, depth equal to 5. You must have set some hyperparameters, right? Those are nothing but your that is what we mean by parameters or hyperparameters. They're not rules, Rahul. They are Rahul. Quick question: are you familiar with decision trees? Are you familiar with any other models? So if you're familiar with decision trees, when you build a decision tree classifier, you must have used certain. Yeah, I mean, if you want to call them rules, you can call them rules, but they're basically like certain metrics that you must have set at the beginning of the algorithm, saying, "Hey, look, I want only my decision tree to be 2 levels deep, or 3 levels deep, or 4 levels deep." So those are all called as hyperparameters. So yeah, that is parameters will have to change. The hyperparameters will change based on model to model, scenario to scenario, data to data. So yeah, the hyperparameters will change, and you will only learn how to tune them as you go along. That's exactly why I said neural networks have the capability to solve world hunger. It's just that training a model is super difficult. They have the capacity and the capability to solve the world's most difficult problems, but building the models is not very easy, right? So because they have a ton of challenges, ton of math that goes into it. It's not as simple as simply calling a function. Yeah. When incorrectly fit decision tree, neural network might actually perform even worse than a simple logistic regression or a decision tree algorithm. So yeah, it's basically like you have a calculator at hand. You need to know how to use it, else a fifth standard kid could beat us in mathematics. Fine, great. So now it comes to the there is one particular part of the neural network that we haven't learned, which is of course the eta element. Just going back to this point of, hey, look, this is how my thing looks like. What do you say? This is essentially how my error curve looks like. At times, what may happen is, this is where I'm going to basically explain why the learning rate is important. See here. So you've started here, let's say, with your beta. This is, let's say, beta naught, and this is your error. You started here, and you want to, let's say, make an update. Beta naught plus is equal to beta naught minus dou e by dou beta naught. Now you suddenly realize that this error or this particular gradient value is so large that when you do this beta naught, when you make this update, you are essentially jumping from here to here because you made such a large update. This value, this subtraction is so large that you ended up making a jump from one corner to one side of the curve to another side of the curve. Or it might also so happen that you started here and you ended up jumping to that particular point. Again, at this particular point, you again make a subtraction. You again jump from here to here because you made a larger subtraction. Again, you again move from here to here, again from here to here, again from here to here. So essentially what will happen is, instead of actually descending from here to here slowly, what is happening is you are starting to diverge on this particular curve, right? So to avoid a scenario like this, what you do is, instead of making a huge step size, you make a smaller step size. So you say, okay, eta times dou e by dou beta naught. So you control the step size rather than making a huge jump from here to here. You make a small step, you make a baby step. Okay, I'll move from here to here, and then 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 finally to the bottommost point, rather than making a huge move. So that's where the learning rate comes in very, very handy. Right? If the learning rate is very large, if eta is very large, what will happen? You will never hit the bottommost point. You will never converge. You'll end up diverging. You'll end up jumping from one corner to another corner. If the eta is very small, what will happen? If the eta is very small, what will happen? It takes a lot of time for you to get here. Exactly. The number of steps that will take you from getting from here to here to here to here will be very, very large, very slow learning. So you have to make sure that the eta is like optimal, and you'll have to evaluate the best possible value of eta as you go along. You'll have to try out different values of eta for different setups. So eta again becomes another tuning parameter for you. Will again become another parameter that you will tune while you build the model. So learning rate is one of the most important hyperparameters, most important parameters that you will end up tuning as you go along. So long story short, eta is super important. Eta is called as learning rate, and a large learning rate means you can jump away from your you can probably start to diverge. Small learning rate means you're likely to take a lot of time to converge. You essentially want a optimal eta value so that you kind of converge at the right time. Why is it called a booster? It's never called a booster. It's called a learning rate. Where is it mentioned as a booster? It's a multiplier. It's not gradient booster. It is gradient descent. So I'm not sure. Maybe because typical values of I haven't ever heard of it, Amandeep, to be honest. Calling it as gradient booster. The gradient boosted is in GBM. That's a different model altogether. Gradient boosting machines is a different model altogether. That's completely different. That has nothing to do with this. GBM, gradient boosting machines, is a boosting technique. That's a different model altogether. That's not a neural network. Typical values of eta range from 0 to 1. There is nothing really complex over here. As simple as what we generally try out is we try out 0.1, 0.05, as the 0.01. Those are the typical values of learning rates that we generally set. What we use is we try out different values. Again, just like your decision tree. How do you know what is the best depth of a decision tree? You would never know what is the best depth of a decision tree. You try different values and see what works the best. Yeah, this equation, guys, is no different. It's the same thing. This is exactly the same. New weight, B is nothing but, let's say, your new weight is equal to old weight minus learning rate times gradient. Okay, it's the same exact equation. Is gradient descent applied in every neural network? Gradient descent is applied in most neural networks. There are different variants of gradient descent algorithms, and we will learn about it. So we're going to basically learn about different types of gradient descents. There are 3 popular gradient descent algorithm variants called batch gradient descent, stochastic gradient descent, and mini batch gradient descent. But I think for that, before we get into the detail, we'll just learn about first of all how does a training process typically look like, right? In the case of neural networks, how does a training process essentially look like? So let me just give you a small understanding about how a training process looks like. So what happens is, whenever you train a neural network basically goes through 3 steps, or 3 broad steps, but then the following steps. How many steps it takes? So the first one is, let's say, your data set. Whenever you look at your data, you can have, let's say, multiple features, x1, x2, xn, how many ever features you have, and then you have, let's say, your target variable. This is your target variable, and for all good reasons, let's say you have let's say 1,000 data points, or 1,000, let's say 10,000 data points. This is your data set. So now you have a network that looks like this, right? So when you, let's say, have n features, how many input nodes will you have? Anyone? You have n, or let's say you have 10 features and you have 10,000 data points. How many input nodes are you going to have? we are still talking about structured data problems. We're talking about linear regression, logistic regression, and we're talking about classification and regression. We have never talked about unsupervised learning neuroutine. As of now, we're still talking about classification, regression, straightforward problems. So yeah. So at this particular, sorry, just give me a second. Yeah. So yes, you are essentially going to have, if you have, let's say, n features or 10 features in this particular case, you're essentially going to have 10 nodes for each feature, basically x1, x2, and so on up to x10, plus one more, which is for your bias. Instead of x, I'm simply going to call it bias, b1. Yeah. So you're going to have 10 input nodes. So the first layer has 10 input nodes. And let's say you're solving a classification problem, a binary class classification problem. So you may have, let's say, multiple, uh, you essentially have, let's say, different architecture as you go along. And let's say at the end, in the last layer, you can either have two nodes at the end, or you can simply have one node also. That is also fine, because you're solving a binary class classification problem. You're just solving a two-class classification problem. You can simply have one node, and that could return a value between 0 and 1 with a sigmoid activation at the end. Or you can say, hey, look, I will have like two nodes at the end. But if you have two nodes at the end, what should you apply at the last? What activation should you apply at the last to get a probability that sums up to 1? No, softmax, absolutely correct. So I'll have to apply a softmax activation so that the probability that is coming out from here and coming out from here is going to be summed up to 100% or 1, so to say. So yeah, it doesn't matter. I mean, however you want to design your algorithm, you can design your algorithm, that design your network. That's absolutely fine. So let's say for the purposes of this particular example, I'm just doing like, let's say 1, and then you're applying, let's say, a sigmoid activation at the end, and then you have different. So basically, different. Yeah, let's say you have the network that basically looks like this. Now the thing is, of course, with so many different weights and everything, let's say you now have 10,000 data points. So now, how do you train your algorithm? So the way you do it is typically, so what you do is you first pass your first data point. Again, this is basically different ways of training your model. So what you can do is you can essentially pass like first data point, second data point, third data point, fourth data point, essentially run a forward pass for all 10,000 data points. This is a training step, guys. Forward pass for all 10,000 data points. I hope you understand what I mean by that, right? So if one first data point will go through a forward pass, you'll get a prediction. Then for the second data point, will go through a forward pass. Third data point will go through a forward pass. All 10,000 data points will go to a forward pass. Once you go to all 10,000 data points in a forward pass, what are you going to get? With the randomly initialized weights, what you're going to get is you're going to get 10,000 predictions. You're essentially going 10,000 predictions. So with the 10,000 predictions, what do you do then? You compare these two, and what you get out of it? You compute the error. Absolutely correct. You then compute the error. So first, what did you do? You randomly initialized weights. Second, what we did is we run a forward pass for all data points. Third is you calculate the error computation. What is the fourth step? What is going to be your next step? Back propagation. Absolutely right. So when you compute your error computation, which is nothing but mean squared error or whatever, this is a classification problem. So it is likely to be log loss or categorical cross entropy. There are different error loss functions. We'll come to that later on. But basically different loss functions. And then once you compute an error, what you do as a fourth step is you then do your back propagation and weight updates. Yeah, back propagation essentially includes your gradient descent. Gradient descent is one way, correct. If you get expected error, then why should we do back propagation? I mean, if the error is very good at the first go, then you don't need to do back propagation. But then that's the whole point. I mean, what are the odds that you will get the best possible error and word in first go? Because you're talking about what 1, 2, 3, 4, 5 threes, 15 weights over here, plus 3 more weights over here, essentially 18 weights, and you're randomly initializing all 18 weights. And then you're saying that you're likely to get the best possible model in the first go. It is more than unlikely, Debashish, that you will get the best possible model in the first go. is there any range to what values? No, there is no range. Essentially what you do is we generally set a, between 0 and 1. What we do is between 0 and 1, we use this as a uniform distribution and assign weights. Between 0 and 1, okay, if that's what you were asking. Typically we do a uniform distribution between 0 and 1 to set value. So when I say 10,000 observations over here, guys, this is basically 10,000. The train test split must have already happened by now. This is only 10,000 train data points. Your test data is sitting separately by now. This is just training data set. These are the 4 things which all the nodes will do, right? Yeah, absolutely. These 4, every node. No, so the error computation will happen not at each node. The error computation will happen once the predictions are generated for the first pass. So everything else, like for example, weight updates and backpropagation will happen for every other node. Forward pass will also happen through every node, and random initialization will happen to every weight. So this happens to weights, this happens to data points, this happens at the outside of your data points. Only the weight updates happens to every weight, so to say. These nodes are and fields are parameters, right? The whole thing will happen for each record, and that's absolutely true. So when you say parameter, so yeah, I mean each weight you can assume that as a parameter. That's what those are called. If you're referring to model parameters, then yes, the hyperparameters are different from this. But yeah, is there any other method for weight initialization? There are different ways for weight initializations. There are more advanced techniques for initializing weight frames in there. But yeah, I mean the most frequently used technique is basically a random initialization with uniform distribution. But of course, there are different ways of initializing weights. There is a Monte Carlo simulation approach towards assigning weights, and so on and so forth. So different approaches are there. Cool. So yeah, let's basically get to once you do these 4 steps. By the way, you did one round of forward pass and 1 round of back propagation. This is basically referred to as one epoch. This is basically referred to as one epoch. 1 round of forward pass and back propagation is called as one epoch. Now that you've done a back propagation, so now what do? You again then go back and run another epoch. Another epoch is again you run through the forward pass, again do error computation, again perform back propagation. That's going to be another epoch. So you keep running multiple epochs, and let's say you probably run through 10,000 epochs or 1,000 epochs or 100 epochs until you get to a certain level of error. Okay, so this is the concept of, this is essentially how the training process really gets started, so to say. Can we set weights to single value instead of randomly? So yeah, there are multiple researches that have happened. So for example, the question is, can I set my weights to zeros? Can I set the same weights? So yeah, I mean, there are different approaches that we can try, and there is like no one best solution. The typical way of doing it is you randomly initialize so that you have enough randomness within your network, and then so that your signals actually get passed all the way through till the end, and the back propagation actually should make sense. If you set everything to the same value, if you set everything to zeros, then it might so happen that the outputs from one node could counterbalance the outputs from other nodes, and that way your network, you would see a lot of dead neurons or dead nodes in your networks. So one of the best practices is that you randomly initialize so that you hope for your network to actually pass values through all the way till the end. Your forward pass should actually make sense. Else you might see that certain neurons are just not passing any values through to the next layer at all. So setting the same values could cause issues like those. Okay, not the 4 steps. The first step will happen only at the beginning of the training process. Steps 2, 3, and 4 together is an epoch. Step 1 only happens once. Step 1 happens at the beginning of the complete training process. Okay. Can we say until 0 gradient? It's not 0 gradient, it's essentially 0 error. But then you would never be able to get to 0 error because there are so many weights, and because of those many number of weights, it's highly unlikely you'll get to 0 minimum error. So what you will see is during your process, one of the things that we are going to do is you can actually plot, you can create a plot like this. Like for example, this is like, let's say your error, and this is your epoch, and across 1, 2, 3, 4, across multiple epochs, what you will see is your error will start to reduce and it will sort of flatten out after a certain point. So then you can say that, hey, look, there's no point in training it beyond a certain point. I'll probably stop at this particular epoch. You can actually create this particular curve, or you can manually visualize the numbers, right? You can start manually visualizing numbers saying, hey, look, beyond a certain point, I don't see my error actually going up or going down. So I'll probably just stop here. And that is probably the point that I'm going to initialize. That's the point. Those are the number of epochs that I'm going to run my model for. Generally, what you do is you set a very high value for epoch to start with, and then you don't change the epoch values because it's basically run multiple times is what you're asking your model to do. You just change other hyperparameters and you monitor this curve. You hope for this curve to go down. So again, for all you know, this might not be like always a curve that is going down. I mean, you might have ended up setting parameters in such a way that your model is actually going all this way, and then it might not even actually, significantly go down beyond a certain point. This curve might look completely random as well. At times, this might actually start to go up as well based on the parameters that you've set. Or when I say parameters, I mean the hyperparameters that you've set to your model. Your learning rate and everything you've set so erratic learning rates, and your model architecture is so bad, then what may happen is that you'll start to see that this thing can actually look completely random as well. So yeah, don't always assume that this curve will always look like this. No, it will always not look like an elbow curve. Are there any methods other methods for backpropagation to reduce error? Yes, absolutely. Yes, there are. We will talk about them in the next few steps. Gradient descent is one way of performing backpropagation, but that's not the only optimization technique that is available. There are other optimization techniques as well. One of the optimization techniques that we will learn about is essentially called as there are other techniques, like for example, one of them is referred to as Adam optimizers. There are different optimization techniques. We will come to it when we get there, probably in the next few steps. Can you explain what decides to use the input for each perceptron? For X inputs, do we have to input all the points to each perceptron? No, so that's not what you're doing right now. When you say X inputs, what do you mean? X inputs in this particular case are input nodes. The whole thing is now not a perceptron. It's basically a network now. Individually, probably we called something like a perceptron or a single layer perceptron as this. This was a perceptron, right? A single layer neural network was basically like a perceptron. This is not a perceptron anymore. This is basically a multi-layer perceptron, or like or almost like a network, so to say. How do we select the number of epochs? Deepali, I think I answered your question. You don't set the number of epochs. You basically set the number of epochs originally to a large value, and then you just hope for your model to get to a lower error. And then you identify what's the best number of epochs based on that particular curve. So you see until what epochs your model is doing well, and then after that you say that, okay, with these hyperparameters, with this learning rate and this particular this kind of architecture, I'll have to run it for, let's say, 200, 300, 400 or 500 epochs based on that particular curve that you just draw. It will stop automatically in case reached minimal error in epoch 800. Well, there are certain conditions that you can set in certain frameworks called as early stopping. Again, if you all have tried XGBoost or gradient boosting, you would be familiar with something called as you would actually be familiar with this complete process of running it through multiple epochs and everything. Looks like none of you all have actually gone through your learning of gradient boosting machines. But the point simply being that I would strongly suggest you to actually go back and look at how gradient boosting machines and everything work. It's very similar to that. But long story short, I think the way it works is there are certain conditions called as early stopping criteria. Certain frameworks, like for example Keras, or let's say there are certain frameworks like PyTorch, they allow you to set early stopping. That means if, for example, after let's say 800 epoch you don't see any improvement, you actually can ask the learning process to halt. So there are certain ways to control that kind of a learning process as well. Control it using that as well. It's not available in all frameworks. Certain frameworks suggest, help it. It is framework dependent. These are all cool functionalities to have. So it's basically framework dependent, I would say. Weight initialization techniques. Image recognition requires a different kind of, or there are certain weight initialization techniques that work really very well for image recognition, for computer vision, for natural language processing. Different techniques are available. I am not saying that we're not going to learn it. I'm just saying that we're too early in the game for us to worry about it at this particular point. Right now, the best approach for us is to start with a random initialization. We'll get to those as we get there. Okay. Error will never be completely zero, Rohin. It will always be close to zero. You'll hope for the error to become zero. It will be very difficult for us to have an error zero. It's like can you have a model with 100% accuracy? Can you build a model with like 100% recall, 100% precision? If something like that actually happens, then that means there's something completely wrong with the model itself in the first place. So it's unlikely to have 100% accuracy or 100% precision model. So similarly, it's 100. When I say error, that's exactly what I mean as well. Error means this is all training and testing error. So yeah, it's impossible to have a 100% accurate model. Okay, brilliant. Again, as I said, as the number of epochs increase, what's likely to happen is that you're likely to move from underfitting to overfitting. Because more number of epochs means more amount of training. More amount of training essentially means more number of times that we retrained our features. We updated our weights, and more number of weight updations essentially means that we have we've essentially trained the model in such a way that it can actually capture a lot of patterns within your trained data set, and what that could yield to eventually is a good amount of overfitting as well. So in all fairness, you do not want a model that is overfitted. So you would require certain ways of handling overfitting. Just like in decision trees, how you have certain ways of handling overfitting, similarly, even in the case of neural networks, you will have certain approaches to handle overfitting and underfitting scenarios as well. But yeah, to to learn more, you have to basically run more number of epochs. That's basically one of the most important things. We'll come to this in a minute, but basically, I think it's important for us to understand that a typical neural network is likely to go through. A typical neural network is basically likely to go through different kinds of optimization algorithms, and as I said, gradient descent has multiple variations. So gradient descent, as I said, has different variations. One is called batch gradient descent, stochastic gradient descent, and mini batch gradient descent. If you remember, we just spoke about how differently these are like the 4 steps that are involved in actually training a model. But at times, what may happen is that batch gradient descent is basically where, take for example, like you have these 6 data points, 1, 2, 3, 4, 5, 6. And if, for example, you pass all your data at the first time, you take the complete data set at the first pass, and then you basically do a forward pass of all your data points, and then after all the points have been done a forward pass, then you basically do a back propagation for all your data points at the same time. That's basically referred to as batch gradient descent. Right? Batch gradient descent is like a regular gradient descent process. Right? Nothing really different. What you do is you just basically take your forward pass for all data points. This process is basically a batch gradient descent. You forward pass for all data points, you compute your error, and then you backward propagate. Then you again do forward pass for all data points, compute error, and then you back propagate. So basically, this is like a batch gradient descent is like one approach. If there's something called as stochastic gradient descent. Stochastic gradient descent is basically another extreme of batch gradient descent. So what will happen is, in the case of stochastic gradient descent, you do forward pass for one data point, then you do back propagation, then again you do forward pass for next data point, then you again do back propagation, then you again do forward pass for the third data point, then you do back propagation. So one epoch in that particular case is still going to be to run through all data points. One epoch is essentially the pass to, basically a pass of all data points. So one epoch is going to have n number of back propagations that will happen in between, right? So you will forward pass for one data point, then you back propagate, forward pass, back propagate, forward pass, and back propagate. Once all the data points are done, that's when you call it as one epoch. Yeah. So that's basically called a stochastic gradient descent. It's like a SGD is what we call it as. That's like another extreme. A midway between these two is called as a mini batch gradient descent, or a batch gradient descent. A mini batch gradient descent. A mini batch gradient descent is
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
is where you say that, hey, look, I'm going to do backpropagation, but this time I'm going to do backpropagation for a batch of data points. So, for example, if you have, let's say, 10,000 observations, so you're going to create 10 batches of 1,000 data points each. So you pass 1,000 data points, then you do your error computation, doing your backpropagation. Then you pass your next 1,000 data points, error computation, backpropagation. Then pass the next 1,000 data points. So until all the 1,000 data points are complete, that's when you call it as one epoch. So I'll just simply repeat. One, if you basically pass all your data points at the same time and then do your error computation and backpropagation, that's called as a batch gradient descent. If for every data point you're doing your batch backpropagation, that's basically referred to as stochastic gradient descent. Then mini batch gradient descent is when you basically pass small batches of data instead of the complete data set. That is essentially referred to as when you pass, let's say, a batch of 10 or batch of 100 or batch of 1,000 data points, and then you do a back propagation. That is basically referred to as mini batch gradient. Okay. Yeah. So tips basically is plot your cost versus time. Time is essentially nothing but number of epochs, right? So error versus time, error versus number of epochs. You can basically plot error versus number of epochs. You can see if your learning rate, if your model is actually increasing or decreasing, you're in error over time or over epochs. You can actually have a look at it. Learning rate, super important. As you can see, learning rate value is a small real value. This is 0.1, 0.01, 0.001, and so on. You can try basically different values and see what works the best. Rescale inputs, this is like a super important data point. Algorithms generally are perform well when your data points are sort of scaled between 0 and 1 or -1 and +1. So it's always a good practice to scale your data points, or rather normalize your data points before you build any neural networks, so to say. Just like how we've implemented like gradient descent, similarly you also have different other optimization algorithms. We have optimization algorithms like, for example, ADAM. ADAM stands for adaptive moment estimation, or ADAM simply. The only difference is, of course, between stochastic gradient descent or gradient descent and ADAM optimization is that ADAM basically has a couple of more additional features in the algorithm, so to say. So just to kind of give you an intuition, the way ADAM is different from ADAM optimization is different from your SG or from your gradient descent is that, in scenarios like these, ADAM optimizer actually works well. Firstly, let's talk about what we mean by momentum. Sorry, first let's talk about adaptive learning rate, and then we'll come to momentum. ADAM has two additional features. One is called adaptive learning rate, and the other is momentum. Adaptive learning rate is simply nothing but, when you're far away, your learning rate, if you remember, we said that in your weight updates is equal to current weight minus eta times your dou E by dou W. That's basically your weight update step. And what we said was this particular error that you're talking about, that this particular learning rate is sort of, we said that it's a constant value, sort of. So you kind of think of it, you can basically have if you sort of think of it. So if, for example, when you start very, very far away, and when you progress from here to here, the way you would want it is that your model starts to accelerate, make larger steps here, and as you come closer, you start making smaller steps. So you want your step size to be extremely large at the beginning, but you want it to become smaller and smaller as it comes closer, so that you want to make sure that you kind of get to the minimum most point as perfectly as possible. So this point of trying to have a very high learning rates at the beginning and smaller learning rates at the end is what smaller learning rates as you get closer to the minima is what is referred to as adaptive learning rate. So ADAM has this additional feature from your gradient descent. So it doesn't use a static learning rate or a constant learning rate. Rather, the learning rate varies from here to here. So as you get closer to your minima, your learning rate tends to decrease. But at the farther points, the learning rate is actually much higher. So that you approach your minima quickly, and then you slowly try to reach your minimum most point. Else, what may happen is that with a very small learning rate, what may happen is at the beginning itself, you might start making baby steps, and you might end up reaching your minima very slowly. So that way, the adaptive learning rate sort of accelerates time to minima. That's number one. Second thing is called as momentum. Now, the thing about momentum is something that will really help, especially in scenarios where you have larger networks. Imagine you have scenarios like these. Imagine you have scenarios like these, where you have really complex models, or where you basically have larger number of weights that you're trying to optimize, and then you have like a really complex surface that you're trying to find a minima in. What momentum basically does is, momentum essentially gives you a way of getting to your minima very quickly and not getting stuck at these minima points. So what momentum helps you is, right at the beginning itself, you have some level of acceleration. So simply put, if you're basically stuck here, what your momentum does is basically kicks you out from this minimum point. Because it has some amount of speed, through which it kind of descends. The descending sort of happens with some amount of speed, or some amount of velocity. So that way, what happens is you sort of descend very quickly to your bottommost point. That's essentially what is referred to as momentum. Momentum is, again, simply put, another term where it helps you not get stuck in your local minima. It helps you sort of kick yourself out of the local minima. So these are like certain enhancements on top of gradient descent that help the model do slightly better than a regular gradient descent algorithm, so to say. Now again, ADAM is not the only optimizer, so you can use gradient descent or stochastic gradient descent, or you can also use ADAM. By and large, ADAM optimizer and gradient descent the ADAM optimizer is much better than regular gradient descent, because it is sort of an enhanced algorithm, enhanced optimizer, so to say. It is basically gradient descent plus a lot of more other things. So yeah, with that sort of, let's dive into some amount of implementation. Let's actually start implementing a very simple model, firstly, without the use of any kind of a framework like a Keras or anything. Let's start to actually implement this using a very simple neural network. And let's actually implement it using, this is like the perceptron, let's say, a very small perceptron that you have. You have x1, x2, and then you have w1, w2, and then you have y, right? So imagine x1 is 2, x2 is 5, and y is 30. Y is supposed to be 31. And we have to find values of w1 and w2 that kind of help us solve for y. We have to find values of w1 and w2 which will help us solve for this particular y, or basically build this particular network out. I have to find corresponding values of w1 and w2 such a way that the error is the lowest. As simple as that. And my training data point is x1 2, x2 5, and y is 31. One single data point right now. I'm not working with many data points, a single data point is fine. Okay. So yeah, let's actually go ahead and start implementing this. Yeah, it's pretty straightforward. So what I'm going to do is, let's actually start writing some piece of code rather than so okay, I hope all of you are able to see my screen. I'm just going to call it simple neural network, and the way I'm going to, of course, do it is I'm going to start with simple initializations. I'm saying x1 is equal to, I think, what were the values that I had? x1 is 1, x2 is 5, and I have y is equal to 31. Right? These were the values that I originally started with, and And we also are saying that, let's say we start with some other metrics, like for example, I don't know what W1 and W2 are. I can start with any random values. It doesn't really matter. Let's say I start with W1 as 9 and let's say W2 as, I don't know, some value is 7 maybe. Yeah, maybe. I don't know. You can start with any values. It really doesn't matter. But technically, let's start with 9 and 7 or 8 and 3, whatever. Doesn't matter. So what I'm going to do is I'm basically going to first, we're going to build a simple neural network. And my network basically is going to look like this. So my network simply looks like this. I have two inputs, x1, x2, and the output is y. And I have w1 and w2 as two weights over here, right? So my output y, my equation is basically my forward pass is simply going to be what? Anyone? What is my forward pass typically going to be like? Anyone? What is going to be my forward pass formula? Yeah, perfect. Absolutely right. That's what it is going to be. So it's going to be x1 w1 plus x2 w2. As simple as that. Pretty straightforward. Nothing overly complex. Very, very simple. That's my formula. So remember the 4 steps. The first step is randomly initialize weights. Right? Randomly initialize weights, and we initialize w1 as I think 9 and w2 as 7 or something like that. The second step is perform a forward pass. The third step is I need to do some error computation. So how do I do my error? My forward pass is in this case x1 w1 plus x2 w2, and my error computation is going to be something like, you know, the actual value minus my predicted value, the whole square. I can also put 1 by n, but n is 1 anyways over here. I just have one data point over here in this particular case. So I can simply do a squared error or a mean squared error. It doesn't matter. There is no mean. I just have one data point. So actual value minus predicted value, the whole square. So this is my predicted value. And then fourth is I need to do my weight updates or my backprop basically. And in my backprop, remember, how do I update my backward propagation backprop? So I need to compute dou E by dou W1. And I need to compute what else? Remember, see, my update step is going to be this, right? W1 updated is equal to W1 current minus some eta times dou E by dou W1. Similarly, W2 plus is equal to W2 minus eta times dou E by dou W2. What is dou E by dou W1 and dou E by dou W2? How can someone quickly tell me? So my error, this is my error, remember. So if I have to do dou E by dou W1, it's going to be dou by dou W1 of y minus x1 W1 plus x2 W2, the whole square. So the actual value minus x1 W1 plus x2 W2, the whole square. Essentially, this is what I need to do. Agreed, everyone? I need to differentiate this essentially. So when I actually differentiate this, this is going to be dou E by dou W1 is going to be any question on this point. I hope all of you are clear till here. Yeah, correct. Absolutely right, Sushira. Yeah, error because of that particular weight. I'm sorry, I'm not fully looking at the questions as we write because I'm just doing this separately. But anyways, dou E by dou W1 is simply going to be minus x1 into y minus x1 w1 plus x2 w2. Essentially, that's what it is going to become. Yeah, or this is nothing but your forward pass. This is nothing but your y hat. This is y minus y hat, right, whole square. And similarly, dou E by dou w2 is going to be minus x2 times y minus y hat. That's what it's going to become. Yeah, we don't know the actual value. We're going to come to that. Absolutely, we don't know the actual value. We're going to compute it as we go along. So I just want you to kind of understand that this is the math that goes behind it, right? So now what we're going to do is basically we're going to use this, and then we're going to try and update, and we're going to try and build this small algorithm over here. Let's also start with a small learning rate, guys. Let's say I start with a learning rate of 0.01 as a very, very small learning rate that I'm starting with, right? So for I in, or for rather epoch, number of epochs, right? For epoch in range of, let's also set the number of epochs. Let's say 100 epochs, range of epochs
So for each epoch, what I wanted to do is I want basically to firstly do a forward pass. First thing is forward pass. So it's going to be y predicted. I'm just going to call it predicted value of y is going to be x1 into w1 plus x2 into w2. That's that's basically our forward pass. Here is where next I'm going to do my error computation. Remember, what is my error computation? My error is going to be y minus y hat the whole square. I just started with some, Nuruddin, I just started with some random number of epochs. I just said, epochs of 100. We'll figure this out. I don't know how many epochs it has to run. I mean, to be very honest, I still don't know what these values are supposed to be. These are random. This is given. This is like the given values, given train data. This is random initialization, and these are parameters to train or hyperparameters of the model. Need to be tuned. I don't know what is like the best value. I have to sort of tune this. Also remember, I'm never going to have just one data point. I might have like, let's say 1,000 data points. So in that case, my forward pass will be again basically for 1,000 data points. I can never, if I want to just do it in like one line, it'll be a little tricky for me to do it using doing it this way. It's easier for me to kind of implement it using NumPy arrays and matrices. Okay, cool. So my error, or maybe we'll just mention it as E, maybe it'll make it easier. Error E is going to be, actual value, which is my y minus y underscore predicted whole square. Actual minus predicted the whole square. This is my error computation. Now comes the back propagation or weight update step. For back propagation, first thing that I need is dou E by dou W1, right? So basically I need dou E by dou W1. And similarly, I would need dou E by dou W2. Remember, I need both the gradients. I need both the gradients because once I get the gradient, that's when I can run my back propagation comfortably. So I need my gradient. So if you remember, my gradient is going to be, by the way, I've just forgotten something. I have a 2 here. So when I actually run the gradient, I'm going to have a 2 here as well. Minus 2 times. So if you see minus 2x1, y minus y hat. So it is going to be minus 2 into x1 is nothing but x1 times y minus y hat is nothing but this value. Similarly for dou E by dou W2, it's going to be minus 2, but this is simply going to be x2 instead of x1. This is dou E by dou W1, but this is my back, or rather, I'm simply going to say gradient computation. Last but not the least, my weight update step. So my new W1 is going to be current W1 minus, quickly, what should I do? My new W1 is going to be current W1 minus, is it going to be directly dou E by dou W1 or multiplied by learning rate? Absolutely correct. I have to multiply it by eta. So it's going to be dou E by dou W1 multiplied by learning rate. Similarly, this is when weight 2 is going to be weight 2 minus dou E by dou W2 multiplied by learning rate. Perfect. And yeah, that's it. So what I'm going to do is once I do this, right? So I'm just simply going to put a print statement over here. So that for every epoch, I have prints coming through. Firstly, we're going to say epoch number, epoch, and I'm also going to get error is going to be, sorry, round off. They're going to round E to like third decimal or something, or second decimal maybe. And I'm also going to, let's say, print W1, same again.
maybe I'm just going to print W1 and W2 for like 3 decimals. We don't know if okay, cool. Everyone okay until this point? F is a formatted string. Thank you so much. This is W2. Thank you so much. Yeah, thanks. Okay. Looks good until this particular point. So let's run this. Cool. Okay. Let's just run this. Let's see what happens. There you go. And look at this. The error has already become 0 here. I don't even need to run it for like so many times because looks like it doesn't seem to. If you observe, it's running for so many times, but actually already on the 20. Where did we go? Like right here. Already here we see that the error has become almost 0. Almost at epoch 8, my error has become like 0. So what you can do is, for example, you can actually capture your error and you can capture epoch, or rather simply just capture error error dot append of e. Yeah, so you basically have, firstly, if you observe, my model is trained, and that it's basically saying that it's basically trained, and it is saying that for a W1 of 8.501 and W2 of 4.5, the error is 0. So you can basically put W1 as 8.5 and W2 as 4.5, and we should ideally get an error of 0. And we can verify that. 8.5 and 4.5, and if you substitute 8.5 and 4.5 with x1 W1 and x2 W2, you should basically get y as 31. And we can verify that. So like, for example, you can go back here and you can just do a quick this is 8.5 and this is 4.5. I think the x1 was 5 and x1 was 1, right? 1 and 5. So this is going to be 8.5 plus 4.5 times 5. And that is typically going to be, I think, 22.5. 22.5. This is 31, clearly. So you kind of got the right weights. We were able to sort of compute the right weights using the metric over here. Additionally, what we've also been able to do is we sort of captured the error as well. So let's actually plot percentage matplot lib inline, and then let's quickly do a error plot. So we can simply do a plt dot plot of we can simply do a quick plotting of the error. Now this is basically on your x-axis. If you observe, this is nothing but your epoch number, because epoch number from 0 all the way until 100, if you see, this is how your epoch is typically varying. So your your error sort of drastically drops, and after that it sort of flattens out. Yeah, clearly showing the kind of behavior that we were sort of talking about a while earlier. It sort of drops, and then after that it sort of flattens out beyond a certain point, right? Yeah, I mean, I just hope. Do we have any questions until this particular point? Are all of us sort of clear with what we are seeing here? Are all of us sort of okay with this simple neural network that we are seeing here? Yeah, that's it. If you know this, if you are able to understand this, then you basically understood the fundamentals of your what do you say of neural networks. The most important fundamentals, of course, not that. Yeah, somebody's basically asking me, can you actually change the learning rate? Yeah, absolutely. I'll probably reduce the learning rate a little bit, and you see what will happen. Look, and I'll just quickly plot it. Maybe you'll realize it. Look what has happened. With a smaller learning rate, do you see what's happening? This was with any learning rate of 0.1, and this is with a learning rate of 0.01. And you see that the learning has actually taken a little longer than expected. Yeah, right now there's no best learning rate, because you just have like one single data point. So your learning rate will simply directly impact the time. That's about it. But if you have more number of data points, that's where things can get a little trickier. Yeah, more number of data points means more issues. So that's where things can be a little more tricky, so to say. Okay. So yeah, that's basically where you'll have to try with typical learning rates will be somewhere around 0.1, 0.01, 0.001, and so on. Okay, so that's great. Now that we all have understood this, yeah, and we can essentially try out a couple of other things as well. Like for example, you can say, hey, look, what if I have, instead of one single data point, what if I had, let's say, two data points? I basically have, let's say, x1, x2, and y. If, for example, instead of one single data point, what if I had, let's say, two data points? For example, I had, let's say, 1 and 10, and something like 5 and 15, 5 and 1. Let's go for 5 and 1. And my outputs are, let's say, 2, 12, 12. Let's say it's 12, 12. Yeah, let's go with 12, 12. So in this particular case, let's go with 11, 12. Okay, these are like my inputs right now. So that means essentially what I'm saying is that I have like two data points. My data set is this. My data set essentially is I have x1, x2, and y. I have 1, 10, 5, 1, and then this is 11, and this is 12. This is how my data currently looks like, let's say. So with this kind of a data, then if you have to sort of now start implementing the same thing, that's where things can get a little tricky, because now what you have to do is now you don't have a single data point. Instead, what you have is now you have an array of data points. So then your error computation is not going to be something as simple as this. Because then what you will have to do is you'll essentially have to put a for loop over here and then run the multiplication for run your error computation for both the data points. Similarly, your gradients, it's not going to be as simple and as straightforward as this, because now you just simply don't have one data point. You have many data points now, so your weight updates have to typically happen. Your weight updates typically have to happen for each data point, so to say. So things can get a little tricky. We can still try implementing a stochastic gradient descent. Like for example, for every data point, you can sort of go ahead and you can perform your backpropagation. Then on another data point, you'll go ahead, update your backpropagation. So you can keep doing this for multiple data points. You can still try doing it, but then things can get a little trickier. That's the point that I'm trying to drive. So like for example, what you will have to do is the same thing. It's just that for I in range of len of, because you have two data points, x1, simply I just put x1, and instead of x1, let's say input, just calling it. So, and what I'm simply going to do is y underscore predicted, simply x1 is equal to x1 underscore input of I. So it's the same thing, guys, same approach that I'm taking, but this time what I'm doing is, you understand why I'm doing the for loop, right? This for loop is basically for each data point. For data point number 1, for I in range of len of x1 underscore input, that means for I in range of these two data points. First, I'm going to use 1, 5, and 11 to train, and then update my weights. And then again, I'm going to pass 10, 1, and 12, pass, train, and update my weights. And that way, at the end, that is basically going to be one epoch for me. And then I'm going to run one more epoch. So I'm going to do the same thing again. Let's quickly try. And maybe I'll initialize this with, let's say, randomly initialized 1 and 1. Let's go with 1 and 1. Okay. Yeah, there you go. Almost after, yeah, look at this. Almost after, where did my error become 0? Almost after the third epoch, my error became 0. Yeah. So simply put, almost like here. Let's plot this until the third decimal, maybe. I've reduced the learning rate a bit, but technically what we are saying is that for W1 is 1 and W2 is 1, W1 is 1 and W2 is 1 approximately, the error is almost 0. So if you put W1 is 1 and W2 is 1, your error is likely to become 0. So if you put 1 into 1 plus 5 into 2 should be 11, which is true. And 10 into 1 plus 1 into 2, which is 12, which is also true. So W1 is 1 and W2 is 2. That's the actual values.
so to say. So yeah, that's the other side of things. Same thing here as well. Yeah, same thing, just that I've implemented it for more than one data point right now. But this time I'm not implementing a single, I'm not implementing a batch gradient descent, but instead I'm implementing a stochastic gradient descent. The reason why I'm implementing a stochastic gradient descent is because I'm updating my weights every time I do a forward pass. I'm doing a forward pass, I'm updating my weights. Again, I do a forward pass for the second data point, I'm updating my weights. So I hope you understand how this is different from what we did earlier. The only difference is I put this small for loop. But what this for loop is doing is it's basically iterating through each data point, and then it's trying to help me compute my error and then update the weights both at the same time. So that's why this is like a slightly different approach than what we had done earlier. Earlier it was just one data point. Here it is two data points, same thing, but I'm doing it one data point after another. So the backprop is happening for every data point. So with a small change, I've sort of implemented a stochastic gradient descent here. Now it doesn't matter how many other data points that you add here, it'll still be the same. Yeah, you can basically add as many data points as you add here and same here. Doesn't matter. It'll still be the same. Okay.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.